somewhere in the constellation Cygnus. A spacecraft spent nearly a decade staring at the same patch of sky without ever looking away. 150,000 stars held in its unblinking gaze. Night after night, year after year, watching for the faintest flicker of shadow that might mean a distant world was passing in front of its sun. The Kepler Space Telescope was not built for speed or spectacle, but for patience, for the slow and quiet work of catching light, measuring its dips and tremors, and finding in those tiny changes the signatures of planets no human eye could ever see. It was a mission of stillness, of waiting, of trusting that the universe would eventually reveal what it had been hiding all along. If these gentle journeys through science and space bring rest, staying close to the channel will bring more nights like this one. And so, with Kepler's long watch as our guide, the story begins here. In the quiet corridors of NASA's Ames Research Center, nestled in the heart of California's Silicon Valley, a scientist named William Borucki spent the better part of 4 decades pursuing a single, elegant idea. His was not the kind of scientific career that makes for dramatic retelling, not the sort of story with sudden breakthroughs or moments of theatrical revelation, but rather a long and patient accumulation of work, of refinement, of gentle persistence in the face of repeated disappointment. The idea itself was beautifully simple, as the best scientific ideas often are, and it concerned the possibility that we might detect planets orbiting distant stars by watching for the tiny dimming of starlight that would occur when such a planet passed between its star and our telescopes here on Earth, or, better still, in space above our atmosphere where the seeing is steadier and the measurements can be made with exquisite precision. William Borucki arrived at NASA Ames in the 1960s. A young physicist with an interest in planetary atmospheres and a particular talent for careful measurement. His early work focused on Venus, that cloud-shrouded world that presents such challenges to anyone wishing to understand its atmosphere from afar. The Venusian atmosphere is thick and hot and wrapped in layers of sulfuric acid clouds, and studying it required Borucki to develop methods for measuring very small changes in light, for teasing out subtle signals from noisy data, for understanding how radiation moves through complex atmospheric systems. This work on Venus, seemingly unrelated to the detection of planets around other stars, would prove essential to everything that followed. The skills he developed, the mathematical frameworks he constructed, the intuition he built for working with faint photometric signals, all of these would become the foundation for his later work on what would eventually become the Kepler Space Telescope. By the early 1980s, Borucki had begun to think seriously about the question of extrasolar planets, those hypothetical worlds that might orbit stars other than our own Sun. At that time, no such planets had been definitively detected, though astronomers had long suspected they must exist in great numbers throughout the galaxy. The question was not whether such planets were out there, but how one might go about finding them. Various methods had been proposed over the years, including looking for the tiny wobble that a planet's gravity would induce in its host star, but Borucki was drawn to a different approach, one that made use of his expertise in precision photometry, in the careful measurement of starlight. The transit method, as it came to be known, relies on a fortunate geometric alignment. If a planet's orbital plane happens to be oriented such that it passes directly between its star and our line of sight, then once per orbit the planet will cross the face of the star, blocking a small fraction of the star's light. For a planet the size of Jupiter transiting a Sun-like star, this dimming amounts to roughly 1% of the star's total brightness, a change that is within reach of careful ground-based observations. But for a planet the size of Earth transiting a similar star, the dimming is far smaller, only about 1/100%, or 84 parts per million to be more precise. Detecting such a tiny change in brightness requires extraordinary precision and extraordinary patience, and it requires watching many thousands of stars simultaneously, since the geometric alignment needed for a transit is relatively rare and any given star is unlikely to have a planet oriented just right. In 1984, Borucki submitted his first formal proposal to NASA for a space-based photometer that could detect these transiting planets. The proposal laid out the basic architecture of what such a mission might look like, the precision required, the number of stars that would need to be monitored, the duration of observations necessary to catch multiple transits of Earth-like planets in Earth-like orbits. A planet orbiting its star at the same distance Earth orbits the Sun would transit once per year, meaning that to confirm a detection and measure an orbital period, one would need to observe the same field of stars for several years at minimum. The proposal was technically sound and scientifically compelling, at least in Borucki's view, but NASA did not select it for development. The technology was not yet mature, the reviewers suggested, and the scientific community had not yet embraced the search for extrasolar planets as a priority worthy of dedicated space missions. Borucki was disappointed but not deterred. He returned to his work, continued refining his ideas, and began collaborating with others who shared his interest in precision photometry and exoplanet detection. Among his most important collaborators was David Koch, a fellow scientist at Ames who brought complementary expertise in spacecraft design and instrument engineering. Together, Borucki and Koch developed detailed mission concepts, working out the specifications for a telescope and camera system that could achieve the necessary photometric precision while remaining within the constraints of a modest NASA budget. They calculated the size of the mirror, the number of pixels in the detector, the field of view required to monitor enough stars, the orbital parameters that would keep the spacecraft stable and allow for continuous observation of a single patch of sky. The mathematics of transit detection occupied much of Borucki's attention during these years. He worked through the statistics of how many stars one would need to observe to have a reasonable chance of detecting Earth-sized planets, accounting for the random orientations of planetary orbits and the varying distances and brightnesses of stars in any given field. He developed algorithms for identifying transit signals in noisy photometric data, for distinguishing true planetary transits from false positives caused by binary stars or instrumental artifacts. He thought carefully about stellar variability, about the natural fluctuations in brightness that stars exhibit due to star spots and flares and other phenomena, and how these variations might mask or mimic the signals from transiting planets. All of this mathematical groundwork was essential preparation, laying the intellectual foundation for a mission that did not yet have funding or approval. In 1992, Borucki submitted another proposal to NASA, this time under the Discovery Program, which had been established to fund focused, cost-effective planetary science missions. The proposal was again rejected. 2 years later, in 1994, he tried once more, and once more the answer was no. The reviewers raised concerns about whether the technology was ready, whether the photometric precision could truly be achieved, whether the scientific case was strong enough to justify the cost. Some of Borucki's colleagues at Ames and elsewhere gently suggested that perhaps he should move on to other projects, that perhaps this particular quest was unlikely to succeed and his talents might be better applied to problems with more immediate prospects for progress. Borucki listened to their advice, considered it thoughtfully, and then continued working on transit detection. The year 1994 was significant for another reason as well. Borucki organized a workshop at Ames Research Center devoted entirely to the question of detecting transiting extrasolar planets. The workshop brought together astronomers, physicists, and engineers from across the country to discuss the challenges and opportunities of the transit method. They reviewed the mathematics of transit detection, examined the available detector technologies, debated the relative merits of ground-based versus space-based observations, and considered the scientific questions that transit discoveries might help to answer. The workshop served multiple purposes, generating new ideas and identifying technical problems to be solved, but it also helped to build a community of researchers who shared Borucki's interest in this approach to exoplanet detection. It demonstrated that the transit method was not merely one scientist's idiosyncratic obsession, but a legitimate avenue of research that deserved serious attention. Following the workshop, Borucki and his collaborators began conducting ground-based tests of their detection concept. Working with the Lick Observatory in the mountains east of San Jose, they set up prototype systems to monitor the brightness of stars and searched for the characteristic dips that would indicate transiting planets. The ground-based observations were limited by atmospheric turbulence, by the interruptions of daylight and weather, by all the challenges that make precision photometry so difficult from the surface of the Earth. But they demonstrated that the basic approach was sound, that transits could be detected if they were large enough, and that the algorithms Borucki had developed for finding signals in noisy data actually worked. These tests, conducted through the middle and late 1990s, provided crucial evidence that a space-based mission could succeed where ground-based observations were limited. In 1995, the field of exoplanet research was transformed by a discovery that came not from transit observations but from the radial velocity method, the technique of measuring the tiny wobble that a planet's gravity induces in its host star. Michel Mayor and Didier Queloz, working at the Haute-Provence Observatory in France, announced the detection of a planet orbiting the star 51 Pegasi, a world roughly half the mass of Jupiter completing an orbit every 4 days. This was the first definitive detection of a planet around a main sequence star other than the Sun, and it electrified the astronomical community. Suddenly, extrasolar planets were not merely hypothetical, they were real, and the search for them took on a new urgency. The discovery of 51 Pegasi b, as the planet came to be called, changed the landscape in which Borucki was working, making his proposals for a transit detection mission seem more timely and more relevant than ever before. In 1998, Borucki submitted another proposal to the Discovery Program, and in 2000, he submitted yet another. Both were rejected. The reviews acknowledged the scientific merit of the concept but continued to express concerns about technical readiness and cost. For formal rejections over nearly a decade might have persuaded many scientists to abandon the effort, to accept that this particular dream was not to be realized, at least not by them. But Borucki had spent too many years thinking about this problem, had invested too much of himself in the mathematics and the technology and the vision, to simply walk away. He continued refining the mission design with David Koch and their growing team of collaborators, addressing each concern raised by the reviewers, demonstrating through laboratory tests and analysis that the photometric precision could be achieved, that the systematic errors could be controlled, that the scientific return would justify the investment. The spacecraft they envisioned would carry a single instrument, a photometer of unprecedented sensitivity, designed to stare continuously at a single field of stars for years on end. The telescope would have a primary mirror about 1.5 meters in diameter, feeding light onto an array of charge-coupled devices. The same basic technology used in digital cameras but developed to far higher standards of precision and stability. The detector array would contain millions of pixels, enough to monitor over 100,000 stars simultaneously, watching for the tiny periodic dips in brightness that would betray the presence of transiting planets. The spacecraft would be placed in an Earth-trailing heliocentric orbit, drifting slowly away from Earth and thus avoiding the perturbations and thermal variations that would come from orbiting our own planet. In this distant orbit, the telescope could maintain a steady orientation, keeping its eye fixed on the same patch of sky without interruption. The choice of target field was itself a matter of careful consideration. The spacecraft would observe a region in the direction of the constellation Cygnus, a field that would remain visible throughout the year and that contained a rich concentration of stars suitable for transit observations. Stars too bright would saturate the detectors. Stars too faint would not provide enough photons for precise measurement, and so the mission planners had to identify a field with the right distribution of stellar brightnesses and types. The Cygnus field satisfied these requirements beautifully, offering tens of thousands of stars in the right brightness range, many of them similar in size and temperature to our own Sun. Finally, in 2001, after 4 formal rejections and nearly 2 decades of development, NASA selected Borucki's mission for flight as Discovery Mission Number 10. The mission would be named Kepler, after the 17th-century astronomer Johannes Kepler, who had derived the mathematical laws describing planetary motion around the Sun. It was a fitting tribute, connecting the ancient quest to understand our own solar system with this new endeavor to discover planetary systems around other stars. For Borucki, the selection was the culmination of a journey that had begun in the 1980s, when the very existence of extrasolar planets was still unconfirmed and the idea of detecting them by their transits seemed to many like a distant dream. The years between selection and launch would bring their own challenges. The detailed engineering work of designing and building a spacecraft that could meet the exacting requirements of the mission, the testing and calibration of the photometer, the development of the software that would process the vast streams of data the mission would return. But the fundamental concept, the elegant idea that had sustained Borucki through all those years of rejection and persistence, remained unchanged. Watch many stars. Watch them carefully. Watch them for a long time, and the planets will reveal themselves through the shadows they cast. William Borucki's journey from that first proposal in 1984 to the mission's approval in 2001 is a testament to a particular kind of scientific temperament, one characterized not by flashes of brilliance or dramatic reversals of fortune but by steady, patient dedication to a worthy goal. His background in Venus atmospheric research, seemingly tangential to the search for exoplanets, had provided him with precisely the skills and instincts needed to conceive and develop the transit detection method. His willingness to organize workshops, to collaborate with engineers like David Koch, to conduct ground-based tests at Lick Observatory, to address each criticism raised by proposal reviewers. All of this reflected a comprehensive approach to scientific work that goes beyond having a good idea to include the hard labor of demonstrating that the idea can actually be realized. And so, as the 1990s gave way to the 2000s, the Kepler mission moved from concept to reality, from papers and proposals to spacecraft components being assembled in clean rooms, from mathematical algorithms to flight software being tested and validated. Borucki, now in the later stages of his career, would serve as the mission's principal investigator, guiding the science team through the years of preparation that lay ahead and the years of observation and discovery that would follow. The photometer he had imagined so many years before, the precise and patient eye that would watch the stars of Cygnus night after night after night, was finally going to be built. And when it launched and began its work, it would transform our understanding of planets and their prevalence in the galaxy, revealing a universe far richer in worlds than even the optimists had dared to hope. But that is a story for later sections of this account, and for now we may simply note that the approval of the Kepler mission in 2001 represented the end of one long journey and the beginning of another, the transition from dreaming about the stars to actually watching them, from imagining what might be out there to finally having the means to find out. In the high desert country of Colorado, where the foothills of the Rocky Mountains rise above the city of Boulder, a team of engineers and scientists spent years carefully assembling what would become one of the most remarkable instruments ever sent beyond our atmosphere. The facility belonged to Ball Aerospace and Technologies Corporation, a company with decades of experience building spacecraft and scientific instruments, and within its clean rooms and assembly halls, the Kepler Space Telescope slowly took shape, piece by careful piece, during the years leading up to its eventual launch. The work required extraordinary patience and precision, as every component needed to function flawlessly in the harsh environment of space, where no repair crew could ever reach it, and where even the smallest flaw might compromise the entire mission. The engineers who dedicated themselves to this task understood that they were building something unprecedented, a camera system of such sensitivity that it would be able to detect changes in starlight far too subtle for any previous instrument to measure, and they approached their work with the quiet diligence that such a responsibility demanded. The heart of the Kepler spacecraft was its telescope, a design known as a Schmidt telescope, which uses a particular arrangement of mirrors and corrective optics to achieve a very wide field of view while maintaining sharp focus across the entire image. The primary mirror of this telescope measured 95 centimeters in diameter, or just under 1 meter, making it a modest size by the standards of great astronomical observatories, yet perfectly suited to the mission's specific requirements. Unlike telescopes designed to study individual objects in great detail, Kepler needed to observe an enormous number of stars simultaneously, watching all of them at once for the tiny dimming events that might indicate a planet passing in front of its host star. This meant that a wide field of view was far more valuable than the ability to resolve fine details, and the Schmidt design provided exactly this capability, allowing the telescope to monitor more than 100,000 stars within a single patch of sky. The mirror itself was crafted from ultra-low expansion glass, a material chosen because it barely changes shape as temperatures fluctuate, and its surface was polished to extraordinary smoothness and then coated with a thin layer of aluminum to reflect incoming starlight toward the focal plane where the camera waited to record it. The camera system that received this focused starlight represented a truly remarkable achievement in engineering, one that pushed the boundaries of what had ever been attempted for a space-based instrument. At the heart of the camera lay the focal plane array, a collection of 42 charge-coupled devices, commonly called CCDs, arranged in a careful pattern to capture the light from all those thousands of stars. Each CCD was a rectangular sensor containing millions of individual light-sensitive elements called pixels, and together the 42 devices contained approximately 95 million pixels in total, making this the largest camera ever launched into space at that time. To put this in some perspective, the digital cameras commonly available to consumers in that era typically contained somewhere between 5 and 12 megapixels, So the Kepler focal plane represented an instrument roughly 10 times more capable than what most people might have used to photograph their families or their holidays. The CCDs were arranged in pairs, with 21 modules each containing 2 sensors, and these modules were positioned to cover a field of view spanning about 115 square degrees of sky, which is roughly equivalent to the area you might cover if you held both your hands at arm's length with your fingers spread wide. The construction of this focal plane array required solving numerous technical challenges that had never been faced before in quite this configuration. The individual CCDs needed to be positioned with extreme precision relative to one another, so that astronomers could accurately determine which star was producing which signal in the collected data. The sensors also needed to operate at very cold temperatures, around -85 degrees Celsius, because thermal energy in the electronics produces unwanted noise that would otherwise obscure the tiny signals the mission hoped to detect. This meant that the focal plane required an elaborate cooling system to draw heat away from the sensors and radiate it into the cold darkness of space, all while maintaining remarkably stable temperatures throughout the long observing campaigns. The wiring and electronics needed to read out the data from 95 million pixels, process that information, and prepare it for transmission back to Earth added further complexity, as did the need to shield all these sensitive components from the radiation environment of space, where energetic particles from the Sun and from distant cosmic sources constantly bombard any spacecraft beyond Earth's protective magnetic field. Perhaps the most impressive aspect of the photometer, which is the technical name for the light-measuring instrument that Kepler carried, was its extraordinary sensitivity to tiny changes in brightness. The engineering team designed the system to detect variations in starlight as small as 20 parts per million, which means it could notice if a star became just 0.002% dimmer than it had been moments before. To understand how remarkable this sensitivity truly is, consider that when an Earth-sized planet passes in front of a star similar to our Sun, it blocks only about 84 parts per million of the star's light, because the tiny planet covers only a minuscule fraction of the star's visible disk. Being able to detect changes of 20 parts per million meant that Kepler could reliably identify these transits, even when the planets involved were small rocky worlds rather than the large gas giants that earlier planet hunting methods had primarily discovered. This level of precision required not only excellent sensors and electronics, but also incredibly stable pointing of the telescope, since any wobble or drift would cause the starlight to move across different pixels, creating apparent brightness changes that had nothing to do with actual variations in the stars themselves. The thermal stability requirements for the Kepler spacecraft were correspondingly stringent, as temperature changes can cause materials to expand or contract slightly, shifting the alignment of optical components and introducing errors into the measurements. The engineering team established a requirement to maintain the temperature of critical components to within 1/10 of a degree Celsius, a level of thermal control that demanded careful attention to every aspect of the spacecraft's design. The telescope tube was wrapped in multilayer insulation, those distinctive gold-colored blankets visible in photographs of many spacecraft, which consist of numerous thin layers of reflective material separated by spacing fabric that together provide excellent protection against both the intense heat of direct sunlight and the bitter cold of shadowed space. The orientation of the spacecraft relative to the Sun needed to remain nearly constant throughout the mission, so that the same surfaces always faced sunward and the same surfaces always faced away, maintaining a steady thermal environment month after month and year after year. Even the slow seasonal changes in the spacecraft's distance from the Sun, which varies slightly as it follows its orbit, needed to be accounted for in the design, ensuring that the gentle warming and cooling over the course of a year would not disrupt the delicate measurements. The data handling systems aboard Kepler faced their own substantial challenges, as the continuous monitoring of so many stars generated enormous quantities of information that needed to be stored, processed, and eventually transmitted back to Earth. Each month, the spacecraft accumulated approximately 12 gigabytes of scientific data, a quantity that might seem modest by the standards of modern computing, but represented a significant challenge for a spacecraft operating millions of kilometers from Earth with limited power for its radio transmitter. The onboard computer could not simply send this data continuously, as the spacecraft needed to spend nearly all its time pointed at its target field of stars rather than turn to aim its antenna at Earth. So instead, the data accumulated in solid-state memory until scheduled communication sessions when the spacecraft would briefly reorient itself to establish contact with the deep space network. These monthly data downloads required the spacecraft to turn away from its stars for a day or so, during which time no observations could be made. But this interruption was far preferable to the alternative of continuous communication that would have severely limited the time available for actual science. When the assembly and testing of the Kepler spacecraft finally reached completion in Boulder, the finished vehicle weighed 1,052 kilograms at launch, or about as much as a small automobile, which included the telescope, the camera, all the electronics and computers, the communication systems, the power-generating solar panels, the structural framework holding everything together, and the supply of hydrazine propellant for occasional trajectory adjustments. The spacecraft was carefully prepared for its journey to the launch site, packed into protective containers, and transported across the country to Cape Canaveral Air Force Station on the Atlantic coast of Florida, where the warm, humid air and the proximity to the sea provided a striking contrast to the dry mountain climate where Kepler had been built. There, in the weeks leading up to launch, technicians performed final checks of all systems, verified that nothing had been damaged during shipping, and prepared the spacecraft for mating with the rocket that would carry it beyond Earth's atmosphere and gravitational embrace. The launch vehicle selected for the Kepler mission was a Delta II rocket, a reliable workhorse of the American space program that had successfully delivered numerous scientific spacecraft to their destinations over its long operational history. The particular configuration used for Kepler included 9 solid rocket boosters strapped around the first stage to provide additional thrust during the crucial first minutes of flight, when the vehicle needed to overcome Earth's gravity and the resistance of the thick lower atmosphere. The rocket stood ready on its launch pad at Space Launch Complex 17B throughout the final preparations, waiting for the moment when all systems would be declared ready and the countdown could proceed to its conclusion. That moment came on the 7th of March in the year 2009, when at 3:52 in the morning Eastern Time, under the dark pre-dawn sky of Florida, the engines ignited and the Delta II lifted away from the pad, carrying Kepler upward through the atmosphere on a pillar of brilliant flame and billowing exhaust. The destination for Kepler was not an orbit around Earth, as many might have expected for a space telescope, but rather a much more distant trajectory that would place the spacecraft in orbit around the Sun itself, following just behind Earth as both bodies traced their annual paths around our star. This Earth-trailing heliocentric orbit, as it is called, was chosen for several important reasons that would contribute to the success of the mission. An orbit around Earth would have meant that the spacecraft regularly passed through Earth's shadow, plunging into darkness once each orbit and experiencing rapid temperature swings as it moved from sunlit regions to shadowed ones and back again. Thermal cycling that would have made it extremely difficult to maintain the stability the photometer required. The Earth-trailing orbit avoided this problem entirely, keeping Kepler in constant sunlight throughout its mission, with only the gentle seasonal variations caused by the slight ellipticity of its path around the Sun. Additionally, being far from Earth meant that the spacecraft would not need to constantly reorient itself to avoid looking at our bright planet, and it avoided the complications of Earth's shadow crossings that would have periodically blocked the very stars Kepler was trying to study. Among the most critical systems aboard the spacecraft were the 4 reaction wheels that enabled Kepler to point with the extraordinary precision its science demanded. Reaction wheels are spinning flywheels oriented in different directions within the spacecraft, and by changing how fast each wheel spins, the control system can cause the spacecraft to rotate without expending any propellant, using the principle of conservation of angular momentum that physics students learn in introductory courses. When a reaction wheel spins faster in one direction, the spacecraft rotates slowly in the opposite direction to compensate, and by carefully coordinating the speeds of multiple wheels, the pointing system can orient the telescope with remarkable accuracy. The Kepler design required a minimum of 3 functioning reaction wheels to provide full pointing control in all 3 axes of rotation, but the engineering team wisely included a 4th wheel as a spare, recognizing that these mechanical systems, with their bearings and motors and spinning masses, represented potential points of failure over the course of a long mission. This redundancy would prove significant in the years to come, as the operational history of the mission would eventually test the limits of the pointing control system in ways that the designers hoped would never occur but prudently prepared for nonetheless. The reaction wheel system needed to maintain pointing accuracy to within a tiny fraction of a pixel on the camera's sensors, which translated to an angular precision of better than 1/50th of an arcsecond, a measurement so small that it defies easy visualization. An arcsecond is 1/3600th of a degree, and 1/50th of that represents an angle so minuscule that it would be like holding a quarter in Boulder, Colorado, and asking someone in Los Angeles to determine which side faces up. This level of precision was essential because even tiny movements of the star images across the pixel boundaries of the CCDs would create apparent brightness variations that could mask or mimic the subtle transit signals the mission sought to detect. The combination of the reaction wheel pointing system, the stable thermal environment of the heliocentric orbit, and the exquisite sensitivity of the photometer all worked together as an integrated system, each component depending on the others to achieve the overall scientific goals of the mission. As Kepler settled into its orbit and began its long vigil watching a single field of stars in the constellations Cygnus and Lyra, the engineering teams on Earth monitored every aspect of its performance, tracking temperatures and voltages and data rates and pointing accuracy, ensuring that all the careful work done in those clean rooms in Boulder was functioning as intended. The spacecraft that had taken so many years to design and build was now operating smoothly in the silent darkness between Earth and Mars, its camera staring unblinking at more than 150,000 stars, waiting patiently for the subtle dimming events that would reveal the presence of worlds beyond our solar system. The journey from concept to orbiting observatory had required the efforts of thousands of people working over more than a decade, solving problems that had never been solved before and achieving levels of precision that had never before been achieved, all in service of a simple question that had occupied human imagination since ancient times: whether other Earths might exist among the stars, and whether someday we might find them. When the Kepler Space Telescope turned its single unblinking eye toward the stars, it did not sweep across the heavens in grand arcs or dart from one fascinating object to another. Instead, it settled its gaze upon a single modest patch of sky and held that gaze, steadily and patiently, for years upon years. This patch of sky, spanning roughly 115 square degrees, sits nestled between the constellations of Cygnus the Swan and Lyra the Harp. And if you were to hold your outstretched hand at arm's length against the night sky, this entire field of view would be covered by the span of your palm and fingers together. It is not an especially famous region of the heavens, not a place where amateur astronomers typically point their backyard telescopes in search of spectacular nebulae or glittering star clusters. Yet this quiet corner of the cosmos became the most intensively studied patch of sky in all of human history, and the reasons for its selection reveal much about the careful, methodical nature of the Kepler mission itself. The choice of this particular field was not made hastily or arbitrarily, but emerged from years of preparatory work and thoughtful deliberation among the scientists and engineers who designed the mission. They needed a region of sky that would satisfy several demanding requirements simultaneously, and finding such a place required balancing competing priorities with considerable care. The Cygnus-Lyra region, as it came to be known, emerged as the optimal solution to a complex puzzle, and understanding why this is so helps us appreciate the elegant practicality that underpinned the entire endeavor. One of the most fundamental requirements was that the chosen field must remain continuously visible to the spacecraft throughout its primary mission, which was planned to last at least 3.5 years. Kepler orbited the Sun rather than the Earth, following our planet in its yearly journey around our star while trailing gradually behind. And from this vantage point, the spacecraft needed to keep its telescope pointed steadily at the same stars while simultaneously keeping its solar panels aimed at the Sun for power and its radiator pointed away from the Sun to keep the sensitive instruments cool. These geometric constraints meant that the target field needed to lie roughly perpendicular to the plane of Earth's orbit, in a direction where the spacecraft could maintain its orientation without needing to rotate significantly as the months passed and its position around the Sun changed. The Cygnus-Lyra region sits at just the right angle in the sky to satisfy these requirements, allowing Kepler to stare fixedly at its chosen stars while the Sun illuminated its solar arrays and the cold of deep space drew heat away from its instruments, all without the need for complex maneuvering that would interrupt the precious observations. Another consideration, perhaps less immediately obvious but equally important, was the density of stars within the chosen field. One might assume that pointing at a region absolutely crowded with stars would be advantageous, since more stars would mean more chances to find planets. But the reality is more nuanced than this simple logic suggests. The Kepler telescope detected planets by measuring the tiny dips in starlight that occur when a planet passes in front of its host star, blocking a small fraction of the star's light from reaching the telescope. This technique, known as the transit method, requires extremely precise measurements of stellar brightness, and if stars are packed too closely together in the telescope's field of view, their light begins to blend and overlap, making it difficult to attribute a brightness change to any particular star. This crowding effect becomes especially problematic near the plane of our Milky Way galaxy, where stars are concentrated most densely and the luminous band of the Milky Way stretches across the sky. The Cygnus-Lyra field was chosen to lie somewhat away from the galactic plane, positioned at a galactic latitude that provided a rich abundance of stars without the problematic overcrowding that would have compromised the precision of the measurements. This careful positioning allowed Kepler to monitor a generous number of stars while still being able to distinguish one star from another and measure each one's brightness with the exquisite accuracy the mission required. The field contains enough stars to make the statistical search for planets meaningful, yet not so many that the stars blur together into an indistinguishable luminous haze. Within this carefully chosen patch of sky, The Kepler mission monitored approximately 150,000 stars in a nearly continuous fashion over the course of its primary mission. This number is itself remarkable when one pauses to consider what it means. Each of these stars was observed repeatedly, with brightness measurements taken every 30 minutes for most targets and every minute for a smaller subset of particularly interesting stars. The resulting flood of data, accumulated over years of patient watching, constitutes one of the most comprehensive surveys of stellar behavior ever undertaken, and from this vast reservoir of measurements emerged the discoveries of thousands of worlds beyond our own. The stars that Kepler monitored were not chosen randomly from among all the stars within its field of view, but were carefully selected in advance based on their suitability for planet detection. This selection process relied upon a remarkable preparatory effort known as the Kepler Input Catalogue, often abbreviated as the KIC, which was assembled by the Stellar Classification Project in the years leading up to the spacecraft's launch. This catalogue represents an enormous undertaking in its own right, a comprehensive survey of all the stars in the Kepler field that gathered information about each star's brightness, color, temperature, size, and other properties that would determine whether it was a good candidate for planet searching. The creation of the Kepler Input Catalogue required extensive observations using ground-based telescopes, instruments that could characterize the fundamental properties of hundreds of thousands of stars so that the mission planners would know which ones to prioritize when Kepler began its watch. These observations measured the apparent brightness of each star in multiple wavelength bands, from blue light through red, and from these color measurements astronomers could estimate each star's surface temperature and, by extension, its spectral type and rough size. This preliminary work was essential because Kepler's limited data transmission capacity meant that it could not simply observe every star in its field and send all the data back to Earth. Choices had to be made, priorities had to be established, and the Kepler Input Catalogue provided the foundation of knowledge upon which those choices rested. The catalogue ultimately contained information on more than 13 million objects within the Kepler field, though only a carefully chosen subset of these would become primary targets for continuous monitoring. The selection criteria favored stars that were most likely to host detectable planets and most likely to yield clean, interpretable signals if a planet happened to transit. This generally meant focusing on stars that were relatively bright, so that enough photons would reach the detector to permit precise brightness measurements, but not so bright that they would saturate the camera's sensitive pixels. It also meant favoring stars that appeared to be relatively stable and well-behaved, rather than wildly variable stars whose intrinsic brightness fluctuations might mimic or obscure the subtle signatures of transiting planets. Among the most important considerations in target selection was the type of star being observed, and the Kepler mission deliberately focused its attention primarily on dwarf stars belonging to the spectral classes known as F, G, and K. These letters, which may seem cryptic at first encounter, represent categories of stars defined by their surface temperatures and the distinctive patterns of light they emit. G-type stars, like our own Sun, have surface temperatures of roughly 5,000 to 6,000 degrees Kelvin and shine with a yellowish-white light. F-type stars are somewhat hotter and larger, with temperatures ranging from about 6,000 to 7,500 degrees Kelvin, while K-type stars are cooler and smaller, with temperatures from roughly 4,000 to 5,000 degrees Kelvin and a light that tends toward the orange end of the spectrum. These three spectral classes were prioritized because they represent stars that are similar enough to our Sun that any planets found around them might plausibly harbor conditions remotely comparable to those on Earth. The term dwarf star in this context refers not to unusually small stars but simply to stars that are in the main sequence phase of their lives, steadily fusing hydrogen into helium in their cores and shining with a relatively stable luminosity over billions of years. These are the stars around which rocky planets like Earth are most likely to have formed, and around which such planets might retain their atmospheres and possibly even liquid water on their surfaces over the immense timescales that life seems to require. By focusing on F, G, and K dwarf stars, the Kepler mission maximized its chances of finding planets that might be broadly Earth-like in their basic properties, while also ensuring that any transiting planets would produce detectable dips in starlight. Larger, brighter stars would make planetary transits proportionally shallower and harder to detect, while smaller, dimmer stars would provide fewer photons for the telescope to measure, increasing the noise in the data. The chosen spectral types represented a carefully considered compromise, a sweet spot in the landscape of stellar possibilities where the prospects for finding and characterizing potentially habitable worlds were most favorable. The Kepler field's location within our galaxy is itself a matter of some interest, though it requires us to step back and consider the broader structure of the Milky Way. Our galaxy is a vast spiral of stars, gas, and dust, spanning roughly 100,000 light-years from edge to edge and containing somewhere between 100 billion and 400 billion stars. The Sun resides within one of the galaxy's spiral arms, a relatively minor structure known as the Orion Spur or sometimes the Orion Arm, which lies between two of the grander spiral arms called the Sagittarius Arm and the Perseus Arm. When Kepler gazed toward the constellation Cygnus, it was looking along the length of the Orion Spur, peering outward through the local stellar neighborhood in a direction that remains within our own spiral arm rather than looking across toward the galaxy's center or out toward its sparse outer reaches. This orientation meant that the stars Kepler observed were relatively nearby by galactic standards, with distances ranging from roughly 600 light-years at the near end to approximately 3,000 light-years at the far end of the sampled volume. These distances, while enormous by any human measure, are quite modest in the context of the galaxy as a whole, representing a sampling of our local cosmic neighborhood rather than a survey of remote galactic provinces. The stars that Kepler watched are our neighbors, relatively speaking, members of the same spiral arm that contains our own solar system and composed of material that originated from the same general regions of interstellar space. The range of distances within the Kepler field meant that the mission sampled stars at various depths within the galaxy, providing a kind of three-dimensional cross-section of the local stellar population. Some of the target stars were close enough that their planets, if detected, might someday be studied in detail by future generations of telescopes. Others were distant enough that their light had been traveling for thousands of years before reaching Kepler's photometer, carrying information about planetary systems that existed when Stonehenge was being built on the plains of southern England or when the first Egyptian pyramids were rising from the desert sands. The preparation of the Kepler mission involved extensive collaboration between the space-based telescope and ground-based observatories, a partnership that continued throughout the mission's operational lifetime and beyond. Before Kepler launched, ground-based telescopes conducted the photometric surveys that fed into the Kepler input catalog, measuring the colors and brightnesses of millions of stars to establish the baseline information needed for target selection. These preliminary observations employed telescopes at observatories in Arizona, Hawaii, and elsewhere, instruments that could survey large areas of sky efficiently and build up the comprehensive stellar census that the mission required. The collaboration continued after Kepler began returning data, as ground-based telescopes played an essential role in following up on the planet candidates that the Space Telescope identified. When Kepler detected what appeared to be a planetary transit, the signal needed to be verified and characterized using additional observations that Kepler itself could not provide. Ground-based spectrographs could measure the subtle wobble of a star induced by an orbiting planet's gravitational tug, confirming that the transit signal was indeed caused by a planet rather than some other phenomenon such as a background eclipsing binary star whose light happened to blend with the target star. These radial velocity measurements, as they are called, provided independent confirmation of planetary detections and also yielded estimates of planetary masses, information that Kepler's transit observations alone could not supply. Ground-based telescopes also contributed high-resolution imaging that could reveal whether an apparent single star in Kepler's relatively coarse view was actually a close pair of stars or a chance alignment with a background object. Such configurations could produce transit-like signals that might be mistaken for planets, and ruling out these false positive scenarios required the sharper vision that large ground-based telescopes with adaptive optics systems could provide. Observatories in Hawaii, Chile, Spain, and elsewhere contributed to this verification effort, their instruments complementing Kepler's unblinking survey with targeted observations of individual systems that merited closer scrutiny. The choice of the Cygnus-Lyra field also ensured that the stars Kepler monitored would be accessible to ground-based observatories in the Northern Hemisphere, where many of the world's largest and most capable telescopes are situated. A field in the southern sky might have been equally suitable from the spacecraft's perspective, but would have limited the opportunities for follow-up observations from northern observatories. By selecting a field that remains visible throughout the year from sites like the Keck Observatory in Hawaii or the various telescopes of the Canary Islands, the mission planners ensured that the crucial ground-based support would be available whenever it was needed. And so the Kepler Space Telescope settled into its long vigil, its gaze fixed upon this carefully chosen patch of sky where approximately 150,000 stars drifted slowly through the cosmos, each one a potential sun to unknown worlds. The spacecraft asked nothing more than to be left alone to watch, to accumulate its measurements night after night and year after year, building up a portrait of stellar variability and planetary transits with a patience that no human observer could match. The Cygnus-Lyra field, selected through diligent preparatory work and careful geometric reasoning, became the most thoroughly examined real estate in the observable universe, a 115-square-degree window through which humanity glimpsed the staggering prevalence of planets in our galaxy. The stars within that window continued their ancient business, burning hydrogen in their cores and sending their light outward in all directions, indifferent to the tiny spacecraft that had taken such an interest in their activities. Some of those stars harbored planets that crossed in front of them during Kepler's watch, dimming their light by tiny but measurable amounts. Others showed no such transits, either because they had no planets or because their planets orbited in planes that did not happen to align with the telescope's line of sight. All of them contributed to the growing body of data that would ultimately reveal how common planets truly are, transforming our understanding of our place in the cosmos. The constellation Cygnus itself, visible in the Northern Hemisphere's summer and autumn skies, became a symbol of sorts for the search for other worlds. Its brightest stars form a pattern sometimes called the Northern Cross, though the swan that gives the constellation its name is perhaps easier to imagine, with outstretched wings and a long neck pointing southward through the Milky Way. Somewhere within its boundaries, though far too faint for the naked eye to discern individually, lie the stars that Kepler watched so patiently, The stars that taught us that planets are not rare exceptions in the cosmos but rather the common and expected companions of stars throughout the galaxy. The choice of this field, made years before the first data arrived, proved to be wise and fortuitous, placing the telescope's limited field of view precisely where it could do the most good. On the 8th of April in the year 2009, some 34 days after Kepler had left the warmth of Earth's atmosphere behind, the spacecraft turned its singular eye toward a small patch of sky and collected its first image of the cosmos. This moment, known in the language of astronomers as first light, represents the instant when a telescope ceases to be merely a complex arrangement of mirrors and sensors and becomes, at last, an instrument of discovery. The image that Kepler returned to Earth on that April day was not particularly beautiful in the conventional sense, not the sort of picture one might frame and hang upon a wall, but to the scientists who had waited so many years to see it, the photograph held a quiet and profound significance that went far beyond aesthetics. The first light image revealed approximately 4.5 million stars, each one rendered as a tiny point of brightness against the velvet darkness of space. These stars filled the field of view like grains of sand scattered across black cloth, some bright and prominent, others so faint they barely registered above the background noise of the detector. The patch of sky that Kepler had chosen to observe, a region spanning portions of the constellations Cygnus and Lyra, had been selected precisely because it contained such an abundance of stars, for the mathematics of planet hunting demanded that Kepler monitor as many suns as possible to have any reasonable hope of catching the rare and fleeting shadows of distant worlds. Looking upon that image, one could begin to comprehend both the ambition and the humility of the mission. The audacious hope of finding other Earths tempered by the knowledge that even 4.5 million stars represented only the smallest fraction of the hundreds of billions that populate our galaxy. Yet even in those earliest days of triumph, as engineers and scientists celebrated the successful capture of first light, there were whispers of concern beginning to circulate among the team. The commissioning phase, that careful period of testing and calibration that follows the launch of any new spacecraft, was revealing problems that no one had anticipated. The data streaming back from Kepler contained unexpected sources of noise, subtle irregularities in the measurements that threatened to obscure the very planetary signals the mission had been designed to detect. Some of these noise sources arose from the thermal environment of the spacecraft, the gentle flexing of materials as Kepler moved from shadow into sunlight and back again during its orbit around the Sun. Others stemmed from the behavior of the charge-coupled devices themselves, the sensitive silicon chips that converted starlight into electrical signals that could be transmitted back to Earth. The charge-coupled devices, or CCDs, that formed the heart of Kepler's camera represented some of the most sophisticated light-detecting technology ever placed aboard a spacecraft. The focal plane array consisted of 42 individual CCDs arranged in a mosaic pattern, each chip containing millions of individual pixels capable of registering the arrival of photons from distant stars. These devices had been tested extensively on the ground, subjected to every manner of examination that engineers could devise, and they had performed admirably in the controlled environment of the laboratory. But space is not a laboratory, and the violence of launch subjects spacecraft components to forces that cannot be perfectly replicated in any Earthbound facility. As the commissioning data began to arrive and scientists examined the performance of each individual CCD, they made a discovery that sent a small chill through the team. Several of the charge-coupled devices had failed during launch, their delicate structures damaged by the tremendous vibrations of the rocket engines or perhaps by some other insult sustained during the journey from Earth to orbit. The loss of these CCDs was not catastrophic to the mission, for the designers had built-in redundancy and the remaining functional devices still provided more than sufficient coverage to carry out the primary science objectives. Nevertheless, the discovery served as a sobering reminder of the precarious nature of space exploration. The way that years of careful planning and billions of dollars of investment can be compromised by the failure of a single component no larger than a postage stamp. The scientists adjusted their observing strategies to account for the dead CCDs, routing the light from certain stars to functioning portions of the detector array, and they carried on with the business of commissioning the spacecraft for its long mission ahead. Then, in June of 2009, just as the team was beginning to settle into the rhythm of routine operations, Kepler gave them all a proper fright. Without warning, the spacecraft entered what engineers call safe mode, a protective state in which the telescope suspends all normal operations and orients itself to await instructions from Earth. Safe mode is designed to prevent damage to the spacecraft during anomalous conditions, a kind of defensive posture that protects the delicate instruments from harm when something unexpected occurs. But for the scientists and engineers who had invested so much of their professional lives in Kepler, the sudden transition to safe mode felt less like a safety feature and more like a heart-stopping emergency. The days that followed were tense ones for the mission team, as engineers worked to diagnose the cause of the safe mode event and devise a strategy for returning Kepler to normal operations. The spacecraft was so far from Earth, following its own orbit around the Sun rather than circling our planet like most space telescopes, that communication delays made every commander exercise in patience. Instructions sent from the ground took time to reach Kepler, and the responses took equally long to return, so that troubleshooting proceeded at a pace that felt agonizingly slow to those who were accustomed to the instant feedback of working with equipment in a laboratory. Eventually, the engineers traced the problem to a software issue rather than a hardware failure, and they were able to coax Kepler back into operational mode without lasting damage to the spacecraft or its instruments. But the safe mode event served as another reminder of the fragility of their enterprise, the way that a single glitch could threaten to unravel years of scientific planning. As the raw data from Kepler's observations began to accumulate, the science team faced a challenge that was in some ways more daunting than any hardware failure. The telescope was performing its basic function admirably, measuring the brightness of stars with a precision that had never before been achieved from space. But the data contained so many signals, so many tiny variations in stellar brightness, that distinguishing the shadows of genuine planets from other sources of variability proved far more difficult than anyone had anticipated. Stars, it turned out, were not the steady and reliable beacons that one might naively imagine. They pulsated and flickered, they rotated and revealed spots on their surfaces. They existed in binary pairs that eclipsed one another, and they varied in brightness for a dozen other reasons that had nothing whatsoever to do with planets passing in front of them. The initial confusion over how to separate planetary transits from this welter of stellar variability consumed the attention of the science team throughout the first year of operations. A planetary transit, that gradual dimming of a star as a planet crosses in front of it, follows a characteristic pattern that is determined by the geometry of the system and the laws of physics. The dimming begins slowly as the planet first touches the edge of the stellar disk, deepens to a maximum when the planet is fully in front of the star, and then gradually brightens again as the planet moves off the other side. This pattern, when plotted on a graph of brightness versus time, creates a distinctive shape that astronomers call a light curve, and in principle it should be readily distinguishable from other sources of variability. In practice, however, the situation proved considerably more complicated. Many of the false positives that plagued the early Kepler data arose from binary star systems, pairs of stars that orbit around their common center of mass and periodically eclipse one another. When one star passes in front of its companion, the total light from the system dims in a way that can look remarkably similar to a planetary transit, especially when the two stars are of very different sizes. Other false alarms came from background eclipsing binaries, systems that happened to lie along the same line of sight as the target star but at a much greater distance, so that their eclipses contaminated the measurements in subtle and misleading ways. Still others arose from instrumental effects, quirks of the detector that caused spurious variations in the recorded brightness of stars even when the stars themselves were perfectly steady. To validate that Kepler was actually capable of detecting planetary transits amidst all this noise, the science team turned to a world that had already been discovered by ground-based observers. The planet known as TRES-2b, a hot Jupiter orbiting a star in Kepler's field of view, had been detected in 2006 using the transit method from Earth-based telescopes. This made it an ideal test case, a known planet whose transit Kepler should be able to observe if the spacecraft was performing as designed. When the team examined the Kepler data for the star hosting TRES-2b, they found exactly what they hoped to find: a clear and unmistakable dip in brightness occurring at precisely the times when the planet was expected to cross in front of its sun. The detection of this transit, from a planet that would later be redesignated as Kepler 1b in honor of its role in validating the mission, provided welcome confirmation that the telescope was indeed capable of fulfilling its scientific promise. Yet even as this early success offered reassurance, criticism of the mission began to emerge from some quarters of the astronomical community. Certain researchers expressed skepticism about the sensitivity claims that the Kepler team had made for their instrument, questioning whether the telescope could really achieve the extraordinary precision necessary to detect Earth-sized planets around Sun-like stars. The transit of an Earth-sized world across a Sun-like star produces a dimming of approximately 84 parts per million, a decrease in brightness so small that it pushes against the fundamental limits of photometric measurement. Some astronomers doubted that any instrument, no matter how carefully designed, could reliably detect signals at this level against the background of stellar variability and instrumental noise. The Kepler scientists responded to these criticisms not with defensiveness but with the quiet confidence of researchers who trusted their data and their methods. They acknowledged the challenges posed by the various noise sources that had been discovered during commissioning, and they explained the sophisticated techniques they were developing to mitigate these effects. The process of creating data analysis pipelines, the complex software systems that would process the raw observations and search for planetary signals, became a major focus of effort throughout the first year of operations. These pipelines had to perform dozens of separate functions, from correcting for instrumental effects to removing the signatures of known variable stars to identifying candidate transits for further examination. One of the most important innovations to emerge from this period was a set of techniques known collectively as pre-search data conditioning, a process designed to remove systematic errors from the observations before the search for transits even began. These systematic errors arose from a variety of sources, including the thermal variations of the spacecraft, the gradual degradation of the detector sensitivity, the slight changes in the pointing of the telescope, and numerous other effects that had nothing to do with the stars being observed but nonetheless introduced unwanted variations into the measurements. The pre-search data conditioning algorithms learned to recognize these patterns and subtract them from the data, cleaning the observations so that the genuine astrophysical signals could be more readily identified. The development of these data processing techniques was painstaking work, requiring the combined expertise of astronomers, statisticians, and computer scientists working together to solve problems that had never been confronted before. Each improvement in the algorithms revealed new subtleties in the data, new sources of systematic error that had previously been hidden beneath the noise. The scientists would implement a correction, examine the cleaned data, discover a new problem, and begin the process again. This iterative refinement continued throughout the mission, with the data analysis pipelines growing steadily more sophisticated as the team gained experience with the peculiarities of Kepler's observations. In June of 2010, slightly more than a year after first light, the Kepler team released its first set of science data to the broader astronomical community. This data release represented a milestone in the mission, a transition from the private work of commissioning and calibration to the public enterprise of shared scientific discovery. The released data contained light curves for more than 150,000 stars, each one a record of brightness measurements spanning the first 43 days of science operations. Along with the data came a list of candidate planetary systems, stars that showed evidence of periodic dimming consistent with transiting planets and that warranted further investigation. The response from the astronomical community was immediate and enthusiastic, as researchers around the world began downloading the data and conducting their own analyses. Some scientists focused on confirming the candidate planets that the Kepler team had identified, using ground-based telescopes to gather additional observations that could rule out false positives. Others searched the data for signals that the official pipeline might have missed, developing independent algorithms to comb through the measurements in search of overlooked worlds. Still others turned their attention to the stellar variability itself, finding in Kepler's precise measurements a wealth of information about the inner workings of stars that had nothing to do with planets but was scientifically valuable in its own right. The shaky start of Kepler's mission, with its failed CCDs and safe mode events and initial confusion over data analysis, might seem like an inauspicious beginning for what would become one of the most transformative astronomical endeavors in history. But in science, as in so many human enterprises, early difficulties often contain the seeds of later success. The challenges that the Kepler team faced during those first uncertain months forced them to develop tools and techniques that would prove essential in the years ahead. The sophisticated data processing pipelines that emerged from the struggle with systematic errors would eventually enable the detection of planets far smaller and more distant than anything that had been found before. The experience gained from troubleshooting hardware anomalies would inform the response to far more serious problems that lay in Kepler's future. And so Kepler continued its patient watch of that crowded patch of sky, measuring the brightness of its stars once every 30 minutes, recording the subtle flickerings of distant suns with a precision that continued to improve as the team refined their methods. The first confirmed planetary detections beyond the validation target of Kepler 1b were beginning to emerge, hints of worlds that would soon be announced to the public and that would mark the true beginning of Kepler's extraordinary harvest. But those discoveries, and the many thousands that would follow, lay still in the future as the mission settled into its long and quiet vigil, a small spacecraft alone in the darkness, watching and waiting for the shadows of other worlds to drift across the faces of distant stars. Among the many worlds that emerged from the data collected by the Kepler Space Telescope, there exists a particular category of planet that, when first discovered in the years before Kepler launched, seemed almost impossible, and yet these same planets proved to be among the easiest for Kepler to find, appearing again and again in the data, Dozens of them, then hundreds. Great massive spheres of hydrogen and helium, much like our own Jupiter in their basic composition, but occupying orbits so impossibly close to their parent stars that astronomers had to revise nearly everything they thought they understood about how planetary systems come to be. And these are the worlds we now call hot Jupiters, gas giant planets that circle their stars in mere days rather than years. And Kepler found them in remarkable abundance, each one a quiet challenge to the theories that had governed our understanding of how planets form and where they ought to reside within their systems. When astronomers speak of distance in the context of planetary systems, they often use a unit called the astronomical unit, which is simply the average distance between Earth and the Sun, approximately 150 million kilometers. And Earth by definition orbits at 1 astronomical unit, while Jupiter orbits at roughly 5 astronomical units, out in the cold outer reaches of our solar system where it takes nearly 12 Earth years to complete a single orbit. And this seemed natural and sensible when we had only our own solar system to study, the small rocky worlds huddled close to the Sun's warmth, the gas giants maintaining their stately distance in the outer darkness. But the hot Jupiters that Kepler discovered orbit at distances of less than 1/10 of an astronomical unit, often far less, closer to their stars than Mercury is to our Sun, so close that they are perpetually bathed in fierce radiation and heated to temperatures that would seem more appropriate to the surfaces of stars than to the atmospheres of planets. One particularly illuminating example of these scalding worlds is Kepler 17b, a planet that was identified in the Kepler data and confirmed through subsequent observations. And this world possesses a mass roughly 2.5 times that of Jupiter, making it a substantial gas giant by any measure. Yet it orbits its star in just 1.49 Earth days, meaning that its year, if we can call it that, is shorter than a long weekend on Earth. And to complete an orbit in such a brief span of time, Kepler 17b must be racing around its star at tremendous velocity while simultaneously being pulled by intense gravitational forces. And the proximity to its star means that the daytime temperatures on this world reach extraordinary values, far beyond anything we experience on Earth, heating the hydrogen and helium atmosphere until it glows with infrared radiation that astronomers can detect from across the vast distances of interstellar space. The case of Kepler 70b represents an even more extreme example of this phenomenon, a planet that orbits so close to its star that it has likely been transformed by the experience in ways that make it quite unlike any world in our own solar system. And the orbital period of Kepler 70b is measured in mere hours rather than days, with the planet completing each circuit around its star in approximately 5.8 hours, which requires it to orbit at a distance of only about 1 solar radius from the surface of the star, essentially skimming along just above the stellar photosphere. And at such proximity the planet receives radiation so intense that any atmosphere it might once have possessed would have been stripped away long ago. And indeed astronomers believe that what we observe as Kepler 70b may be the exposed core of what was once a much larger gas giant, a planet that was gradually evaporated by the ferocious radiation of its star until only the dense rocky or metallic core remained. A kind of planetary remnant that speaks to processes of destruction rather than creation, worlds being slowly unmade by the very stars they orbit. The measurement of reflected light from these hot Jupiters has proven to be another fruitful area of investigation, and Kepler 7b provides a particularly interesting case study in this regard, as this planet was found to reflect a surprisingly large fraction of the light that falls upon it from its star, making it one of the more reflective hot Jupiters in the Kepler catalogue. And the analysis of this reflectivity, combined with detailed observations of how it varies as the planet orbits, has revealed the presence of clouds and hazes in the planet's atmosphere, structures of condensed material suspended in the hydrogen and helium gas, perhaps composed of silicates or other refractory materials that can remain solid even at the extreme temperatures present on such worlds. And these clouds appear to be distributed unevenly across the planetary surface, concentrated in certain regions and absent from others, creating patterns of brightness and darkness that astronomers can map from the subtle variations in the light that reaches us across dozens of light years. The very existence of hot Jupiters presents a significant puzzle for theories of planetary formation, because according to our understanding of how gas giant planets come into being, they simply cannot form in the locations where we observe them. And this is because the formation of a gas giant requires a substantial core of rock and ice to first accumulate in the protoplanetary disk, a core massive enough to gravitationally capture the hydrogen and helium gas that comprises the bulk of the planet's final mass. And this process can only occur beyond a boundary called the snowline, the distance from a young star beyond which water and other volatile compounds can exist as solid ice rather than vapor. Because it is only with the presence of these ices that sufficient solid material can accumulate to build a core large enough to capture gas. And the snowline in a typical protoplanetary disk lies at roughly 2 to 3 astronomical units from the star, meaning that gas giants must form at distances comparable to or greater than this, out in the cold outer regions of the disk. Yet we observe hot Jupiters orbiting at 1/20th or 1/50th of this distance, in regions where the formation of such massive worlds would have been physically impossible. The resolution to this puzzle lies in the process known as planetary migration, the gradual movement of planets from the orbits where they formed to different orbits where we observe them today. And this migration can occur through several different physical mechanisms, each of which operates on different timescales and produces somewhat different outcomes. And understanding these mechanisms has become an important area of research in planetary science, driven in large part by the hot Jupiter discoveries made by Kepler and other planet-hunting missions, as astronomers work to explain how gas giants can travel from the outer reaches of their natal systems to the close stellar proximities where we find them today. The first major mechanism is known as disk migration, which occurs while the planet is still embedded in the protoplanetary disk from which it formed. And in this scenario, the young gas giant gravitationally interacts with the gas and dust that still surrounds the star. And these interactions can either add energy to the planet's orbit or remove it, depending on the details of the disk structure and the planet's mass. And in many cases, the net effect is a transfer of angular momentum from the planet to the disk, which causes the planet to spiral slowly inward toward the star, a process that can continue for millions of years as long as the disk remains present, carrying the giant planet from the outer system where it formed into the inner regions where we observe hot Jupiters today. And this mechanism has the advantage of explaining why hot Jupiters are found on circular orbits aligned with the equators of their stars, as the disk itself tends to damp out any eccentricity or inclination during the migration process. The second major mechanism is gravitational scattering, which occurs in systems where multiple giant planets form and subsequently interact with one another through their mutual gravitational attraction. And in such systems, the planets may pass close to one another in ways that dramatically alter their orbits, sometimes flinging one planet outward into a highly elliptical orbit while sending another inward toward the star. And if a planet is scattered into an orbit that brings it very close to the star at its closest approach, the tidal forces exerted by the star can gradually circularize the orbit over time, shrinking it down until the planet settles into a short-period circular orbit characteristic of hot Jupiters. And this mechanism tends to produce hot Jupiters on orbits that are misaligned with the stellar equator, sometimes even retrograde, orbiting in the opposite direction to the star's rotation. and the observation of such misaligned systems provides evidence that at least some hot Jupiters arrived at their present locations through scattering rather than disk migration. The statistical analysis of the Kepler data has allowed astronomers to determine just how common these hot Jupiters actually are, and perhaps surprisingly, despite how easy they are to detect, hot Jupiters turn out to be relatively rare, present around only approximately 1% of Sun-like stars, which means that for every 100 stars similar to our Sun, only about one of them hosts a hot Jupiter, and this relative rarity is itself an important clue about the conditions required to form and deliver such planets to their close-in orbits, suggesting that while the migration processes are real, they do not operate efficiently in every system. And indeed our own solar system represents the more common outcome, with gas giants remaining in the outer regions where they formed rather than migrating inward to become hot Jupiters. Another notable discovery from the Kepler mission is Kepler 13ab, a hot Jupiter orbiting one component of a stellar system located approximately 2,000 light-years from Earth, and this planet is remarkable for several reasons, not least of which is its substantial mass, estimated at somewhere between 4 and 8 Jupiter masses, making it one of the more massive hot Jupiters known, and detailed observations of this world have revealed evidence for a stratosphere, a layer in the atmosphere where temperature increases with altitude rather than decreasing, which on Earth is caused by the absorption of ultraviolet radiation by ozone, and on Kepler 13ab appears to be caused by the absorption of starlight by molecules of titanium oxide, which can only exist in gaseous form at the extreme temperatures present on this world. And this stratospheric inversion creates distinct signatures in the spectrum of light from the planet, allowing astronomers to probe the vertical structure of an atmosphere located more than 1,000 light-years away. The question of why hot Jupiters stop migrating where they do, rather than continuing their inward spiral until they plunge into their stars, has led to the development of what astronomers call parking mechanism theories, various physical processes that might halt or reverse the migration before the planet is destroyed, and several such mechanisms have been proposed, including the truncation of the protoplanetary disk by the star's magnetic field, which creates an inner edge to the disk beyond which there is no more material to transfer angular momentum with the planet, and the heating of the inner disk by stellar radiation, which changes its properties in ways that can reverse the direction of migration, and the simple raising of stellar tides on the planet, which at sufficiently close distances transfers angular momentum back to the orbit faster than the disk can remove it. And each of these mechanisms would produce slightly different distributions of hot Jupiter orbital periods. And astronomers continue to study the statistical properties of the known hot Jupiter population to determine which parking mechanisms are most important in practice. The temperatures that exist on these worlds are difficult to fully appreciate from our everyday experience, as the daytime hemispheres of many hot Jupiters are heated to values exceeding 2000 Kelvin, which is hotter than the surface of many red dwarf stars. And at such temperatures the atmosphere behaves in ways quite unlike anything we observe on the planets of our own solar system, with molecules breaking apart into their constituent atoms, metals existing as gases, and the boundary between planet and star becoming conceptually blurred. And because hot Jupiters orbit so close to their stars, they are almost certainly tidally locked, with one hemisphere permanently facing the star in eternal day while the other hemisphere faces away in eternal night. And the temperature contrast between these two hemispheres is extreme, with the day side glowing at temperatures that might reach 3000 Kelvin while the night side cools to perhaps 1000 Kelvin, and the atmosphere attempts to redistribute this heat through powerful winds that blow from day to night, racing across the planet at speeds measured in kilometers per second. The Kepler mission was not specifically designed to study hot Jupiters in detail, as its primary goal was the detection and statistical characterization of Earth-like planets. But the abundance of hot Jupiters in the data, combined with their large sizes and short orbital periods, meant that they could be studied with remarkable precision. Their transits deep and frequent, their secondary eclipses as they passed behind their stars revealing information about their dayside temperatures and compositions. And in this way the hot Jupiter population became a testing ground for techniques and theories that would later be applied to smaller and more Earth-like worlds. And the lessons learned from these Scalding giants about atmospheric structure, cloud formation, and planetary migration have enriched our understanding of planetary systems as a whole. And so as we consider these worlds, these great balls of hydrogen and helium racing around their parent stars in orbits measured in days or even hours, we might reflect on how strange and various the universe of planets has proven to be, with worlds that exist in conditions so far removed from our experience that they almost seem to belong to a different category of astronomical object entirely. And yet they are planets, formed from the same materials and processes as the worlds of our own solar system, just delivered by circumstance into orbits that we never anticipated until we looked closely enough to find them. And Kepler found them in abundance, each one a data point in the growing catalogue of planetary diversity, each one a quiet testament to the inventiveness of nature in arranging matter around stars. And we can let these thoughts settle gently as we continue onward, through the calm dark of space where distant worlds circle distant suns, some scalding and some frozen, some massive and some small, all of them real, all of them waiting to be understood. Among all the revelations that emerged from the Kepler Space Telescope's patient survey of the heavens, perhaps none proved quite so unexpected, or quite so thought-provoking, as the discovery of what our own solar system appears to be missing. For when scientists began to tally the kinds of worlds that orbit other stars, they found that the most common type of planet in our galaxy, the variety that shows up again and again around star after star, is a size of world that simply does not exist here at home, orbiting our own sun. These planets, which astronomers came to call super-Earths and mini-Neptunes, occupy a size range between our familiar rocky Earth and the much larger ice giant Neptune, and their abundance throughout the Milky Way stands as one of the most surprising findings in the entire history of planetary science. A gentle reminder that what we experience in our own cosmic neighborhood is not necessarily typical of what exists elsewhere in the universe. To understand this discovery, it helps to consider the range of planetary sizes that we knew about before the era of space telescopes dedicated to finding other worlds. In our solar system, we have the four inner rocky planets: Mercury, Venus, Earth, and Mars, all of which are relatively small and dense, composed primarily of rock and metal, with solid surfaces beneath their atmospheres where such atmospheres exist. Then, separated by the asteroid belt, we have the four outer planets, Jupiter and Saturn being the enormous gas giants, followed by Uranus and Neptune, which are smaller but still quite large, classified as ice giants due to their substantial compositions of water, ammonia, and methane ices alongside hydrogen and helium. What we do not have, anywhere in our solar system, is a planet that falls between these two groups in size, something larger than Earth but smaller than Neptune, a world that might possess characteristics of both the rocky inner planets and the gaseous outer ones. Neptune has a radius approximately 3.9 times that of Earth, while Earth itself is the largest of the rocky planets in our system. This leaves a rather substantial gap in the sizes of worlds orbiting our Sun, and for many years, astronomers assumed quite reasonably, that this gap might be a natural feature of how planetary systems form. Perhaps there was something about the physics of planet formation that made it difficult to create worlds in this intermediate size range. Or perhaps the processes that built solar systems tended to produce either small rocky worlds close to the star or large gaseous ones farther out, with nothing much in between. These assumptions seemed sensible given what we could observe, which was, after all, limited to the single example of our own solar system. Kepler changed all of this, thoroughly and permanently, by providing the first statistically meaningful census of planets orbiting other stars. As the mission observed its target field in the constellation Cygnus, watching hundreds of thousands of stars for the tiny dimming that would indicate a transiting planet, certain patterns began to emerge from the data. The transit method favors the detection of larger planets, since they block more light, and planets that orbit close to their stars, since they transit more frequently and are more likely to have their orbital planes aligned with our line of sight. But even accounting for these biases, the distribution of planet sizes that Kepler detected told a clear and surprising story. Planets in the size range of roughly 1.5 to 2 Earth radii, which is to say planets significantly larger than Earth but much smaller than Neptune, turned out to be extraordinarily common, appearing around a substantial fraction of all the Sun-like stars in the survey. These worlds came to be classified broadly into two categories that overlap in size but differ in their likely compositions. Super-Earths, a term that became widely used despite some ambiguity in its precise definition, generally refers to planets that are larger and more massive than Earth but still primarily rocky in composition, possessing solid surfaces much like our own world, though with stronger surface gravity due to their greater mass. Mini-Neptunes, on the other hand, are planets of similar or somewhat larger size that possess substantial gaseous envelopes, thick atmospheres of hydrogen and helium that give them lower overall densities, making them more similar in composition to the ice giants of our outer solar system, though much smaller and often much closer to their host stars. The boundary between these two categories is not sharp, and determining whether a particular planet is a large super-Earth or a small mini-Neptune often requires careful measurements of both the planet size and its mass, from which the density can be calculated. Among the many specific discoveries that illustrated this new understanding of planetary populations, the confirmation of Kepler 22b in December of 2011 stands as a particularly notable milestone. This world, orbiting a star somewhat similar to our Sun at a distance that places it within the habitable zone, became the first confirmed super-Earth-sized planet known to orbit within the region around its star where liquid water might conceivably exist on the surface. Kepler 22b has a radius approximately 2.4 times that of Earth, placing it firmly in the size range that our solar system lacks, and its orbital period of about 290 days gives it a year not terribly different in length from our own. The announcement of this discovery generated considerable interest, as it represented a kind of planet that might, under the right circumstances, possess conditions amenable to life as we understand it, though many uncertainties remained about the planet's actual nature, including whether it possesses a solid surface at all or whether it might be more Neptune-like in composition. The accumulating data from Kepler allowed astronomers to conduct statistical analyses of the entire population of detected planets, correcting carefully for the known biases in the detection method, and the results of these analyses were striking in their implications. Studies suggested that roughly 30% of Sun-like stars host at least one super-Earth in a relatively close orbit, and when the analysis was extended to include smaller red dwarf stars, which are far more numerous in the galaxy, the fraction appeared even higher. Super-Earths and mini-Neptunes, it became clear, are not rare or unusual objects but rather the most common type of planet in the Milky Way, outnumbering both smaller Earth-sized worlds and larger gas giants. The galaxy is filled with these intermediate-sized planets, orbiting stars of all types, in a tremendous variety of orbital configurations, and yet our own solar system contains not a single example. As more and more planetary sizes were measured with increasing precision, a curious feature began to emerge in the distribution of planet radii. There appeared to be a relative scarcity of planets at a size of roughly 1.8 Earth radii, a dip in the population that separated smaller, denser worlds from larger, puffier ones. This feature, which astronomers came to call the Radius Valley, or sometimes the Fulton Gap after one of the researchers who helped characterize it, suggested that planets do not form in a smooth continuum of sizes but rather tend to cluster on either side of this boundary. Below the valley, planets are predominantly rocky super-Earths with relatively high densities, while above the valley, planets tend to be mini-Neptunes with substantial gaseous envelopes that give them lower densities despite their larger sizes. The explanation for this Radius Valley that gained the most support among planetary scientists involves a process called photoevaporation, a term that describes the gradual stripping away of a planet's atmosphere by the intense radiation from its host star. According to this theory, many planets form with modest atmospheres of hydrogen and helium, captured from the disk of gas and dust that surrounded the young star. For planets that are sufficiently small, however, these primordial atmospheres are not gravitationally bound strongly enough to resist the continuous bombardment of high-energy radiation from the star, particularly during the first few 100 million years when young stars tend to be especially active and emit copious amounts of X-rays and ultraviolet light. Over time, this radiation heats the atmosphere and causes it to escape into space, eventually stripping the planet down to its bare rocky core. Planets that start out somewhat larger, however, have stronger gravitational fields that can retain at least some of their primordial atmosphere even in the face of this radiation. The result is a bifurcation in the population, with smaller planets losing their atmospheres entirely and becoming dense rocky super-Earths, while larger planets retain enough gas to remain as puffy mini-Neptunes. The Radius Valley represents the transition zone between these two outcomes, a size at which the fate of the atmosphere hangs in the balance, dependent on factors such as the intensity of the stellar radiation, the composition of the atmosphere, and the precise mass of the planet. This theoretical framework, while still subject to ongoing refinement and investigation, provides a coherent explanation for the observed distribution of planet sizes and helps to explain why the distinction between rocky and gaseous worlds falls where it does. Before the super-Earths captured the full attention of the astronomical community, Kepler had already made history by confirming the first unambiguously rocky exoplanet ever detected. Kepler 10b, announced in January of 2011, was a world with a radius of about 1.4 times that of Earth, orbiting extremely close to its host star with a period of less than 1 Earth day. Follow-up observations using ground-based telescopes allowed astronomers to measure the mass of this planet by detecting the tiny wobble it induces in its star, and the combination of mass and radius gave a density that was clearly consistent with a rocky composition similar to Earth's. This was definitive evidence that rocky planets exist around other stars, a finding that may seem obvious in retrospect but was of tremendous scientific importance at the time. However, Kepler 10b is by no means a habitable world, or indeed a pleasant place by any measure that might apply to life as we know it. orbiting so close to its star. This rocky planet is tidally locked, meaning one side perpetually faces the star while the other faces away into the cold of space, and the surface temperature on the day side exceeds 1,300 degrees Celsius, hot enough to melt most types of rock. The surface may well be covered in flowing lava, glowing dully red or orange with the heat of the stellar radiation that pounds relentlessly down upon it. Kepler 10b serves as a reminder that being rocky does not necessarily mean being Earth-like in any broader sense, and that the diversity of planets in the universe includes many worlds that bear little resemblance to the temperate, watery environment we call home. Another intriguing world that emerged from the Kepler data is Kepler 138d, a planet that has attracted particular interest because its measured mass and radius suggest a surprisingly low density, lower than would be expected for a purely rocky world. This planet is part of a system containing multiple transiting planets, and careful analysis of the gravitational interactions between these worlds has allowed astronomers to constrain their masses with reasonable precision. The density of Kepler 138d appears to require a substantial component of water or other volatile materials, leading to speculation that it might represent a water world, a planet with a global ocean of extraordinary depth, far deeper than any ocean on Earth, or perhaps a world with an atmosphere rich in water vapor. The exact nature of this planet remains uncertain, as different compositions could produce similar densities, but it stands as an example of the exotic possibilities that exist among the super-Earth population. In December of 2011, the same month that saw the announcement of Kepler 22b, astronomers also reported the discovery of Kepler 20e and Kepler 20f, two planets that stood out for being smaller than Earth rather than larger. Kepler 20e has a radius of approximately 0.87 times that of Earth, while Kepler 20f is slightly larger than Earth at about 1.03 Earth radii. These were the first exoplanets confirmed with sizes genuinely comparable to or smaller than our own world, demonstrating that Kepler had the sensitivity to detect truly Earth-sized worlds and not merely the larger super-Earths that produce deeper transits and are easier to find. Both planets orbit quite close to their star, with periods of 6 and 20 days respectively, making them far too hot for liquid water to exist on their surfaces. But their discovery was nonetheless a significant achievement in the ongoing search for worlds similar to our own. The puzzle of why our solar system lacks super-Earths and mini-Neptunes, when these planets are so abundant elsewhere in the galaxy, remains an active area of research and speculation. Several theories have been proposed to explain this curious absence. One possibility involves the migration of Jupiter early in the history of our solar system, a scenario sometimes called the Grand Tack hypothesis, in which Jupiter formed farther from the Sun and then migrated inward before eventually migrating back outward again. This wandering giant planet might have disrupted or scattered the material that could have formed super-Earths in the inner solar system, preventing their formation or ejecting them from the system entirely. Another possibility is that super-Earths did once exist in our solar system but were destabilized by gravitational interactions with the giant planets and either fell into the Sun or were flung out into interstellar space during some early period of dynamical chaos. It is also possible that the conditions in the disk of gas and dust from which our solar system formed were simply different from the conditions that prevail in typical planet-forming disks, leading to a different distribution of planet sizes by some process that remains poorly understood. The amount of solid material available in the inner disk, the timescale over which the gas dissipated, the locations where planetesimals first began to accumulate, all of these factors could influence the types of planets that ultimately form, And our solar system may simply represent one particular outcome among many possible outcomes, shaped by the specific circumstances that happened to prevail 4.5 billion years ago. Whatever the reason for this absence, the discovery that super-Earths and mini-Neptunes dominate the planetary census of the galaxy has profound implications for our understanding of how planets form and evolve. Our solar system, with its neat division between small rocky worlds and large gaseous ones, is apparently not the standard template for planetary systems but rather something of an outlier, a somewhat unusual configuration that happens to be the one we call home. The most common planets in the universe are worlds we have never seen up close, worlds of a type that we cannot study by simply pointing our telescopes at the sky around us, worlds that exist in abundance around distant stars but not around our own sun. This realization invites a certain humility, a recognition that the universe is far more varied and inventive than we might have supposed based solely on the example nearest to hand. The planets that Kepler found in such profusion, the super-Earths and mini-Neptunes that populate the galaxy in their countless billions, represent a major category of world that we knew nothing about until quite recently, a category that now appears to be the dominant mode of planet formation in the cosmos. And so the data continues to accumulate. The surveys continue to expand to other regions of the sky, and our understanding of the planetary population of the Milky Way continues to grow, revealing ever more clearly the remarkable diversity of worlds that orbit the stars. In the year 2011, on the 15th day of September, a team of astronomers working with Kepler data announced a discovery that seemed to belong more to the realm of science fiction than to the careful, methodical world of observational astronomy. And yet there it was, confirmed beyond reasonable doubt. A planet orbiting not one star but two, a world where any hypothetical observer standing on its surface, or perhaps floating in its thick atmosphere, would witness the rise and set of two suns moving across the sky in their own intricate dance. And this world was given the designation Kepler 16b. Though it quickly acquired an informal name drawn from popular imagination, a name that acknowledged the debt that real science sometimes owes to the dreams of storytellers. And that name was Tatooine, after the fictional desert world from a well-known film series where a young man once watched twin suns sink toward a distant horizon. The existence of planets orbiting binary star systems had been theorized for many decades before this confirmation, and astronomers had long suspected that such worlds might be rather common throughout the galaxy, given that a significant fraction of all stars exist in binary or multiple star systems rather than in solitary splendor like our own sun. But theoretical possibility and confirmed observation are very different things. And the detection of Kepler 16b represented the first time that scientists could point to unambiguous evidence that a planet was indeed orbiting around both members of a binary pair, following a path that enclosed both stars within its orbital embrace, a configuration that astronomers call circumbinary, meaning around the binary, to distinguish it from the other theoretical possibility where a planet might orbit just one member of a binary system while the companion star circles at a much greater distance. The Kepler 16 system lies approximately 200 light-years from Earth in the direction of the constellation Cygnus, the Swan, and it consists of two stars that orbit their common center of mass once every 41 days. With the primary star being a K-type dwarf somewhat smaller and cooler than our Sun, perhaps 6 to 9% of the Sun's mass, and the secondary being an M-type red dwarf with only about 20% of the Sun's mass, making it a dim and ruddy companion to its larger partner. And the planet Kepler 16b orbits around this stellar pair at a distance of approximately 105 million kilometers. Completing each circuit in 229 days. placing it at roughly the same distance from its stars as Venus is from our Sun, though the cooler nature of its host stars means that it receives less warmth than Venus does, making its surface temperature something closer to that of a very cold Earth, perhaps -70 or -80 degrees Celsius. Far too cold for liquid water even if the planet had a solid surface, which it does not, being a gas giant of roughly Saturn's size and composition. The detection of this planet required specialized techniques that went beyond the standard transit hunting methods that Kepler employed for single-star systems, and this work was led by several astronomers whose expertise in binary star systems made them particularly well-suited to searching for these elusive circumbinary worlds. Among them Lawrence Doyle of the SETI Institute and William Welsh of San Diego State University, both of whom had been thinking carefully about how binary stars might reveal the presence of orbiting planets and how the unique complications of such systems might actually provide additional information rather than merely additional confusion. When a single star hosts a transiting planet, the timing of each transit is remarkably predictable, with each crossing occurring at intervals determined solely by the planet's orbital period. So that if the orbital period is, say, 100 days, then transits will occur on day 0, day 100, day 200, and so forth, with perhaps very small variations caused by gravitational tugs from other planets in the system. But in a circumbinary system, the situation becomes considerably more complex because the stars themselves are constantly moving, orbiting around their common center of mass, which means that sometimes the planet crosses in front of one star, sometimes in front of the other, and sometimes in front of both in quick succession, and the timing of these events shifts depending on where the stars happen to be in their own orbital dance at the moment the planet passes through the line of sight to Earth. These shifts in transit timing, called transit timing variations, become a powerful diagnostic tool in the hands of careful analysts, because the pattern of timing variations encodes information about the masses and orbital parameters of all the bodies involved, both the two stars and the planet itself, allowing astronomers to construct detailed models of the system's architecture with remarkable precision. And it was precisely this kind of analysis that allowed Doyle, Welsh, and their colleagues to confirm not only that Kepler-16b existed but also to determine its mass, its orbital characteristics, and its relationship to the two stars it accompanies. The announcement of Kepler-16b naturally raised the question of whether this was an extraordinarily rare curiosity, a statistical fluke that happened to fall within Kepler's field of view, or whether it represented the first member of a larger population waiting to be discovered. And this question was answered fairly quickly, in the affirmative, as the specialized search algorithms developed for circumbinary detection were applied more broadly to the growing archive of Kepler data. In early 2012, the discovery of two more circumbinary planets was announced, these being Kepler-34b and Kepler-35b, both of them gas giants orbiting binary star systems in the Kepler field. And while they shared the general characteristic of being large planets on circumbinary orbits, they differed from Kepler-16b and from each other in various details, suggesting that nature had produced a diverse population of these worlds rather than following a single template. And this diversity was reassuring because it implied that circumbinary planets were not the result of some extraordinarily improbable set of circumstances, but rather emerged naturally from the ordinary processes of planet formation operating in binary environments. Kepler-34b orbits a pair of Sun-like stars that circle each other every 28 days, with the planet itself completing its orbit in 289 days, while Kepler-35b orbits a pair of stars that complete their mutual orbit in 21 days. with the planet requiring 131 days to complete its circuit. And both planets are somewhat smaller than Jupiter, placing them in a similar category to Kepler 16b as modest gas giants rather than the inflated hot Jupiters found orbiting very close to single stars. The discovery of multiple circumbinary systems allowed astronomers to begin identifying patterns and testing theories about how such planets form and where they can exist in stable orbits. And one of the most important findings concerned the minimum distance at which a planet can orbit a binary pair without being gravitationally disrupted by the complex tidal forces generated by two moving stellar masses. Theoretical calculations had long suggested that a circumbinary planet must maintain a certain safe distance from its host stars in order to avoid being ejected from the system or torn apart by gravitational perturbations. And the general rule that emerged from both theory and observation is that the planet must orbit at a distance of at least 3 times the separation of the binary stars themselves. So if the two stars are separated by, say, 10 million kilometers as they orbit their common center, then any planet must remain at least 30 million kilometers away from that center in order to maintain long-term stability. And planets that venture closer than this critical distance find themselves in a chaotic gravitational environment where the constantly shifting positions of the two stars create overlapping zones of influence that can gradually perturb the planet's orbit until it either collides with one of the stars, falls into an unstable trajectory, or is ejected from the system entirely. This stability boundary creates an interesting consequence for the habitable zones of binary star systems. Because the region where liquid water might exist on a rocky planet's surface must lie outside this minimum stable distance, and in some binary systems this condition is met while in others the habitable zone lies within the forbidden region, making it impossible for potentially life-bearing worlds to exist on stable orbits. Among the most intriguing of the circumbinary systems discovered by Kepler was one that appeared to harbor not just one planet but multiple worlds, a finding that demonstrated that complex planetary systems can indeed form and persist around binary stars. And this system, designated Kepler 47, was first announced in 2012 with 2 confirmed planets, and subsequent analysis eventually revealed a 3rd planet, bringing the total to 3 by 2019. The Kepler 47 system is located approximately 3,300 light-years from Earth, making it one of the more distant systems studied intensively by the Kepler mission, and it contains a Sun-like primary star paired with a red dwarf companion that orbit each other every 7.5 days. Quite a bit faster than the binaries in the other systems discussed so far. And around this stellar pair orbit 3 planets with orbital periods of approximately 49 days, 187 days, and 303 days respectively. The outermost planet in this system, which carries the designation Kepler 47c, orbits within what astronomers consider the habitable zone of the binary pair, the region where temperatures might allow liquid water to exist on a rocky surface. Though Kepler 47c itself is likely a gas giant incapable of supporting life as we understand it. But the mere existence of a planet in the habitable zone of a circumbinary system was significant because it demonstrated that such configurations are dynamically possible, opening the door to the hope that smaller, rocky worlds might exist in similar positions around other binary stars. Another notable circumbinary system was Kepler 453, announced in 2015, which also harbors a planet within the habitable zone of its binary hosts, a world designated Kepler 453b that orbits a pair of stars every 240 days. Placing it in a temperature regime that might theoretically allow for liquid water if the planet had the right atmospheric composition, though once again the planet appears to be a gas giant rather than a rocky world. The planet Kepler 453b presented additional interest because its orbital plane is tilted just slightly relative to the plane of the binary star orbit. And this tilt causes the transits to drift over time, sometimes appearing across the face of one or both stars and sometimes missing entirely, a phenomenon called transit wobble that required particularly careful analysis to confirm the planet's existence and to determine its orbital parameters with precision. Throughout the Kepler mission, the specialized search for circumbinary planets continued, with William Welsh and his collaborators developing increasingly sophisticated algorithms to detect the characteristic signatures of these worlds amid the complex light curves produced by eclipsing binary stars. And by the end of the mission, the confirmed population of circumbinary planets stood at approximately 10 to 12 worlds, depending on how one counts borderline cases and systems with somewhat ambiguous detections. A small number compared to the thousands of planets found around single stars, but still a significant population given the additional challenges involved in both formation and detection. The existence of these worlds poses interesting questions about planet formation, because the traditional models that explain how planets coalesce from disks of gas and dust around young stars must be modified to account for the gravitational complications introduced by a second stellar mass. One prominent theory of planet formation, called the disk instability model, suggests that giant planets can form relatively quickly when regions of a protoplanetary disk become gravitationally unstable and collapse directly into planet-sized bodies. But this process requires a relatively calm and uniform disk, and the presence of a binary companion stirs and heats the inner regions of the disk in ways that might prevent such instabilities from developing, which suggests that circumbinary planets, particularly the giant planets detected by Kepler, likely formed through the alternative mechanism of core accretion, where solid particles gradually stick together to form larger and larger bodies until a rocky core massive enough to attract a gaseous envelope emerges. Furthermore, many theorists believe that circumbinary planets probably did not form at their current locations, where the gravitational environment would have been too turbulent for the delicate early stages of planet building, but rather formed in the calmer outer regions of the protoplanetary disk and later migrated inward to their present orbits through interactions with the remaining gas and dust, a process that must have been carefully balanced to allow the planets to settle into stable orbits just outside the critical stability boundary without overshooting and falling into the danger zone. The fact that many of the detected circumbinary planets orbit remarkably close to this stability boundary, just slightly beyond the minimum safe distance, supports this migration hypothesis, because it suggests that the planets were gently guided inward until they reached the edge of the stable region and could migrate no further without risking ejection, parking themselves at the innermost possible location like cars lined up against a curb. The total number of circumbinary planets discovered by Kepler may seem modest compared to the overall mission haul, but it must be remembered that these detections are inherently more difficult than those around single stars, partly because of the complex light curves that must be analyzed, partly because circumbinary planets with orbital periods longer than a few hundred days may transit only rarely during the mission lifetime, and partly because the transit probability, the geometric likelihood that the orbital plane is aligned to produce observable transits, is somewhat lower for circumbinary systems due to their extended configuration. Statistical analyses suggest that circumbinary planets may be roughly as common as planets around single stars, with perhaps 1 in 10 binary systems hosting at least one planet, though the uncertainties remain large and future surveys will be needed to refine these estimates. But even this preliminary assessment implies that the galaxy contains billions of worlds orbiting pairs of stars, worlds where double sunsets are the norm rather than the exception. worlds that until September of 2011 remained entirely in the realm of imagination. The Kepler mission's contribution to circumbinary planet science extended beyond mere detection, as the precise timing measurements enabled by its 4 years of continuous observation allowed astronomers to measure the masses and orbital eccentricities of these worlds with unprecedented accuracy, building a foundation for theoretical models of circumbinary dynamics that will guide future studies for decades to come. And the techniques developed by Welsh, Doyle, and their colleagues have been adapted for use with other telescopes and other datasets, continuing the search for these doubly illuminated worlds even after Kepler itself fell silent. So when you drift towards sleep and picture distant skies, you might imagine for a moment standing on a high plateau beneath an atmosphere thick enough to dim the stellar glare, watching 2 suns move across the heavens in their endless orbital waltz, sometimes close together, sometimes far apart, casting double shadows that lengthen and shorten in complex patterns unknown on any single starred world. And you might reflect that such places truly exist, that Kepler found them, that the universe accommodates possibilities even stranger and more wonderful than the fictions that anticipated them. And with that thought settling gently into your mind like dust settling through still air, you can let your eyes grow heavy and your breathing slow, knowing that somewhere out there, around one of those 10 or 11 confirmed systems, 2 suns are rising now over a world that orbits them both, marking the start of another day in a cosmos that continues to surprise and soothe in equal measure. When we gaze at the night sky and consider the planets that orbit distant stars, it is easy to imagine each world as a solitary companion to its sun, drifting alone through the vast emptiness of space. But the Kepler Space Telescope gradually revealed something rather different, something that speaks to the busy and companionable nature of planetary formation. Many stars, it turns out, host not 1 or 2 planets, but entire families of worlds, all orbiting in careful procession around their parent star. These systems with 5, 6, 7, or even 8 planets became some of the most fascinating discoveries of the Kepler mission, and they taught us that our own solar system, with its 8 major planets, is perhaps not so unusual in its multiplicity, even if the particular arrangement of those worlds differs in ways that are themselves quite interesting to consider. In February of 2011, the Kepler team announced a discovery that captured the quiet attention of astronomers around the world, though it arrived without fanfare or dramatic proclamation, as is fitting for the steady work of science. The Kepler 11 system, located approximately 2,000 light-years away in the direction of the constellation Cygnus, was found to host 6 planets, all of which happened to transit across the face of their star as seen from our vantage point. This alone was remarkable, as the geometric alignment required for multiple planets to all cross in front of their star is not something we would expect to encounter frequently. The star itself is rather similar to our own Sun, a yellow dwarf of comparable size and temperature, which made the comparison to our own solar system all the more inviting, even as the differences became immediately apparent. The 6 planets of Kepler 11, designated with the letters B through G in the order of their discovery, all orbit extraordinarily close to their star. 5 of these 6 worlds complete their orbits within a region smaller than the orbit of Mercury around our own Sun. To put this in perspective, Mercury orbits at an average distance of about 58 million kilometers from the Sun, and yet in the Kepler 11 system, 5 substantial planets are packed into this compact region, each following its own circular path, each maintaining a careful distance from its neighbors. The innermost planet, Kepler 11b, completes an orbit in just over 10 days, while the outermost of the inner five, Kepler 11f, takes about 47 days to circle the star. Even Kepler 11g, the most distant planet in the system, orbits in just under 118 days, which would place it well inside the orbit of Venus if it were transported to our own solar system. The masses of these planets, determined through careful analysis of the way they gravitationally tug on one another, revealed that they are larger than Earth but smaller than Neptune, falling into that intermediate category that astronomers have come to call super-Earths or mini-Neptunes, depending on their presumed composition. They appear to possess substantial envelopes of hydrogen and helium gas, puffing them up to sizes larger than their masses alone would suggest. This was itself a small revelation, as it indicated that planets of this intermediate size, which do not exist in our own solar system, can retain significant atmospheres even when orbiting relatively close to their stars. What made the Kepler 11 system particularly instructive was the arrangement of its planetary orbits, which showed evidence of what astronomers call orbital resonances. A resonance occurs when the orbital periods of two planets form a simple numerical ratio, such as 2 to 1 or 3 to 2, meaning that one planet completes exactly 2 orbits for every 1 orbit of its neighbor, or 3 orbits for every 2. In the Kepler 11 system, several adjacent pairs of planets are near, though not exactly in, such resonant configurations. This near-resonant arrangement is thought to be a signature of the migration history of these planets, suggesting that they did not form in their current locations but instead drifted inward from farther out in the protoplanetary disk, moving gently through the gas and dust that surrounded their young star billions of years ago. The resonance chains observed in systems like Kepler 11 indicate a gentle form of migration, where planets move slowly inward over millions of years, nudged by interactions with the disk material, and as they migrate, they can capture one another into these resonant relationships. The fact that the resonances are not exact but merely approximate suggests that some subsequent perturbation may have slightly disrupted the original perfect arrangement, though the general pattern remains visible as a kind of fossil record of the system's early history. Understanding these migration pathways helps astronomers reconstruct the conditions that existed when these planets were young, and it provides clues about how planets come to occupy the orbits we observe them in today. As the Kepler mission continued its patient observations over the years, more and more multi-planet systems came to light, and among the most impressive was Kepler 90, a system that eventually proved to host 8 planets, matching the count of our own solar system. The Kepler 90 system is located about 2,500 light-years away, also in Cygnus, and its star is slightly hotter and more massive than the Sun. The initial discoveries of planets in this system accumulated over several years, with each new world adding to the growing sense that this was a particularly prolific stellar neighborhood. The 8th planet in the Kepler 90 system, designated Kepler 90I, was announced in December of 2017, and its discovery came about through an interesting collaboration between astronomers and artificial intelligence. Researchers at Google and the University of Texas at Austin applied a neural network, a type of machine learning algorithm loosely inspired by the structure of biological brains, to the Kepler dataset. The neural network was trained to recognize the subtle patterns of dimming caused by transiting planets, distinguishing these signals from the many other sources of noise and variability that affect stellar brightness measurements. When applied to the Kepler 90 system, the neural network identified the faint signal of Kepler 90I, a small rocky world about 30% larger than Earth that had been overlooked in previous analyses. Kepler 90I orbits very close to its star, completing a circuit in just 14.5 days, and its surface is likely extremely hot. Far too hot for liquid water or any form of life as we understand it. But its discovery demonstrated that the Kepler dataset still held secrets waiting to be uncovered, and that new analytical techniques could reveal planets that had previously escaped detection. The full Kepler 90 system, with its 8 worlds, became a kind of distant mirror to our own solar system, though a somewhat distorted one, as all 8 planets in Kepler 90 orbit within the equivalent of Earth's orbit around the Sun. Once again, we see the pattern of compact arrangement that Kepler revealed to be so common among planetary systems in our galaxy. Another system that illustrates the phenomenon of orbital resonance with particular elegance is Kepler 80, which hosts at least 6 planets, 5 of which are locked into a remarkable resonance chain. The planets Kepler 80d, Kepler 80e, Kepler 80b, Kepler 80c, and Kepler 80g have orbital periods that form a connected sequence of resonances, with each adjacent pair maintaining a specific ratio that keeps the system in a delicate but stable gravitational harmony. The periods of these planets are approximately 3 days, 4 days, 7 days, 9 days, and 15 days, and the ratios between adjacent pairs are close to 9:7, 3:2, 3:2, and 4:3. This chain of resonances means that the planets periodically align in specific configurations, giving each other gravitational nudges at regular intervals that reinforce their mutual arrangement rather than disrupting it. Such resonance chains are thought to be the natural outcome of smooth, gentle migration through a protoplanetary disk, and their survival over billions of years indicates that the system has remained relatively undisturbed since its formation. Systems with disrupted resonances, by contrast, may have experienced more violent histories, with close encounters or gravitational scattering events that knocked the planets out of their original harmonic relationships. The Kepler 80 system thus serves as a kind of pristine example of ordered planetary architecture, a clockwork arrangement that has ticked along since the early days of the solar system's youth. As more multi-planet systems were discovered and characterized, a striking pattern began to emerge from the data, a pattern that was elegantly described in a study led by astronomer Lauren Weiss at the University of California, Berkeley. Weiss and her colleagues examined the sizes of planets in multi-planet systems detected by Kepler and found that planets orbiting the same star tend to be similar in size to one another. They described this as the peas in a pod pattern, evoking the image of a vegetable garden where the peas within a single pod are more similar to each other than peas from different pods might be. This peas in a pod architecture suggests that the conditions within a given protoplanetary disk tend to produce planets of similar sizes, at least within the inner regions where Kepler was most sensitive. The spacing between adjacent planets also tends to be regular, with planets distributed at relatively uniform intervals, like evenly spaced beads on a string. This finding was somewhat surprising, as one might have expected planetary systems to display a wide range of architectures, with planets of varying sizes scattered haphazardly around their stars. Instead, there appears to be a certain orderliness to planetary formation, a tendency toward homogeneity within individual systems that speaks to the physics of how planets coalesce from the material available in their natal disks. The discovery and characterization of these multi-planet systems relied heavily on a technique called transit timing variations, which uses subtle deviations in the timing of planetary transits to infer the presence and properties of gravitationally interacting worlds. If a planet were alone in its orbit around a star, Its transits would occur at perfectly regular intervals, like the ticking of an idealized clock. But when multiple planets are present, their gravitational tugs on one another cause slight accelerations and decelerations in their orbital motions, which in turn cause their transits to occur slightly earlier or later than predicted. By measuring these timing variations with great precision, astronomers can determine the masses of the interacting planets, even without measuring their gravitational effects on the star itself. Transit timing variations were essential for confirming that the planets in systems like Kepler 11 and Kepler 80 are genuinely interacting gravitationally, ruling out the possibility that the observed transit signals might arise from unrelated phenomena. They also provided mass estimates that, combined with the size measurements from transit depths, allowed astronomers to calculate the densities of these planets and thus infer something about their compositions. A planet with a low density is likely to be rich in gases or ices, while a planet with a high density is more likely to be rocky, like Earth or Venus. The transit timing variation technique thus transformed the Kepler dataset into a resource not just for counting and measuring planets but for understanding what they are made of. The compact multi-planet systems revealed by Kepler have an interesting cousin in the TRAPPIST-1 system, which was discovered not by Kepler but by ground-based telescopes and later studied in detail by the Spitzer Space Telescope. TRAPPIST-1 is a small, cool red dwarf star located about 40 light-years from Earth, and it hosts 7 Earth-sized planets, all orbiting within a region smaller than the orbit of Mercury. The parallels to Kepler's compact systems are striking, and the TRAPPIST-1 planets are also arranged in a resonance chain, with each planet's orbital period forming a simple ratio with its neighbors. The innermost planet completes an orbit in just 1.5 days, while the outermost takes about 19 days, and all 7 worlds are thought to be rocky, with several residing in or near the star's habitable zone. The discovery of TRAPPIST-1 reinforced the lessons of Kepler, showing that compact multi-planet systems are a common outcome of planetary formation, not just around Sun-like stars but around the smaller, cooler stars that make up the majority of stars in our galaxy. The comparison between TRAPPIST-1 and Kepler's compact systems highlighted both the similarities and the differences between planetary architectures, and it underscored the diversity of worlds that exist beyond our solar system. Among the most remarkable multi-planet systems discovered by Kepler is Kepler 444, a system that stands out not for the number of its planets or the intricacy of its resonances but for its extraordinary age. Kepler 444 is estimated to be approximately 11.2 billion years old, making it more than twice as old as our own solar system and nearly as old as the Milky Way galaxy itself. This ancient star hosts 5 small, rocky planets, all of which orbit within a region smaller than the orbit of Mercury, completing their circuits in periods ranging from about 3.5 days to just under 10 days. The existence of rocky planets in such an ancient system tells us that the processes of planet formation were already operating efficiently when the universe was still young, when heavy elements like silicon and iron were less abundant than they are today. The Kepler 444 planets are likely too hot and too close to their star to be habitable in any conventional sense, but their presence demonstrates that rocky planets have been forming for most of the history of the cosmos. This has implications for the possibility of life elsewhere in the universe, as it suggests that billions of years have been available for life to arise and evolve on countless worlds that formed long before our own Earth existed. As the Kepler mission accumulated its vast catalogue of planets and planetary candidates, astronomers began to draw broader conclusions about the prevalence of multi-planet systems. Statistical analyses suggested that the majority of planets in our galaxy do not orbit alone but instead share their stellar neighborhoods with sibling worlds. The precise fraction depends on the assumptions made about detection biases and the true distribution of orbital inclinations, but the general picture is one of companionship rather than solitude. Stars with one known planet often have additional planets that remain undetected, either because their orbits do not happen to transit as seen from Earth or because their signals are too faint to distinguish from noise. This inference, that multi-planet systems are the norm rather than the exception, has profound implications for our understanding of planetary formation and for the search for habitable worlds. It suggests that the conditions in protoplanetary disks tend to favor the formation of multiple planets, perhaps through a combination of abundant building material and favorable timescales for growth. It also implies that when we identify a star with one interesting planet, there may well be other planets in the system waiting to be discovered, each with its own story to tell about the history and dynamics of that distant stellar family. And so the Kepler Space Telescope, through its patient and meticulous observations, revealed that planetary systems are often crowded and busy places, with multiple worlds orbiting in careful procession, sometimes locked into resonant chains that preserve the memory of their gentle migrations, sometimes displaying the Ps in a pod uniformity that speaks to the organizing principles of planetary formation. These discoveries, from the 6 transiting planets of Kepler 11 to the 8 worlds of Kepler 90, from the resonant harmony of Kepler 80 to the ancient system of Kepler 444, expanded our understanding of the possible arrangements that planets can take and reminded us that our own solar system, with its diverse family of worlds, is just one example among countless variations on the theme of planetary architecture. The universe, it seems, delights in creating not single planets but whole communities of worlds, each system a quiet neighborhood of orbiting bodies, circling their star in the endless, unhurried rhythm of celestial motion. And so we come now to the worlds that captured imaginations most gently, the planets that seemed to whisper of distant shores and unknown waters, the places where conditions might, just possibly, allow for liquid water to pool upon a surface and linger there through the long turnings of alien seasons. These are the planets of the habitable zone, sometimes called the Goldilocks zone in a nod to that old fairy tale, where the porridge was neither too hot nor too cold but rather something comfortably in between. It is a concept that guided much of Kepler's patient searching, a way of sifting through thousands upon thousands of distant worlds to find those few that orbit at just the right distance from their stars, receiving just the right amount of warmth, existing in that narrow band where water need not boil away into space nor freeze solid as stone. The habitable zone is not a fixed thing, not a rigid boundary drawn with absolute certainty across the cosmic maps. Rather, it is an estimate, a calculated range that depends upon many factors. And during Kepler's long mission, the understanding of this zone evolved and shifted and refined itself through careful study and gentle debate among those who think deeply about such matters. At its simplest, the habitable zone describes the region around a star where a planet with an atmosphere something like Earth's might maintain liquid water on its surface, not so close that the water would evaporate and be lost to space through processes involving ultraviolet light breaking apart water molecules, and not so far that even a thick atmosphere could not trap enough warmth to prevent permanent freezing. But of course planets are complicated things, and atmospheres vary enormously, and the boundaries of habitability depend upon assumptions about atmospheric composition and pressure and cloud cover and so many other variables that the zone becomes less a sharp line and more a gradual fading of probability. During Kepler's mission, scientists developed what came to be called conservative and optimistic boundaries for the habitable zone. Two different ways of drawing the lines depending upon how cautiously or generously one wished to estimate. The conservative habitable zone represents the more careful calculation. The region where scientists felt quite confident that an Earth-like planet could maintain surface water based on well-understood physics and atmospheric models that had been tested against our own solar system. The inner edge of this conservative zone was placed where a runaway greenhouse effect would likely begin, where increasing temperatures would put more water vapor into the atmosphere, which would trap more heat, which would evaporate more water in an unstoppable cycle that would eventually leave a planet dry and scorched. The outer edge was placed where carbon dioxide would begin to condense into clouds or frost at the surface, marking the point beyond which even a thick carbon dioxide atmosphere could not prevent global freezing. The optimistic habitable zone extended these boundaries somewhat, allowing for the possibility that planets might remain habitable under conditions more extreme than our conservative model suggested. Perhaps a planet somewhat closer to its star might avoid the runaway greenhouse through different cloud patterns or atmospheric chemistry. Perhaps a planet somewhat farther out might maintain warmth through internal heat sources or atmospheric compositions we had not fully considered. The optimistic boundaries drew upon observations of Venus and Mars, noting the points in solar system history where these worlds might have possessed liquid water before their climates shifted to their present states. Venus may have been habitable until perhaps 700 million years ago, suggesting that the inner edge of habitability might extend closer to a star than the conservative estimate allowed. Mars shows evidence of ancient rivers and lakes, suggesting that the outer edge might extend farther out under certain atmospheric conditions. These different boundaries mattered enormously when cataloguing Kepler's discoveries. For a planet that fell within the optimistic zone but outside the conservative zone carried a different kind of uncertainty than one that sat comfortably within both estimates. Scientists had to be careful in their language, precise in their claims, acknowledging that habitability remained a probability rather than a certainty, a zone of possibility rather than a guarantee of welcoming conditions. And so the habitable zone evolved from a simple concept to a nuanced framework, a tool for thinking about planetary possibilities that acknowledged the limits of what could be known from brightness measurements alone. Among the worlds Kepler found within these estimated zones, several emerged as particularly intriguing candidates for further study, planets whose sizes and orbital distances placed them in that narrow range where conditions might, under the right circumstances, allow for something like familiar chemistry to occur. One such world was Kepler 62f, announced in April of 2013 as part of a 5-planet system orbiting a star somewhat smaller and cooler than our Sun, located roughly 1,200 light-years away in the direction of the constellation Lyra. Kepler 62f measured approximately 1.4 times the radius of Earth, placing it in that ambiguous size range where it might be a rocky world with a solid surface or might possess a thick envelope of lighter elements that would make it something more like a small Neptune. Its orbital period of 267 days placed it within the habitable zone of its host star, receiving somewhat less warmth than Earth receives from the Sun. The discovery of Kepler 62f came alongside its sibling Kepler 62e, another potentially habitable world in the same system, making this star remarkable for hosting not one but 2 planets of roughly Earth size within the zone where liquid water might persist. The system demonstrated that habitable zone planets need not be solitary wanderers, that multiple such worlds might orbit the same star, perhaps exchanging material through impacts over the ages, perhaps developing independently under similar stellar influences. Scientists noted that Kepler 62f would likely require a substantial atmosphere with significant greenhouse warming to maintain liquid water at its surface, given the modest amount of starlight it receives. And without direct observations of its atmosphere, such questions remained beautifully open, inviting speculation while resisting confirmation. Then came April of 2014 and the announcement of Kepler 186f, a world that achieved a particular distinction in the long catalogue of distant planets, becoming the first Earth-sized planet confirmed to orbit within the habitable zone of another star. Previous discoveries had found larger planets in habitable zones or Earth-sized planets in orbits too close to their stars. But Kepler 186f combined both qualities, measuring just 1.1 times Earth's radius while orbiting at a distance that placed it near the outer edge of its star's habitable zone. The host star, Kepler 186, was a red dwarf roughly half the size and mass of the Sun, cooler and dimmer, requiring planets to orbit much closer to receive comparable warmth. Kepler 186f completed its orbit in 130 days, a swift year by Earth standards but a comfortable distance from its diminutive star. The discovery of Kepler 186f carried particular significance because of its size. A planet just slightly larger than Earth was far more likely to be rocky, to possess a solid surface where liquid might collect and weather might occur, and the slow processes of geology might shape landscapes over millions of years. Larger planets, those exceeding 1.5 or 1.6 Earth radii, increasingly tended to retain thick atmospheres of hydrogen and helium that would create crushing pressures at depth and conditions utterly unlike anything we would call Earth-like. Kepler 186f sat comfortably below this threshold, suggesting, though not proving, a composition similar to our own world, a dense ball of rock and iron with perhaps a thin skin of atmosphere and, just possibly, the sparkle of water under an alien sun that appeared as a dim orange disk in skies we can only imagine. Red dwarf stars like Kepler 186 present both advantages and challenges for habitability. They are the most common type of star in our galaxy, comprising perhaps 3/4 of all stars, meaning that if their planets can be habitable, then the universe contains far more potential homes for life than if only Sun-like stars provide suitable conditions. They burn their fuel slowly, remaining stable for tens of billions of years, far longer than the Sun's projected 10 billion-year lifespan, providing patient constancy for any life that might arise. But they also tend toward magnetic activity, producing flares that can bombard close-orbiting planets with radiation, potentially stripping away atmospheres and sterilizing surfaces. Planets in the habitable zones of red dwarfs orbit so close that they likely become tidally locked, always showing the same face to their star as the Moon shows to Earth, creating permanent day and night hemispheres with unknown consequences for climate and habitability. The year 2015 brought several more noteworthy additions to the catalogue of potentially habitable worlds. In January, scientists announced the discovery of Kepler 442b and Kepler 438b, both planets that seem to fall squarely within the habitable zones of their respective stars, both small enough to suggest rocky compositions. Kepler 442b orbited a star slightly smaller and cooler than the Sun, completing its year in 112 days and measuring approximately 1.34 times the radius of Earth. Calculations suggested it received roughly 70% of the sunlight that Earth receives, placing it in a comfortable region of the habitable zone where liquid water seemed plausible given reasonable atmospheric assumptions. Its host star lay about 116 light-years away, relatively close by the standards of Kepler discoveries, and the star's modest activity levels suggested a relatively calm environment for any planets in its vicinity. Kepler 438b initially generated considerable interest as one of the most Earth-like planets yet discovered, measuring just 1.12 times Earth's radius and orbiting in the habitable zone of a red dwarf star approximately 470 light-years away. Its size placed it firmly in the range expected for rocky planets, and its position relative to its star suggested surface temperatures that might allow for liquid water. For a time it occupied a prominent place in lists of potentially habitable worlds, a small sphere of possibility glittering in the data from Kepler's patient observations. But as is often the case in science, further study introduced complications and uncertainties. Later in 2015, researchers examining the host star of Kepler 438b discovered evidence of powerful stellar flares, eruptions of energy that regularly bathed the planet in harsh radiation. These flares occurred frequently and with substantial intensity, raising concerns about whether any atmosphere could survive such bombardment over geological timescales, or whether the planet's surface might be sterilized by the regular influx of high-energy particles. The discovery served as a reminder that habitability depends upon far more than orbital distance alone, that the behavior of the host star matters enormously, and that red dwarf planets face challenges that planets around Sun-like stars might avoid. Kepler 438b did not vanish from the catalogue or lose its physical properties, but its status as a potentially habitable world became considerably more uncertain, a lesson in the caution required when extrapolating from limited data. July of 2015 brought the announcement of Kepler 452b, a discovery that garnered considerable attention for its resemblance not just to Earth but to the Earth-Sun system as a whole. Unlike many previous discoveries of habitable zone planets around red dwarf stars, Kepler 452b orbited a star remarkably similar to our Sun, a G-type star of nearly identical temperature and luminosity, located approximately 1400 light-years away in the constellation Cygnus. The planet's orbital period of 385 days placed it in a habitable zone orbit almost identical to Earth's, receiving similar amounts of stellar energy and experiencing similar year lengths. Scientists described it as something like Earth's cousin, a world that shared key orbital characteristics with our own planet while remaining tantalizingly beyond detailed investigation. Kepler 452b measured approximately 1.6 times the radius of Earth, placing it at the boundary between likely rocky planets and those that might possess significant gaseous envelopes. This size made its composition uncertain, perhaps a larger rocky world with a thicker atmosphere, perhaps something with a small amount of retained hydrogen and helium, creating conditions unlike anything on Earth. Its host star was somewhat older than the Sun, approximately 6 billion years compared to our star's 4.5 billion years, suggesting that if the planet followed a similar evolutionary path to Earth, it might have had more time for geological and potentially biological processes to unfold. The star's greater age also meant it had grown slightly brighter over time, as stars do as they age, meaning Kepler 452b currently receives about 10% more energy than Earth receives from the Sun, perhaps placing it at an interesting moment in its climatic evolution. The discovery of Kepler 452b highlighted both the triumphs and limitations of Kepler's method. Here was a planet orbiting in the habitable zone of a Sun-like star, discovered through the patient accumulation of transit signals over several years of observation. Yet without mass measurements, the planet's composition remained uncertain. Without atmospheric observations, its surface conditions remained unknown. Without detailed study, it remained a point of light that dimmed slightly every 385 days. A planet known to exist but understood only in the broadest terms. The cousin remained distant, known by family resemblance but never met, never examined closely, never truly understood. And this was perhaps the central challenge that Kepler's habitable zone discoveries presented to science: the frustrating gap between knowing that a planet exists and knowing whether it might truly be habitable. Kepler could measure a planet's size and orbital period with remarkable precision. From these measurements and knowledge of the host star, scientists could calculate how much energy the planet received and whether liquid water might be possible on its surface. But the actual presence of water, the existence of an atmosphere, the composition of that atmosphere, the nature of any surface beneath it, all of these remained beyond Kepler's ability to determine. The telescope saw shadows, not surfaces. It measured dimming, not chemistry. It found candidates for habitability without being able to confirm whether any of them actually possessed the conditions that make a world welcoming to life. This limitation drove much of the subsequent planning for future space telescopes and encouraged the development of techniques for studying planetary atmospheres from afar. Kepler found the planets. Other instruments would need to characterize them. The transit method itself offered a pathway toward atmospheric study, for when a planet passes in front of its star, some starlight filters through any atmosphere the planet possesses, acquiring subtle spectral signatures that reveal atmospheric composition. But such observations required larger telescopes, brighter stars, and more favorable geometries than most of Kepler's targets provided. The habitable zone planets Kepler discovered remained, for the most part, beautiful possibilities rather than confirmed habitable worlds, invitations to further study rather than final answers. Despite these limitations, the sheer number of habitable zone candidates Kepler found allowed scientists to begin answering a question of profound importance, a question about how common Earth-like planets might be across the galaxy as a whole. In 2013, a team of researchers led by Eric Pettigura published an analysis of Kepler data that attempted to calculate what they called Eta-Earth, the fraction of Sun-like stars that host Earth-sized planets in their habitable zones. By carefully accounting for the planets Kepler did detect, the planets it would have missed due to unfavorable orbital alignments, and the planets it would have missed due to signal strength limitations, they extrapolated from the observed sample to estimate the underlying population. Their findings suggested that roughly 22% of Sun-like stars might host an Earth-sized planet in their habitable zone. Given the estimated number of Sun-like stars in the Milky Way, this calculation implied approximately 40 billion Earth-sized planets orbiting in habitable zones throughout our galaxy, a number so large it nearly defies comprehension. 40 billion opportunities for liquid water and stable temperatures, and perhaps the gradual chemical complexification that leads, in at least one instance we know of, to life. 40 billion worlds roughly Earth-sized at roughly Earth-like distances from roughly Sun-like stars, scattered throughout a galaxy that itself is only one among hundreds of billions of galaxies in the observable universe. The Eta-Earth calculation sparked considerable debate among astronomers, for such extrapolations depend sensitively upon assumptions and definitions and the handling of uncertain data. Different researchers using different methods and different definitions of Earth-sized and habitable zone arrived at different estimates, some higher and some lower, but all suggesting that Earth-like planets were not rare. The conservative estimates placed Eta-Earth lower, perhaps around 10%, while optimistic estimates pushed it higher, perhaps above 30%. The exact value remained uncertain, but the general conclusion seemed robust. Planets like Earth were not flukes, not cosmic accidents, not vanishingly rare. They were common outcomes of the planetary formation process, natural products of the physics that builds worlds from spinning disks of gas and dust. This statistical result was perhaps Kepler's most profound legacy regarding habitable worlds. The mission found specific planets, gave them names and numbers and catalogue entries, measured their sizes and orbits and host star properties. But beyond these individual discoveries lay the statistical truth they revealed, the mathematical pattern hidden in thousands of data points that spoke to the abundance of small worlds throughout the cosmos. Even if none of Kepler's specific habitable zone candidates proved truly habitable, even if stellar flares or lack of atmospheres or unfavorable compositions made each one unsuitable for life as we understand it, the numbers suggested that habitable worlds existed somewhere. Perhaps many somewheres. Perhaps around stars not yet examined by any telescope. Perhaps around stars that would be surveyed by future instruments building upon Kepler's foundations. And so the catalogue of Goldilocks worlds grew throughout Kepler's mission, each new announcement adding another name to the list of possibilities, each discovery refining the statistical understanding of how common such worlds might be. The planets remained distant and unreachable, their surfaces unknown, their conditions uncertain. But their existence was no longer in doubt, and their abundance suggested that the universe was perhaps richer in potentially habitable real estate than earlier generations had dared to hope. The search continued, patient and unhurried, finding world after world in that narrow comfortable zone where temperatures might be just right for water to flow and pool and perhaps, in ways we cannot yet detect, to harbor the strange chemistry of life. When we gaze upon a star, we see only its outermost layer, that thin luminous surface from which light escapes and travels across the vastness of space to reach our instruments or our eyes. What lies beneath that surface, in the dense interior where nuclear fusion transforms hydrogen into helium and releases the energy that makes stars shine, remains hidden from direct observation. And yet, just as geologists learned to study the interior of our own planet by measuring how seismic waves travel through rock and metal, so too have astronomers developed methods to peer beneath stellar surfaces by observing how stars vibrate. This field of study is called Asteroseismology, and the Kepler Space Telescope transformed it from a promising but limited technique into one of the most powerful tools available for understanding the fundamental properties of stars throughout our galaxy. The principle underlying asteroseismology is elegantly simple, even if the mathematics required to interpret the observations grows quite complex. Stars are not static objects but rather spheres of hot gas held in a delicate balance between the inward pull of gravity and the outward pressure generated by the energy flowing from their cores. This balance is dynamic rather than fixed, and disturbances in the stellar interior can set up patterns of oscillation that cause the entire star to expand and contract in rhythmic patterns. These oscillations manifest as tiny changes in the star's brightness and in the wavelengths of light it emits, changes so subtle that detecting them requires instruments of extraordinary sensitivity and the patience to observe continuously over extended periods of time. Our own Sun exhibits these oscillations, and the study of solar oscillations, known as Asteroseismology, had been providing valuable insights into the Sun's interior structure for decades before Kepler launched. Scientists had discovered that the Sun rings like a bell, with millions of individual oscillation modes superimposed upon one another, each mode probing a different region of the solar interior. By carefully measuring the frequencies of these modes and comparing them to theoretical models, researchers could determine properties such as the depth of the convection zone, the rotation rate at various depths, and even the helium abundance in regions far beneath the visible surface. The success of Asteroseismology naturally raised the question of whether similar techniques could be applied to other stars. But the observational requirements were daunting. For the brightness variations caused by stellar oscillations are typically measured in parts per million, and detecting them requires continuous monitoring without the interruptions caused by daylight, weather, or atmospheric turbulence. Kepler was designed primarily to find planets by detecting the slight dimming that occurs when a planet passes in front of its host star, but the same capabilities that made it an effective planet hunter also made it an ideal instrument for asteroseismology. The telescope's photometric precision, achieved through its large mirror, sensitive detectors, and position in deep space far from Earth's atmosphere, allowed it to measure brightness variations at the level of a few parts per million over timescales ranging from minutes to years. Its continuous monitoring of the same field of stars, without the interruptions that plague ground-based observatories, provided the unbroken time series data that asteroseismology requires. And its simultaneous observation of more than 150,000 stars meant that even though asteroseismology was not the primary mission objective, Kepler could still observe thousands of potential targets while carrying out its planet search. The Kepler Asteroseismic Science Consortium, an international collaboration involving researchers from dozens of institutions, had been preparing for the mission's launch for years, developing the theoretical tools and analysis software needed to extract asteroseismic information from the expected flood of data. When the observations began arriving, the results exceeded even the most optimistic expectations. Solar-like oscillations, the same type of pressure-driven pulsations observed in our Sun, were detected in thousands of stars across the Kepler field. Red giants, evolved stars that have exhausted the hydrogen fuel in their cores and expanded to many times their original size, proved particularly amenable to asteroseismic study because their oscillation periods are longer and their amplitudes slightly larger than those of main sequence stars like the Sun, making the signals easier to detect and analyze. The ability to detect these oscillations in such large numbers of stars opened new avenues of investigation that would have seemed impossible just a few years earlier. Each star's oscillation pattern encodes information about its mass, radius, age, and internal structure, properties that are otherwise very difficult to measure for stars other than the Sun. Traditional methods of determining stellar masses typically require the star to be part of a binary system, where orbital dynamics can be used to weigh the components, or rely on comparisons with theoretical models that carry significant uncertainties. Stellar ages are even more challenging to determine, for stars change slowly over their main sequence lifetimes, and distinguishing a star that is 2 billion years old from one that is 4 billion years old often proves impractical with conventional techniques. Asteroseismology provided a way around these limitations, offering mass estimates accurate to a few percent and age estimates that, while still carrying considerable uncertainty, were far more reliable than those obtained through other methods. The researchers who developed the analysis pipelines for processing Kepler's asteroseismic data deserve particular recognition for their contributions, even though their work involved years of painstaking effort that may seem less dramatic than the discoveries their tools enabled. Daniel Hubber, working initially at the University of Sydney and later at the Institute for Astronomy in Hawaii, was instrumental in developing automated methods for measuring oscillation frequencies in large samples of stars and for deriving stellar properties from those measurements. His work helped transform asteroseismology from an artisanal craft, in which each star required individual attention from expert analysts, into a systematic science capable of characterizing populations of thousands of stars with consistent methods. Travis Metcalfe contributed essential advances in stellar modeling, developing grid-based approaches that could rapidly compare observed oscillation frequencies to theoretical predictions and identify the stellar parameters that best reproduced the data. These pipelines processed the observations of star after star, building up catalogues of stellar properties that would serve as fundamental references for subsequent investigations. One of the more unexpected discoveries to emerge from Kepler's asteroseismic observations concerned the internal rotation of red giant stars. Theory had predicted that as a star evolves off the main sequence and its core contracts while its envelope expands, the core should spin up dramatically, much as a spinning figure skater accelerates by pulling in their arms. The convective envelope, meanwhile, should slow its rotation as it expands, leading to a situation in which the deep interior of the star rotates much faster than its surface. Observations of the Sun had already demonstrated that differential rotation occurs in stellar interiors, with the solar equator rotating faster than the poles and with subtle variations in rotation rate at different depths. But probing the rotation of stellar cores remained beyond reach until Kepler provided data of sufficient quality and duration. The breakthrough came through the detection of mixed modes, a particular type of oscillation that behaves like a pressure wave in the outer layers of the star but transitions to a gravity wave in the deep interior. These mixed modes sample both the envelope and the core of the star, and their frequencies carry information about conditions in both regions. By analyzing the subtle patterns in the mixed-mode frequencies of red giants observed by Kepler, researchers confirmed that the cores of these stars do indeed rotate faster than their surfaces, but with an important caveat. The cores were spinning faster, yes, but not nearly as fast as theoretical models had predicted. Something was extracting angular momentum from the cores and transporting it outward, slowing the rotation far more efficiently than standard models could explain. The physical mechanism responsible for this angular momentum transport remains an active area of research, with magnetic fields and internal gravity waves among the proposed explanations. But the observational constraints provided by Kepler have transformed what was once a purely theoretical question into an empirical puzzle with real data to guide the investigation. Among the many curious objects that emerged from Kepler's observations was a class of binary star systems that came to be known informally as heartbeat stars. These systems consist of two stars in highly elliptical orbits around their common center of mass, arranged so that the orbital plane lies along or nearly along our line of sight. As the stars approach each other at the closest point in their orbit, gravitational tidal forces distort their shapes, stretching them from spherical into elongated configurations. This distortion changes the area of stellar surface visible to us, causing the brightness of the system to vary in a characteristic pattern that resembles, when plotted on a graph, the trace of a heartbeat on a medical monitor. The initial rise corresponds to the stars approaching each other, the sharp peak to their closest approach, and the gradual decline to their separation as they swing around to the far reaches of their orbits. These heartbeat stars were not entirely unknown before Kepler, but the mission revealed them in far greater numbers and diversity than had been anticipated. More than 170 such systems were identified in the Kepler data, spanning a wide range of orbital periods and stellar types. Many of these systems also exhibited tidally induced oscillations, stellar pulsations excited by the periodic gravitational squeezing that occurs near closest approach. The study of these oscillations provided yet another window into stellar interiors, one that offered complementary information to the solar-like oscillations studied in single stars and in less eccentric binaries. Not all of Kepler's asteroseismic targets yielded results that conformed to expectations, and in some cases the deviations from predicted behavior led to significant discoveries in their own right. The star catalogued as KIC 846-2852, which would later become famous under the informal name Tabby's star after the astronomer Tabitha Boyajian, who led the effort to understand its behavior, first attracted attention as a potential target for asteroseismology before its more dramatic peculiarities became apparent. The star is a main sequence F-type star, somewhat larger and hotter than our Sun, and it was included among the targets being evaluated for asteroseismic study in the early months of the mission, when researchers examined its light curve. However, they discovered something entirely unexpected: a series of deep, irregular dips in brightness unlike anything seen in other Kepler targets. These dips blocked up to 20% of the star's light, far too much to be explained by a transiting planet, and their irregular timing and depth defied easy explanation. The mystery of Tabby's star consumed considerable attention from researchers and the public alike, with proposed explanations ranging from swarms of comets to alien megastructures. The eventual consensus pointed toward clouds of dust, perhaps produced by the breakup of a family of comets or a disintegrating asteroid, as the most likely cause of the dimming events. What bears noting in the context of asteroseismology, however, is how the star's initial selection as an asteroseismic target demonstrates the interconnected nature of stellar astrophysics. The same observations that might have revealed the internal structure of this particular star instead revealed an external phenomenon of a completely different character. A reminder that the universe does not always conform to our categories and that comprehensive monitoring of stars often yields surprises that no one anticipated. The characterization of stellar properties through asteroseismology had important implications for the interpretation of planetary discoveries as well. When a planet transits its host star, the depth of the transit tells us the ratio of the planet's radius to the star's radius, not the absolute size of the planet itself. To determine how large a planet actually is, we must know the size of its host star with reasonable accuracy. Early in the Kepler mission, stellar radii were estimated primarily through spectroscopic observations and comparisons with theoretical models, methods that sometimes produced significant errors. Asteroseismic measurements offered a more direct and reliable way to determine stellar radii, and when researchers applied these measurements to Kepler host stars, they discovered that some of the stellar classifications in the original input catalogue had been incorrect. Stars that had been classified as Sun-like dwarfs were in some cases revealed to be larger evolved stars, and planets whose radii had been estimated assuming a smaller host star turned out to be proportionally larger than initially reported. This recalibration affected the statistics of the planetary population in modest but meaningful ways, illustrating how our understanding of planets depends fundamentally on our understanding of the stars they orbit. Over the course of the mission, more than 500 solar-like oscillators were characterized with unprecedented precision, each one providing detailed information about its mass, radius, density, and evolutionary state. This sample, though small compared to the total number of stars monitored by Kepler, represented an enormous advance over what had been possible before. The stars spanned a range of ages and compositions, allowing researchers to trace how stellar properties vary across different populations within our galaxy. Some of the characterized stars were hosts to confirmed or candidate planets, enabling studies of how planet occurrence rates depend on stellar mass and age. Others were members of stellar clusters, groups of stars known to share a common origin and age, providing crucial tests of how well asteroseismic age estimates agreed with ages derived through independent methods. The legacy of Kepler's asteroseismic observations extends far beyond the individual discoveries made during the mission's active lifetime. The data itself, preserved in public archives and analyzed with ever-improving techniques, continues to yield new insights years after the telescope ceased operations. New theoretical models, new analysis methods, and new scientific questions lead researchers back to the Kepler observations again and again, extracting information that was always present in the data but waiting for the right approach to reveal it. The stellar ages determined through asteroseismology contribute to our understanding of galactic archaeology, the effort to reconstruct the history of the Milky Way by studying the ages and chemical compositions of stars throughout the galaxy. The characterization of stellar interiors informs models of stellar evolution that apply not just to the specific stars observed by Kepler but to stars throughout the universe. The transformation of asteroseismology from a niche specialty into a mainstream astrophysical tool stands as one of Kepler's quieter but more profound legacies. Before the mission, the technique had been applied in detail to only a handful of stars, the Sun, and a few others bright enough or unusual enough to warrant the intensive observations required. After Kepler, the technique could be applied to thousands of stars simultaneously, turning what had been a collection of individual case studies into a statistical science capable of addressing questions about stellar populations on galactic scales. The steady, patient accumulation of stellar oscillation data, photon by photon, orbit by orbit, year by year, revealed the hidden interiors of distant suns and demonstrated once again that sustained observation often proves more valuable than any single dramatic discovery. The stars pulse with rhythms that encode their deepest secrets, and Kepler listened long enough to decode what many of them had to say. In the month of December in the year 2010, while the Kepler Space Telescope continued its patient vigil over 150,000 distant stars, a new kind of observer joined the search for other worlds. These observers were not professional astronomers, nor did they possess advanced degrees in astrophysics or planetary science. They were ordinary people, sitting in their homes, looking at their computer screens, and they would come to discover extraordinary things that the most sophisticated algorithms had somehow overlooked. The project was called Planet Hunters, and it was built upon a simple but profound observation about the nature of human perception, which is that our brains, shaped by millions of years of evolution to recognize patterns in the world around us, possess certain capabilities that remain remarkably difficult to replicate in even the most carefully designed computer programs. The Planet Hunters project emerged through an organization called Zooniverse, which had pioneered the concept of citizen science on a large scale, inviting members of the public to contribute their time and attention to genuine scientific research. The idea was elegantly straightforward in its conception. Kepler was transmitting vast quantities of light-curve data back to Earth, showing how the brightness of each star varied over time, and while computer algorithms could process this data with impressive speed, searching for the telltale dips that might indicate a planet crossing in front of its host star, there remained a significant number of signals that fell into uncertain categories, neither clearly planetary nor clearly spurious, and these ambiguous cases accumulated in their thousands as the mission progressed. Human pattern recognition operates in ways that differ fundamentally from the methods employed by automated transit detection software. When a computer algorithm searches through Kepler data, it typically looks for periodic signals, expecting that if a planet exists, it will cross in front of its star at regular intervals, producing multiple identical dips in the light curve that can be stacked and averaged to confirm the detection. This approach works remarkably well for planets with short orbital periods, those that complete their journeys around their stars in a matter of days or weeks, because during the course of Kepler's observations, such planets would transit many times, creating a repeating pattern that algorithms could readily identify. But for planets with longer orbital periods, those taking months or even years to complete a single orbit, the situation becomes considerably more challenging. A planet with an orbital period of 300 days, for instance, might transit only 3 or 4 times during the entire span of Kepler's primary mission, and if even one of those transits happened to coincide with a gap in the data, perhaps during one of the quarterly spacecraft rolls when Kepler adjusted its orientation, the remaining transits might be too few in number to trigger an automated detection. Worse still, a planet with an orbital period longer than the observation window would produce only a single transit, a solitary dimming event that computer algorithms were generally programmed to discard, since a single dip could so easily be caused by instrumental effects or stellar variability rather than a genuine planetary crossing. This is where human observers demonstrated an unexpected advantage. When a person looks at a light curve, they do not simply search for periodic signals matching a mathematical template. Instead, they perceive the overall character of the data, noticing subtle variations in shape and depth that might distinguish a genuine transit from instrumental noise, recognizing patterns that feel somehow planetary even when they occur only once or twice in the entire dataset. The human brain, it turns out, is remarkably adept at detecting the sort of smooth, symmetrical dimming caused by a spherical planet crossing a stellar disk, and at distinguishing this characteristic shape from the jagged, irregular fluctuations caused by detector glitches or cosmic ray impacts. The Planet Hunters interface presented volunteers with light curve segments, each showing approximately 30 days of brightness measurements for a particular star, and asked them simply to mark any features that looked like potential transits. The volunteers required no special training beyond a brief tutorial explaining what transit signals typically looked like, and no expertise beyond the pattern recognition capabilities that every human brain possesses as standard equipment. Each light curve segment was examined by multiple independent volunteers, and when several people marked the same feature as a potential transit, that star was flagged for further investigation by the scientific team. By the end of Kepler's mission, more than 300,000 people had registered to participate in Planet Hunters, contributing millions of individual classifications and examining light curves from stars scattered across the Kepler field of view. These volunteers came from all walks of life and from countries around the world, united only by their curiosity about distant planetary systems and their willingness to spend some portion of their free time staring at graphs of stellar brightness. Some participated casually, classifying a handful of light curves during a lunch break or a quiet evening, while others became deeply invested in the search, returning day after day to examine new data and discuss interesting candidates with fellow volunteers in the project's online forums. It was in these forums that some of the most significant discoveries began to take shape, as volunteers shared unusual light curves they had encountered and debated whether particular features might represent genuine planetary transits or some other phenomenon entirely. The scientific team at Yale University, led by Professor Deborah Fisher, worked closely with the volunteer community, providing guidance and feedback while also paying careful attention to the candidates that volunteers found most compelling. Professor Fisher had spent her career studying extrasolar planets and understood better than most that the search for other worlds benefits enormously from fresh perspectives and diverse approaches. And she recognized early on that the Planet Hunters volunteers were not merely providing additional processing capacity, but were bringing genuinely different capabilities to bear on the data. In the year 2012, two volunteers named Kian Jack and Robert Gagliano noticed something peculiar in the light curve of a star that had not previously attracted significant attention from the automated detection pipelines. Kian Jack was examining data through the Planet Hunters interface when he encountered a pattern that seemed difficult to explain through any simple mechanism. A complex series of brightness variations that suggested something unusual was occurring in this particular stellar system. He flagged the star for discussion, and Robert Gagliano, another dedicated volunteer, joined in the effort to understand what they were seeing. Together, and in consultation with the scientific team, they gradually pieced together an explanation that was far stranger than anyone had initially imagined. The star in question was not a single star at all, but rather a pair of stars orbiting around their common center of mass, what astronomers call a binary system. This in itself was not unusual, since binary stars are actually quite common throughout the galaxy. But the dimming patterns in the light curve indicated that a planet was orbiting this binary pair, tracing a wide path around both stars simultaneously rather than circling just one of them. Such arrangements are called circumbinary planets, and they had only recently been confirmed to exist at all, with Kepler having detected the first definitive examples just the year before. Finding such a planet through citizen science was remarkable enough, but further analysis revealed that the situation was even more extraordinary than a simple circumbinary orbit. The system, which would eventually receive the catalogue designation Kepler 64, but was informally known as PH1b in honor of its discovery through Planet Hunters, turned out to exist within a four-star system, one of the most complex stellar environments in which a planet had ever been found. The planet orbits a pair of stars that are themselves gravitationally bound to a second pair of stars located somewhat farther away, creating a hierarchical arrangement of stellar companions that would produce a constantly changing pattern of sunrises and sunsets for any observer on the planet's surface, though the planet itself is a gas giant inhospitable to any familiar form of life. The discovery of PH1b demonstrated conclusively that citizen scientists could make genuine contributions to astronomical research, finding objects that professional astronomers and their computer algorithms had overlooked. Kian Jack and Robert Gagliano were not merely acknowledged in the announcement of the discovery, but were included as co-authors on the scientific paper describing the planet, their names appearing alongside those of professional astronomers in the peer-reviewed astronomical literature. This was a significant recognition of the substantive intellectual contribution that citizen scientists could make, going well beyond simple data processing to encompass the creative pattern recognition and careful analysis that lies at the heart of scientific discovery. The validation of Planet Hunters candidates required rigorous scientific scrutiny, and Professor Deborah Fisher oversaw this process with meticulous care. When volunteers identified a promising candidate, the scientific team would examine the original Kepler data in detail, looking for any signs that the observed dimming might be caused by something other than a transiting planet. They would check for background stars that might be contaminating the measurements, search for secondary eclipses that might indicate a binary star system rather than a planetary companion, and analyze the precise shape of the transit to ensure it matched theoretical predictions for a planet crossing a stellar disk. Candidates that survived this initial scrutiny would then be subjected to ground-based follow-up observations, using telescopes equipped with high-resolution spectrographs to measure the gravitational wobble of the host star and confirm the presence of a planetary companion. This validation process was essential for maintaining the scientific credibility of citizen science discoveries. ensuring that candidates announced as genuine planets had been subjected to the same rigorous standards applied to discoveries made through any other method. Professor Fisher and her colleagues understood that the long-term success of citizen science depended on demonstrating that volunteers could identify candidates of genuine scientific significance, and they invested considerable effort in ensuring that every confirmed Planet Hunters discovery met the highest standards of astronomical evidence. In the year 2013, the Planet Hunters project announced another significant discovery: a planet designated PH2b that orbited within the habitable zone of its host star. The habitable zone, sometimes called the Goldilocks zone, is the region around a star where temperatures are moderate enough to allow liquid water to exist on a planet's surface, neither so hot that water would boil away nor so cold that it would freeze permanently into ice. PH2b was a large planet, roughly the size of Jupiter, and as a gas giant it was unlikely to possess a solid surface where liquid water might pool and collect. But the discovery demonstrated that citizen scientists could identify planets in scientifically interesting regions of stellar systems, including the zones where conditions might potentially be suitable for life. The habitable zone candidates identified by Planet Hunters were particularly valuable precisely because they tended to have longer orbital periods, requiring more time to complete each journey around their host stars. And these longer-period planets were exactly the ones that automated detection algorithms often struggled to identify. A planet orbiting at Earth-like distances from a Sun-like star would transit only once per year, and over the course of Kepler's primary mission, such a planet might produce only 3 or 4 observable transits, too few for many computer algorithms to detect with confidence. Human observers, examining the data with different expectations and different pattern recognition strategies, proved remarkably capable of identifying these elusive long-period candidates, effectively extending the reach of the Kepler mission toward the more distant regions of stellar systems. The scientific papers describing Planet Hunters' discoveries were published in respected peer-reviewed journals, including the monthly notices of the Royal Astronomical Society, one of the oldest and most prestigious astronomical publications in the world. These papers followed all the conventions of professional astronomical literature, presenting detailed analyses of the light curve data, describing the follow-up observations used to validate each candidate, and placing the discoveries in the broader context of what was known about planetary system architecture. What made them unusual was the author list, which included not only the professional astronomers who had led the scientific analysis, but also the citizen science volunteers whose initial identifications had brought these particular stars to the attention of the research team. The inclusion of volunteers as co-authors on peer-reviewed papers represented a meaningful acknowledgement of the intellectual contribution that citizen scientists make to astronomical research. It was not simply a matter of volunteers providing labor, examining light curves so that professional astronomers did not have to, but of volunteers exercising genuine scientific judgment, recognizing patterns that others had missed, and identifying candidates that would ultimately prove to be confirmed planets. The decision to include volunteers as co-authors reflected a recognition that the boundary between professional and amateur science is less sharp than it might sometimes appear, and that important contributions can come from unexpected sources. The educational impact of Planet Hunters extended well beyond the specific discoveries made through the project. Hundreds of thousands of people gained direct experience with authentic astronomical data, learning to recognize the signatures of planetary transits and understanding firsthand the challenges involved in distinguishing genuine signals from instrumental artifacts. For many participants, Planet Hunters provided their first glimpse into the actual practice of scientific research, showing them that science proceeds not through sudden flashes of insight but through patient, careful examination of data, looking for patterns that might easily be overlooked by anyone not paying close attention. The project also demonstrated that meaningful scientific participation is available to anyone with curiosity and a willingness to contribute, regardless of formal credentials or professional training. The volunteers who discovered PH1b were not professional astronomers, but their discovery was no less significant for that reason, and their names appeared in the scientific literature alongside those of researchers who had spent decades studying extrasolar planets. This democratization of scientific participation represents one of the most significant legacies of the citizen science movement, showing that the boundaries of the scientific community can be extended to include anyone willing to engage seriously with scientific questions. For the Kepler mission specifically, Planet Hunters provided a valuable complement to automated data analysis, extending the sensitivity of the survey toward precisely the kind of planets that were most difficult for computers to detect. The long-period planets, the single transit candidates, the complex systems with multiple overlapping signals, all of these fell more readily within the grasp of human pattern recognition than within the capabilities of standard transit detection algorithms. As the Kepler data archive continues to be analyzed and reanalyzed with ever more sophisticated techniques, the contributions of citizen scientists remain woven into the fabric of what we have learned about planetary systems beyond our own. The collaboration between professional astronomers and citizen science volunteers also modeled a different kind of relationship between science and the public, one based on active participation rather than passive consumption of scientific findings. Rather than simply reading about discoveries made by others, Planet Hunters volunteers became part of the discovery process itself, contributing their time and attention and pattern recognition abilities to the shared endeavor of understanding the universe. This participatory model of science engagement has since been extended to many other areas of research, from galaxy classification to wildlife monitoring to the analysis of historical documents, creating ongoing opportunities for public involvement in authentic scientific work. Professor Fisher and her colleagues at Yale continued to refine the Planet Hunters methodology throughout the Kepler mission, developing improved interfaces and better methods for combining volunteer classifications into scientific candidate lists. They published careful studies examining the performance of citizen scientists relative to automated algorithms, demonstrating quantitatively the advantages that human observers brought to certain categories of detection challenges. These meta-analyses of the citizen science process itself contributed to the broader understanding of how human and machine intelligence can be combined effectively, with each compensating for the limitations of the other. As the Kepler primary mission concluded and transitioned into the extended K2 mission, Planet Hunters adapted accordingly, presenting volunteers with data from new fields of stars and continuing to identify interesting candidates for professional follow-up. The community that had formed around the project remained active and engaged, with experienced volunteers helping newcomers understand the subtleties of light curve analysis and discussing interesting candidates in ongoing online conversations. The sense of shared purpose that animated these discussions reflected something important about human motivation, which is that people genuinely want to contribute to meaningful endeavors, and that given the opportunity to participate in authentic scientific research, many will embrace that opportunity with enthusiasm and dedication. The stars that Kepler observed remain available for study, their light curves archived and accessible to anyone who wishes to examine them. The contributions of the hundreds of thousands of Planet Hunters volunteers are preserved in those archives as well, their classifications and discussions forming a permanent record of citizen science engagement with one of the most significant astronomical surveys ever conducted. And somewhere in those archives, waiting perhaps to be noticed by some future observer, there may remain planets not yet discovered, their transit signals present in the data but not yet recognized, patient as always for the careful eye that will finally perceive them. When we speak of finding planets around distant stars, we must also speak of the things that pretend to be planets but are not, and this quieter side of the Kepler mission occupied as much time and careful thought as the discoveries themselves. For every genuine world that Kepler revealed, there were many signals that mimicked the appearance of a transiting planet, dipping the light of a star in patterns that seemed, at first glance, to match what we might expect from a small rocky body passing before its sun. The challenge of separating the real from the false became one of the most painstaking aspects of the entire endeavor, requiring the development of new software, new statistical methods, and years of follow-up observations using some of the most powerful telescopes on Earth. In the early years of the mission, the Kepler team came to understand that more than 90% of the initial candidates flagged by the spacecraft would require some form of additional validation before they could be called confirmed planets. This is a remarkable number when one pauses to consider it, suggesting that for every 10 promising signals, 9 of them needed further scrutiny to determine whether they were genuine or merely imposters wearing the guise of distant worlds. The universe, it seems, is full of phenomena that can fool even the most sensitive instruments, and the careful work of eliminating these false positives became as essential to the mission as the original observations themselves. The most common source of confusion came from eclipsing binary stars, which are pairs of stars locked in orbit around one another, periodically passing in front of each other as seen from our vantage point. When one star in such a pair crosses before its companion, the total light we receive from the system decreases, and if the geometry happens to be favorable, this decrease can look remarkably similar to what we would expect from a planet transiting a single star. The depth of the dimming, the duration of the event, and even the shape of the light curve can all conspire to create a signal that appears planetary in nature. Eclipsing binaries were the primary contaminants in the Kepler data, accounting for a substantial fraction of the false positive signals that the team encountered throughout the mission. The situation was made more complicated by the nature of Kepler's observations, for the spacecraft was designed to monitor a very large field of view containing hundreds of thousands of stars simultaneously. Each pixel on the detector received light from a small patch of sky, and in crowded regions of the field, the light from multiple stars could fall upon the same pixel or group of pixels. This phenomenon, known as blending, meant that a faint eclipsing binary in the background could contribute its periodic dimming to the light curve of a brighter foreground star, creating the appearance of a planetary transit where none existed. The foreground star would seem to host a planet, but the true source of the signal would be a completely different stellar system lying far behind it, unresolved and invisible as a separate object. These blended signals were particularly troublesome because they could not always be identified through examination of the light curve alone. The dimming might have exactly the right depth and duration to suggest a planet of a particular size, and without additional information, there would be no way to know that the signal originated from a background source rather than from the target star itself. The Kepler team realized early on that they would need to develop sophisticated methods to distinguish between genuine planetary transits and these various forms of contamination, and this led to the creation of several innovative software tools and analytical techniques. One of the most significant developments in this area was a statistical validation technique called Blender, which was developed by Guillermo Torres and his colleagues at the Harvard-Smithsonian Center for Astrophysics. The name itself hints at the problem it was designed to address. Blender was created to evaluate the probability that an observed signal might arise from a blended background source rather than from a true planetary companion. The software worked by simulating vast numbers of possible false-positive scenarios, including eclipsing binaries at various distances, companion stars of different brightnesses, and various geometric configurations that might produce the observed light curve. By comparing these simulated scenarios against the actual observations, Blender could calculate the likelihood that the signal was genuine versus the likelihood that it arose from one of the many possible false positive sources. The method was computationally intensive, requiring careful modeling of the stellar populations in the Kepler field and detailed consideration of the instrument's optical properties. Torres and his team applied Blender to many of the most interesting Kepler candidates, including several that would go on to be confirmed as genuine planets. The technique proved particularly valuable for validating small planets in the habitable zones of their stars, where the signals were often faint and the scientific stakes were highest. By demonstrating that the probability of a false positive was acceptably low, Blender allowed astronomers to claim planetary discoveries even in cases where traditional confirmation methods were not feasible. As the number of Kepler candidates grew into the thousands, it became clear that analyzing each one individually with a tool like Blender would be impractical. The mission needed a way to validate planets in bulk, processing large numbers of candidates simultaneously while still maintaining rigorous statistical standards. This need was addressed by Timothy Morton, who developed a validation software package called VESPA, a name derived from the phrase validation of exoplanet signals using a probabilistic algorithm. The VESPA software built upon the principles established by Blender but was designed to operate much more efficiently, allowing astronomers to assess hundreds or thousands of candidates in the time it would have taken to analyze just a handful using earlier methods. Morton's approach relied on calculating the false positive probability for each candidate by considering all the ways in which a non-planetary signal might produce the observed data. The software took into account the properties of the target star, the characteristics of the transit signal, and the statistical likelihood of various false positive scenarios occurring by chance. When the false positive probability fell below a certain threshold, typically set at 1%, the candidate could be considered validated as a genuine planet. This did not mean absolute certainty, for science rarely deals in absolutes, but it meant that the odds of error were acceptably small for the purposes of building a reliable catalogue of planetary systems. The development of VESPA represented a significant advance in the study of exoplanets, enabling the Kepler team to confirm large batches of planets in single announcements rather than the one-by-one approach that had characterized earlier efforts. The software became widely used throughout the astronomical community and was applied not only to Kepler data but also to observations from other missions and ground-based surveys. Morton's contribution to the field was substantial, and the VESPA validation framework remains an important tool in the ongoing search for worlds beyond our solar system. While statistical validation techniques could handle many candidates, some signals required more direct forms of investigation. Radial velocity follow-up campaigns provided one such approach, using ground-based telescopes to measure the tiny wobble that a planet induces in its host star as the two bodies orbit their common center of mass. Instruments such as the high-resolution Eshel spectrometer at the W.M. Keck Observatory in Hawaii and the HARP spectrograph at the European Southern Observatory in Chile were employed to observe promising Kepler candidates, searching for the telltale Doppler shifts that would confirm the presence of a planetary companion. These observations required considerable telescope time and were most effective for larger planets around brighter stars, where the stellar wobble was strong enough to be detected with current technology. For smaller planets and fainter stars, the radial velocity signal was often too weak to measure, and astronomers had to rely on other validation methods instead. Another important technique involved speckle imaging, a method that uses very short exposures to freeze out the blurring effects of Earth's atmosphere and reveal fine details in the vicinity of a target star. By observing Kepler candidates with speckle imaging systems, astronomers could search for nearby companion stars that might be responsible for false positive signals. If a second star was found very close to the target, within the same Kepler pixel, then the observed transit signal might actually belong to this companion rather than to the primary star. Ruling out such nearby sources was an essential step in validating many Kepler discoveries, and speckle imaging campaigns were conducted at several observatories including the Gemini telescopes and the WIYN observatory at Kitt Peak. As the Kepler mission matured, the software pipelines used to process the data underwent continuous refinement. The development known as KPOP, which stood for Kepler Pipeline of Pipelines, represented an effort to integrate and optimize the various algorithms used to detect and characterize transit signals. This work involved testing different approaches to signal detection, comparing their performance on both real data and simulated observations, and combining their strengths to create a more robust and reliable overall system. The goal was to maximize the number of genuine planets detected while minimizing the number of false positives that slipped through, and the ongoing improvements to the pipeline contributed to the steady growth of the Kepler catalog over the years. Among the many candidates that required extensive validation, one notable example was the signal designated KOI 456.01. where KOI stands for Kepler Object of Interest. This candidate orbited a star known as Kepler 160, a G-type star similar to our own Sun, and the signal suggested a planet approximately twice the size of Earth in an orbit that might place it within the habitable zone. The prospect of such a world naturally attracted considerable attention, but confirming its planetary nature proved challenging. The validation process for KOI 456.01 required careful analysis to rule out the various false positive scenarios that might explain the observed data, and the candidate remained in a somewhat uncertain status for an extended period. The case illustrated how even the most promising signals could resist easy confirmation, demanding patience and thoroughness from the scientific team. A particularly elegant solution to the false positive problem emerged from a simple statistical insight concerning systems with multiple transiting candidates. If a single star showed evidence of two or more transiting bodies, the probability that all of these signals were false positives dropped dramatically. While any one signal might be explained by an eclipsing binary or a blended background source, it would be extraordinarily unlikely for two or three or more such impostors to conspire to create multiple fake signals around the same star. This principle, known as verification by multiplicity, allowed astronomers to confirm planets in multi-candidate systems with high confidence, even without additional follow-up observations. The power of this approach was demonstrated in a remarkable announcement made in February of 2014, when the Kepler team confirmed the existence of 715 new planets in a single release. These planets resided in 305 stellar systems, each of which hosted multiple transiting candidates. By applying the verification by multiplicity argument, The team was able to show that the false positive probability for these candidates was extremely low, allowing them to be promoted from candidates to confirmed planets in one sweeping announcement. This represented the largest single increase in the number of known exoplanets at that time and demonstrated how statistical reasoning could serve as a powerful tool for planetary validation. The February 2014 announcement also had implications for our understanding of planetary architectures, as the confirmed systems revealed a population of compact multi-planet systems that seemed to be common throughout the galaxy. Many of these systems contained planets of similar sizes orbiting in resonant or near-resonant configurations, suggesting orderly formation and evolution processes. The ability to confirm large numbers of planets simultaneously through multiplicity arguments opened new avenues for studying these systems as ensembles rather than as isolated discoveries. Over the course of the mission, the Kepler team's understanding of the false positive rate underwent substantial refinement. Early estimates suggested that perhaps 40% of Kepler candidates might turn out to be false positives, a figure that would have significantly undermined the reliability of the catalogue. However, as validation techniques improved and more candidates were carefully scrutinized, this estimate was revised steadily downward. By the later stages of the mission, the false positive rate was understood to be closer to 10% for most categories of candidates, and even lower for multi-planet systems and other subsets where additional constraints could be applied. This improvement in the false positive rate reflected not only advances in validation methodology but also better understanding of the astrophysical sources of contamination. The Kepler team developed increasingly sophisticated models of the eclipsing binary population, the distribution of background stars, and the optical properties of the spacecraft itself. Each refinement allowed for more accurate assessment of false positive probabilities and greater confidence in the growing catalogue of confirmed planets. The work of eliminating false positives, while less celebrated than the discoveries themselves, was fundamental to the scientific legacy of the Kepler mission. Without rigorous validation, the catalogue of Kepler planets would have been contaminated with an unknown number of impostors, undermining any statistical conclusions drawn from the data. The development of tools like Blender and Vespa, the patient campaigns of radial velocity and imaging follow-up, and the clever application of statistical arguments like verification by multiplicity all contributed to a final catalogue that astronomers could trust and use with confidence. In the quiet work of validation, we see something of the true nature of scientific progress, which often proceeds not through dramatic revelations but through the careful, methodical elimination of alternatives. The astronomers who developed these techniques understood that finding planets was only the beginning, and that knowing which signals to believe required just as much ingenuity and persistence as detecting them in the first place. The art of eliminating false positives, practiced across many years and involving many researchers around the world, ensured that when we speak of the planets discovered by Kepler, we speak of worlds whose existence has been tested against the many ways the universe might deceive us, and found to be real. And so we come now to a quieter chapter in our story, though one touched by a certain kind of loss, the kind that comes when a machine that has served faithfully begins to show the signs of its long labors. We have spoken at length about the instruments aboard Kepler, about the photometer and the charge-coupled devices and the software that sifted through the light of distant suns, but we have not yet given proper attention to the humble reaction wheels, those spinning mechanical devices tucked away inside the spacecraft, doing their work in silence, day after day, year after year, holding Kepler steady against the gentle but persistent forces that sought to turn it from its appointed gaze. It is these reaction wheels that we must now consider, for it was their gradual failure that brought the primary mission to its close. And it is in understanding this failure that we come to appreciate both the fragility and the remarkable resilience of the machines we send into the void. A reaction wheel, you see, is a rather elegant solution to a fundamental problem of spaceflight. When a spacecraft is drifting through the emptiness between worlds, there is nothing to push against. No air, no water, no solid ground, and yet the spacecraft must still be able to turn itself, to point its instruments in one direction or another, to maintain a precise orientation despite the small disturbances that accumulate over time. The solution, worked out by engineers many decades ago, relies on a principle that Isaac Newton would have recognized immediately. The principle that for every action there is an equal and opposite reaction. If you spin a heavy wheel in one direction inside the spacecraft itself will rotate ever so slightly in the opposite direction. And by carefully controlling the speed of the wheel, you can control the rate and direction of that rotation. It is rather like the way a figure skater can change their spin by extending or drawing in their arms. Except that in this case the spinning mass is separate from the body of the spacecraft, and its rotation can be precisely commanded by the onboard computers. Kepler carried 4 of these reaction wheels when it launched, each one mounted along a different axis, and together they allowed the spacecraft to control its orientation in all 3 dimensions of space, to pitch and yaw and roll as needed to keep its telescope pointed at that single patch of sky in the constellations Cygnus and Lyra. For wheels might seem excessive when only 3 dimensions need controlling, and indeed 3 wheels would have been sufficient for normal operations. But the 4th wheel was included as a spare, a precaution against the possibility that one of the wheels might fail during the course of the mission. This kind of redundancy is common in spacecraft design, a recognition that machines operating in the harsh environment of space, far beyond the reach of any repair crew, must be built with extra margins of safety. The designers of Kepler hoped that all 4 wheels would continue working throughout the mission, but they planned for the eventuality that one might not. The reaction wheels aboard Kepler were relatively small devices, each one massing only a few kilograms, but they spun at tremendous speeds, thousands of revolutions per minute, and they did so continuously, year after year, adjusting their speeds by tiny increments to keep the telescope pointed with the extraordinary precision that the science demanded. The bearings inside these wheels, the surfaces where metal meets metal and friction must be minimized, were subjected to stresses that accumulated with each rotation, and though they were designed to last for the duration of the mission and beyond, the reality of mechanical systems is that wear is inevitable, that microscopic imperfections grow over time, that the lubricants meant to ease the friction slowly degrade in the radiation environment of space. It was only a matter of time before these stresses began to manifest as problems. The first sign of trouble came on July 14, 2012, when reaction wheel number 2 began to show elevated levels of friction. The telemetry sent back to Earth revealed that the wheel was struggling, requiring more torque than usual to maintain its commanded speed, and the engineers at Ball Aerospace and at NASA's Ames Research Center, who monitored Kepler's health with careful attention, recognized immediately that something was wrong. They attempted various measures to address the problem, including periods of rest for the affected wheel and changes in its operating parameters, but the friction continued to increase, and within a short time it became clear that wheel number 2 could no longer be relied upon. It was, in the parlance of spacecraft engineers, failed, and though Kepler could continue to operate with 3 wheels, The margin of safety that the fourth wheel had provided was now gone. The mission continued, but with a new awareness of vulnerability, a recognition that the loss of one more wheel would bring the primary mission to an end. For nearly a year, the 3 remaining wheels held steady, and Kepler continued to gather its precious data, adding to the growing catalogue of planetary candidates, refining the estimates of how common Earth-sized worlds might be. But on May 11, 2013, the telemetry from Kepler brought unwelcome news. Reaction wheel number 4 had begun to exhibit the same symptoms that had preceded the failure of wheel number 2. Elevated friction, difficulty maintaining commanded speeds, and within hours it became clear that this wheel too had failed. With only 2 working reaction wheels remaining, Kepler could no longer maintain the precise 3-axis stabilization that its scientific observations required. The spacecraft could still turn, could still point itself in different directions, but it could no longer hold itself steady enough to detect the tiny dips in starlight that betrayed the presence of transiting planets. The primary mission, as it had been conceived and executed for 4 years, was over. To understand why 3 wheels are the minimum required for this kind of stabilization, we must think for a moment about the geometry of space itself. Space, as we experience it, has 3 dimensions, 3 independent directions in which objects can move or turn, and to control a spacecraft's orientation completely, one must be able to apply torques along all 3 of these axes. Each reaction wheel, mounted along a particular axis, provides control of rotation around that axis, and so 3 wheels, mounted along 3 perpendicular axes, provide the minimum capability needed for full 3-axis control. With only 2 wheels, there remains one axis of rotation that cannot be controlled by the wheels alone, and though the spacecraft can use other methods to manage this axis, such as firing small thrusters or allowing the solar radiation pressure to provide a restoring force, these methods are not precise enough for the kind of observations that Kepler was designed to make. The telescope needed to hold its pointing to within a few thousandths of an arcsecond, a level of precision that only the reaction wheels could provide, and with 2 of them gone, that capability was lost. The response from the engineering team was immediate and methodical. Charlie Sobek, the mission manager at NASA's Ames Research Center, led the effort to assess the situation and determine what options remained. The team had long known that this day might come, had discussed the scenarios and planned the contingencies, but the reality of facing a crippled spacecraft still demanded careful and deliberate action. The first priority was to ensure that no further harm came to Kepler, that the remaining systems were protected and that the spacecraft was placed in a stable configuration that would conserve its limited resources, particularly the hydrazine fuel that powered its small thrusters. This fuel, which had been used sparingly throughout the mission for tasks the reaction wheels could not perform, was now more precious than ever, for it represented the only means of controlling Kepler's orientation in the absence of working wheels. The spacecraft was commanded into what the engineers called a point rest state, a configuration in which it was oriented with its solar panels facing the sun, ensuring a steady supply of electrical power, while the reaction wheels were spun down and the thrusters were used only as needed to maintain this basic orientation. In this state, Kepler could remain stable for long periods, drifting quietly while the teams on Earth considered their options. It was a kind of hibernation, a pause in the spacecraft's active work, but one that preserved the possibility of future operations if a solution could be found. During the summer of 2013, the engineering team made a determined effort to revive reaction wheel number 4, hoping that the symptoms it had shown might have been temporary, that a period of rest might have allowed whatever problem afflicted it to resolve. The wheel was carefully spun up again, its telemetry monitored with intense attention, but the results were disappointing. The friction remained elevated, the wheel could not maintain stable operation, and it soon became clear that the damage was permanent. The attempt to restart the wheel was unsuccessful, and with that failure, the last hope of restoring Kepler's original pointing capability faded. The news of Kepler's crisis spread quickly through the scientific community, and the response was one of both sorrow and appreciation. Researchers who had built their careers on Kepler data, who had spent years analyzing the light curves and confirming the planetary candidates, spoke openly about what the mission had meant to them and to the field. Letters and messages arrived at NASA, from professional astronomers and from members of the public, expressing gratitude for the discoveries Kepler had made and hope that some way might be found to continue its work. The spacecraft had become, in its 4 years of operation, something more than a machine. It had become a symbol of humanity's curiosity about the cosmos, a quiet sentinel that had revealed the existence of worlds beyond counting, and the prospect of its loss touched many who had followed its progress. William Borucki, the principal investigator who had spent decades advocating for the mission and guiding it to fruition, felt the weight of this moment acutely. He had devoted a substantial portion of his professional life to Kepler, had persevered through years of rejection and setback to see it launched, and had led the scientific team through 4 years of remarkable discovery. To see the spacecraft crippled, unable to continue the work it had been designed to do, was a kind of grief, the loss of a project that had been not just a scientific endeavor but a personal calling. And yet Borucki and his colleagues took comfort in what had been achieved. The primary mission had been designed to last 3.5 years, and Kepler had exceeded that goal, operating for 4 years before the second wheel failure brought its observations to a halt. In that time, it had identified over 2,600 candidate planets, objects awaiting confirmation by follow-up observations, and it had already yielded confirmed discoveries that had reshaped our understanding of planetary systems. The mission was not a failure. It was a success that had simply reached the limits of its mechanical endurance. Still, there was a period of uncertainty, weeks and then months during which the future of Kepler remained unclear. NASA convened review panels and engineering assessments, asking whether there was any way to continue scientific operations with the remaining spacecraft capabilities. The possibility of repurposing Kepler for a different kind of mission was discussed, though the details of what that mission might look like remained to be worked out. In the meantime, the spacecraft drifted in its point rest state, conserving fuel, waiting, while the people who had built and operated it considered what might still be possible. The data that Kepler had already collected continued to yield discoveries during this period. The light curves from 4 years of observations were stored in archives on Earth, and scientists around the world were still working through them, identifying new candidates, refining the parameters of known systems, publishing papers that added to the growing body of knowledge about exoplanets. The spacecraft's scientific legacy was secure, regardless of what happened next, but there was a natural hope that Kepler might yet have more to give, that some clever engineering solution might allow it to continue its work in some form. And so we leave Kepler, for now, in this quiet state of waiting, its solar panels turned toward the sun, its instruments powered down, its remaining reaction wheels still and silent. The crisis of 2013 marked the end of one chapter in its story, But as we shall see in the sections that follow, it was not the end of the story itself. The engineers and scientists who had brought Kepler so far were not ready to give up, and in the months to come they would devise a new way of operating the spacecraft, a method that would allow it to continue hunting for planets even with only 2 working wheels. But that is a tale for another time, and for now we may simply rest with the knowledge that Kepler had already accomplished what it set out to do, had answered the question that William Borucki had posed so many years before, had shown us that planets are common in our galaxy, that Earth-sized worlds orbit in the habitable zones of other stars, and that we are not alone in the universe in the sense that other places exist where life as we know it might find a home. The wheels had come off, as the saying goes, but the journey was far from over, and the gentle light of distant suns continued to fall upon Kepler's silent mirror, waiting to be gathered once more. When the second of Kepler's 4 reaction wheels failed in May of 2013, the spacecraft found itself in a condition that many observers believed to be terminal, a state from which no meaningful scientific work could reasonably be expected to continue. The reaction wheels, those spinning mechanisms that had allowed the telescope to maintain its extraordinarily precise pointing for more than 4 years, were essential to the kind of observations that Kepler had been designed to perform, and without at least 3 of them functioning properly, the telescope could no longer hold its gaze steady enough to detect the tiny dimming of starlight that betrayed a planet crossing in front of its host star. The situation appeared, to most who considered it carefully, to represent the end of an era, a conclusion to what had been one of the most successful planet-hunting missions in the history of space exploration. Yet within the engineering teams at Ball Aerospace and the Jet Propulsion Laboratory, and among the scientists who had devoted years of their careers to understanding and operating this remarkable instrument, there persisted a quiet determination to explore whether something, anything, might yet be salvaged from what remained. It is worth pausing here, as we settle further into this gentle exploration of ingenuity, to consider what the loss of those reaction wheels truly meant in practical terms. A reaction wheel works by spinning a weighted disk at varying speeds, and by changing how fast the disk spins, the spacecraft can rotate itself in the opposite direction without expending any propellant, a principle derived from the conservation of angular momentum that you may remember from basic physics, though remembering it is not at all necessary for our purposes here tonight. Kepler had been designed with 4 such wheels, 3 for controlling the telescope's orientation along each of the 3 axes of space, and 1 spare in case any single wheel should fail. When the first wheel failed in July of 2012, the mission continued with its 3 remaining wheels, still capable of performing its intended observations. But when the second wheel failed the following year, no backup remained, and the telescope was left with only 2 functioning wheels, which was simply insufficient to maintain the rock-steady pointing that exoplanet detection requires. The problem, stated simply, was that without control along all 3 axes, the telescope would gradually drift away from whatever target it was attempting to observe, and even a drift too small for human eyes to perceive would be enough to ruin the extraordinarily sensitive photometric measurements that Kepler needed to perform. The telescope required a pointing stability measured in fractions of an arcsecond, a unit so small that it is difficult to convey its meaning in everyday terms, though perhaps it helps to know that 1 arcsecond is the angle subtended by human hair viewed from a distance of roughly 20 meters, and Kepler needed to do considerably better than that. With only 2 reaction wheels, such stability seemed entirely beyond reach, and the spacecraft appeared destined to become an expensive piece of debris drifting silently through its orbit around the Sun, its primary mirror still perfect, its photometer still sensitive, but its ability to point at anything with the required precision forever compromised. It was in this context that a Ball aerospace engineer named Doug Weimer proposed an idea that was both elegantly simple in concept and extraordinarily challenging in execution. Weimer suggested that the spacecraft might be able to use the pressure of sunlight itself, the gentle but persistent push exerted by photons striking the spacecraft surfaces, as a substitute for the missing reaction wheel. This phenomenon, known as solar radiation pressure, is something that spacecraft engineers typically regard as a nuisance, a constant perturbation that must be corrected for rather than exploited. The idea of using it intentionally for attitude control was not entirely new, but applying it to a telescope that required such extreme pointing precision was something that had never been attempted before. The principle behind Weimer's proposal rested on a careful balancing act. If the spacecraft could be oriented such that the pressure of sunlight pushed equally on both sides of the solar panels and the telescope body, then the torques produced by that pressure would cancel each other out, leaving the spacecraft in a state of equilibrium. This balanced configuration would reduce but not eliminate the drift caused by the missing reaction wheel, and the remaining two wheels could then be used to control the other two axes of rotation while the solar pressure handled the third. It was rather like balancing a pencil on its tip. If the pencil were 800 kilograms and located 150 million kilometers from the nearest helping hand. The engineering team at Ball Aerospace, working in close collaboration with the mission operations staff at the Laboratory for Atmospheric and Space Physics in Boulder, Colorado, began developing procedures to test whether this concept could actually work in practice. Throughout the summer and autumn of 2013, they conducted a series of increasingly sophisticated tests, gradually refining their understanding of how the spacecraft behaved under various orientations and configurations. The work was painstaking and methodical, requiring careful analysis of telemetry data and repeated adjustments to the spacecraft's attitude control software. In October of 2013, the team conducted a proof-of-concept test that would determine whether the K2 mission, as it was beginning to be called, had any real chance of success. The test demonstrated that balanced pointing was indeed possible, that the spacecraft could be oriented in such a way that solar pressure provided a stabilizing influence rather than a destabilizing one, and that the pointing precision achievable in this configuration, while not as good as what Kepler had achieved during its primary mission, was nevertheless sufficient to perform meaningful astronomical observations. The results were encouraging enough that NASA began seriously considering whether to approve an extended mission based on this new operating mode. In May of 2014, following months of technical review and programmatic consideration, NASA formally approved the K2 mission, giving the wounded telescope a second life that few had thought possible when the reaction wheel failure was first diagnosed. The approval marked not just a technical achievement but also a philosophical one, a recognition that the resources already invested in the Kepler spacecraft, the careful engineering, the sensitive instruments, the years of operational experience, retained significant value even when the original mission could no longer be performed exactly as intended. Sometimes, in science as in life, the path forward requires accepting that the destination has changed while recognizing that the journey itself still holds meaning. The K2 mission operated under constraints quite different from those of the original Kepler mission. Where Kepler had stared continuously at a single patch of sky in the constellation Cygnus for years on end, K2 would need to shift its gaze regularly to maintain the balanced pointing that made observations possible at all. The spacecraft could only achieve its equilibrium configuration when pointed in directions that lay along the plane of the ecliptic, the flat disk in which Earth and the other planets orbit the Sun. This meant that K2 would observe different fields of view roughly every 80 days, with each period of observation designated as a campaign, and each campaign targeting a different region of sky along that ecliptic plane. This observing strategy, born entirely of necessity, turned out to have certain advantages that the original mission had lacked. While Kepler had studied one region of sky with extraordinary depth and precision, K2 would sample many different regions with somewhat less precision but considerably greater variety. The ecliptic plane happens to contain a number of interesting astronomical targets that the original Kepler field did not include, among them the planets of our own solar system, numerous asteroids and other small bodies, several prominent star clusters, and regions of active star formation containing young stellar systems quite different from the older, settled stars that Kepler had primarily observed. Campaign 0, as the first observing period was designated, began in March of 2014, even before the formal approval of the K2 mission, serving as an engineering demonstration to verify that the new observing mode could actually produce scientifically useful data. The results were sufficiently promising that the mission proceeded to Campaign 1 and beyond, eventually completing 19 separate campaigns before the spacecraft finally exhausted its fuel supply in October of 2018. Each campaign lasted approximately 80 days, and each observed a different field along the ecliptic, building up over time a diverse catalogue of photometric observations spanning many different types of stellar systems and astronomical phenomena. The precision achieved by K2 was, as expected, somewhat degraded compared to the primary Kepler mission, roughly 5 times worse by most measures, though the exact figure varied depending on the brightness of the target star and the specific details of the observation. This reduced precision meant that K2 was less sensitive to the smallest exoplanets, the Earth-sized worlds that had been among Kepler's most exciting discoveries, but it remained quite capable of detecting larger planets, super-Earths and mini-Neptunes and gas giants, particularly around the smaller, cooler stars where the transit signal is proportionally larger and easier to detect. What K2 gained in exchange for this reduced precision was a breadth of target selection that the original mission had never possessed. Kepler had been designed and optimized for a single purpose: the detection of Earth-like planets around Sun-like stars, and while it had achieved extraordinary success in that endeavor, its field of view and observing strategy had been fixed from the beginning. K2, by contrast, could observe whatever targets happened to lie within its campaign fields, and the guest observer program that NASA established allowed astronomers from around the world to propose targets and investigations that extended far beyond the original exoplanet focus. This guest observer program opened Kepler's remarkable photometric capabilities to the broader astronomical community, inviting researchers who studied everything from asteroids to distant galaxies to submit proposals for K2 observations. The program democratized access to the spacecraft in a way that the primary mission had not, allowing scientists who had never been involved with Kepler to design observations and analyze data from this uniquely sensitive instrument. The result was a flowering of diverse science that encompassed stellar variability, binary star systems, asteroseismology, supernova detection, and the study of solar system objects, alongside the continued search for exoplanets that remained the mission's central purpose. Among the most intriguing targets that K2 observed were nearby young stars, stellar systems in the early stages of their development when planets might still be forming or settling into their final orbits. These young systems are relatively rare in the solar neighborhood, but several lay within the fields that K2 observed, and the data gathered on them provided valuable insights into the early evolution of planetary systems. Star clusters, too, fell within K2's purview, collections of stars that form together from the same cloud of gas and dust and thus share common properties of age and composition. By observing stars in clusters, astronomers could study how stellar variability and planetary occurrence rates depend on these fundamental stellar properties in ways that were difficult to assess from the more heterogeneous stellar populations that Kepler had observed. The spacecraft even turned its attention to objects within our own solar system, observing the distant ice giant Neptune during Campaign 3 and tracking numerous asteroids as they moved across the fields of view during various campaigns. These observations, quite different from anything Kepler had been designed to perform, demonstrated the versatility of the instrument and the creativity of the scientific community in finding new uses for an old spacecraft. Perhaps most remarkably, K2 made direct observations of supernovae, the explosive deaths of massive stars that represent some of the most energetic events in the universe. Because K2 observed each campaign field continuously for roughly 80 days, it was able to capture the complete light curves of supernovae that happened to explode within its field of view, recording the brightening and fading of these distant explosions with a precision and cadence that ground-based observations rarely achieve. These observations provided new constraints on the physics of stellar explosions and contributed to ongoing efforts to understand the mechanisms that produce these spectacular events. Among the exoplanet discoveries that emerged from K2, several stand out as particularly significant for our understanding of planetary systems beyond our own. The spacecraft observed the TRAPPIST-1 system during Campaign 12 in late 2016 and early 2017, providing data that supported and extended the ground-based observations that had first identified this remarkable system of 7 Earth-sized planets orbiting an ultra-cool red dwarf star less than 40 light-years from Earth. While the initial discoveries of the TRAPPIST-1 planets had been made by the ground-based TRAPPIST telescope in Chile, the K2 observations provided additional photometric data that helped confirm and characterize the planetary system, demonstrating the value of space-based observations even for targets that could be studied from the ground. Another notable K2 discovery was the planet now designated K2-18b, first detected during Campaign 1 in 2015. This planet orbits a red dwarf star approximately 120 light-years from Earth, completing one orbit every 33 days and residing within its star's habitable zone, the range of distances where temperatures might allow liquid water to exist on a planetary surface. K2-18b is considerably larger than Earth, roughly 8 times more massive, placing it in the category of planets sometimes called super-Earths or mini-Neptunes, worlds with no analogue in our own solar system whose compositions and atmospheric conditions remain subjects of active investigation. What made K2-18b particularly notable was not merely its detection but what subsequent observations revealed about its atmosphere. In 2019, several years after the initial K2 discovery, astronomers using the Hubble Space Telescope detected water vapor in the atmosphere of K2-18b, marking the first time that water had been identified in the atmosphere of a potentially habitable exoplanet. The detection relied on a technique called transmission spectroscopy, in which light from the host star passes through the planet's atmosphere during a transit, allowing certain wavelengths to be absorbed by atmospheric molecules while others pass through unimpeded. By analyzing the pattern of absorption, astronomers were able to identify the spectral signature of water vapor, suggesting that this distant world possesses at least some of the chemical ingredients that we associate with habitability. The discovery of water vapor on K2-18b was widely reported and generated considerable public interest, though it is important to note that the presence of water vapor does not by itself indicate that a planet is habitable or inhabited. K2-18b is likely quite different from Earth in many ways, and its large mass suggests that it may possess a deep atmosphere rich in hydrogen and helium, quite unlike the thin blanket of nitrogen and oxygen that surrounds our own world. Nevertheless, the detection demonstrated the remarkable journey that a planet could take, from initial identification by a repurposed spacecraft operating at reduced precision, through careful analysis and follow-up observation, to eventual characterization of its atmospheric composition using humanity's most powerful space telescope. The K2 mission continued until October of 2018, when the spacecraft finally exhausted the fuel it needed to maintain its balance pointing and transmit data back to Earth. Over the course of its extended mission, K2 observed more than 500,000 stars across its 19 campaigns, discovering hundreds of confirmed exoplanets and thousands of additional candidates awaiting confirmation. The mission demonstrated that failure need not be final, that ingenuity and determination can sometimes find ways forward that were not apparent when the original plans went awry, and that scientific instruments, like the people who build and operate them, can sometimes surprise us with their resilience. The spacecraft was decommissioned on the 30th of October, 2018, placed in a safe orbit around the Sun where it will continue to drift for millennia to come, its instruments finally silent after more than 9 years of continuous operation. The data it gathered, both during its primary mission and during the K2 extended mission, will continue to be analyzed for years and perhaps decades, yielding new discoveries long after the telescope itself has fallen quiet. And somewhere in the archives of Ball Aerospace, the proposal from Doug Weimer remains, a document that outlined how solar photon pressure might be used to balance a wounded spacecraft and give it one more chance to contribute to human understanding of the cosmos. This was the Phoenix mission, born not from fire but from failure, a testament to the proposition that even when things do not go according to plan, there may yet be paths forward that preserve what can be preserved and accomplish what can still be accomplished. The universe does not arrange itself for our convenience, and the instruments we build do not always perform as we intend, but within those constraints there often remains room for creativity, for adaptation, and for the quiet satisfaction of finding a way to continue the work when continuing seemed impossible. Among the thousands upon thousands of worlds that Kepler observed during its years of patient watching, there emerged a collection of planets so strange, so unexpected, and so wonderfully bizarre that they seemed almost to belong to the realm of science fiction rather than to the careful domain of observational astronomy. These were the worlds that defied easy categorization, the planets that challenged our assumptions about how planetary systems form and evolve, and the discoveries that reminded us, again and again, that the universe possesses an imagination far more varied and surprising than our own. We might call them the Hellworlds and the Oddballs, the strange cousins and the peculiar neighbors in the great family of exoplanets, and each one of them has a story worth telling in the quiet hours before sleep. Let us begin with a world called Kepler 70b, which orbits so close to its host star, a type of stellar remnant called a subdwarf B star, that its surface temperature reaches approximately 5,700 degrees Celsius. To put this extraordinary figure into some perspective, we might note that this temperature actually exceeds the temperature of the visible surface of our own Sun, which hovers around 5,500 degrees Celsius. The Sun, of course, is a main sequence star in the prime of its hydrogen-burning life, radiating energy from nuclear fusion deep within its core, and yet here is a planet whose surface burns hotter than that stellar photosphere. The reason for this remarkable situation lies in the history of Kepler 70b itself, which astronomers believe may be the exposed remnant core of what was once a much larger gas giant planet, similar perhaps to Jupiter or Saturn in its youth. Long ago, when the host star expanded during a red giant phase of its evolution, the outer layers of the unfortunate planet would have been stripped away by the intense heat and the gravitational interaction with the bloated stellar envelope, leaving behind only the dense, metallic core that we detect today. This core, now exposed to the fierce radiation of the compact stellar remnant, glows with a temperature that seems almost impossible for a planetary body, and yet the transit observations and the careful analysis confirm that it is indeed there, orbiting in a blisteringly short period of just a few hours, a seared and ancient survivor of a violent stellar transformation. Quite different in character, but equally puzzling to planetary scientists, are the pair of worlds known as Kepler 36b and Kepler 36c, which orbit the same star at distances so remarkably similar that their gravitational interactions must be extraordinarily intense. These two planets circle their host star with orbital distances that differ by only about 0.013 astronomical units, which means that at their closest approach, they pass within approximately 1.9 million kilometers of one another. On a cosmic scale, this is an almost intimate proximity, and the gravitational tugs that each planet exerts upon the other during these close encounters must produce tidal forces and orbital perturbations of considerable magnitude. What makes this system even more intriguing, however, is the striking difference in the densities of these two neighboring worlds. Kepler 36b appears to be a rocky super-Earth-type planet, dense and compact, with a composition perhaps similar to that of our own terrestrial worlds. Kepler 36c, by contrast, is a puffy, low-density world more akin to a mini-Neptune, swollen with thick atmospheric gases that give it a much larger radius despite having only modestly more mass than its neighbor. The coexistence of these two very different types of planets in such close orbital proximity raises fascinating questions about planetary formation and migration, about how such disparate worlds could have ended up sharing nearly the same orbital space around their common star, and about the long-term stability of such an arrangement over billions of years of gravitational pushing and pulling. Perhaps no Kepler discovery captures the transient and fragile nature of some planetary bodies quite like the world-designated Kepler 1520b, which is also known by its original catalogue number KIC 125575548b, and which has earned the evocative informal name of the disintegrating planet. This small, rocky world orbits so close to its host star, completing each circuit in approximately 15.5 hours, that the intense stellar radiation is literally vaporizing the planetary surface and carrying away rocky material into space. The result is a long, trailing tail of dust and debris that streams away from the planet much like the dust tail of a comet when it approaches the Sun, and this tail produces a distinctive and variable signature in the light curve that Kepler observed. Unlike the clean, sharp-edged dips of most planetary transits, the signal from Kepler 1520b shows a gradual dimming followed by a longer, slower brightening as the dusty tail sweeps across the face of the star. The depth of these transit-like events varies from orbit to orbit, suggesting that the rate of mass loss is not constant but fluctuates depending on conditions at the planetary surface. Astronomers estimate that this unfortunate world may be losing mass at a rate that will cause it to completely disintegrate within 100 million years or so, a very short span by cosmic standards, and we are fortunate to be observing it during this dramatic final chapter of its existence. The planet is essentially evaporating before our eyes, dissolving into a stream of rocky vapor and dust, and the Kepler observations have given us a unique window into this extraordinary process of planetary destruction. The fate of being consumed by a host star is not limited to small, rocky worlds, however, and the gas giant planet Kepler 432b provides a sobering example of a large planet that is gradually spiraling toward its own demise. The host star of this system is an aging red giant, a star that has exhausted the hydrogen fuel in its core and has expanded to many times its original size as it burns heavier elements in shells surrounding the inert core. Kepler 432b, which has a mass roughly 6 times that of Jupiter, orbits this bloated star in an eccentric, elongated path that brings it very close to the stellar surface at its closest approach. At this intimate distance, the gravitational tides raised by the red giant are gradually robbing the planet of orbital energy, causing it to spiral slowly but inexorably inward with each passing orbit. In perhaps 50 million years, give or take, the planet will plunge into the outer atmosphere of the red giant star and be consumed entirely, its hydrogen and helium gases mixing with the stellar envelope, its existence as a separate planetary body coming to a fiery end. For now, however, Kepler 432b continues its precarious dance around its dying star, a massive world living out its final cosmic moments in a system that is itself approaching the later stages of stellar evolution. Among the strangest worlds that Kepler found is the small planet Kepler 78b, an Earth-sized world that orbits its host star in the astonishingly brief period of just 8.5 hours. This orbital period is so short, and the corresponding orbital distance so small, that the planet circles its star at a distance of less than 2 stellar radii from the stellar surface. At this proximity, the surface of Kepler 78b is heated to temperatures exceeding 2000 degrees Celsius, far above the melting point of rock, and the entire surface of the planet is believed to be covered in an ocean of molten lava that glows with an angry red or orange hue. The planet is a lava world, a hellish sphere of liquid rock that perpetually faces its nearby star, and the conditions there are as inhospitable to life as any we might imagine. What makes Kepler 78b particularly puzzling to planetary scientists, however, is not merely its extreme environment but the fundamental question of how it came to exist in its current location at all. According to our best models of planetary formation, such a close-in orbit should not be possible for a planet of this size and composition. When the host star was younger and still forming, it would have been much larger, and the space where Kepler 78b now orbits would have been inside the star itself. The planet could not have formed there, and yet our models of planetary migration do not easily explain how it could have moved to such an extreme orbit after forming farther out. The existence of Kepler 78b represents a genuine puzzle, a world that by all rights should not be where we find it, and its presence challenges us to refine our understanding of how planetary systems assemble and evolve over time. The universe, it seems, enjoys placing planets in gravitationally complex environments, and the Kepler mission revealed several examples of planets orbiting not 1 but 2 or even 3 stars simultaneously. One particularly charming example is Kepler 453b, a circumbinary planet that orbits around both stars of a binary pair. What makes this world especially noteworthy in the history of its discovery is that the transit events that revealed its presence actually precessed out of view for several years before precessing back into a geometry where the planet crossed the face of the stars as seen from Earth. Because the orbital plane of the planet is not perfectly aligned with the orbital plane of the two stars, the gravitational influences within the system cause the planetary orbit to slowly wobble or precess over time, much like a spinning top that gradually changes the orientation of its axis. For a period of years, this precession carried the orbital path out of the narrow band where transits could be observed, and the planet effectively vanished from the Kepler data despite continuing to exist and orbit in perfect regularity. Later, as the precession continued, the geometry shifted once more, and the transit events reappeared, allowing the planet to be confirmed at last. This hide-and-seek behavior serves as a gentle reminder that the transit method, powerful as it is, can only detect planets whose orbits happen to align favorably with our line of sight, and that the universe may hide many more worlds in orientations where we simply cannot see them pass in front of their host stars. Even more gravitationally complex is the system designated KOI-5, in which a planet called KOI-5ab orbits within a hierarchical triple star system. The planet itself circles the primary star of the system, while that star is itself locked in a binary orbit with a second star, and both of these are accompanied by a third, more distant stellar companion that orbits the inner pair at a much greater separation. The gravitational dynamics of such a system are extraordinarily intricate, with each star tugging on the others and on the planet in a delicate cosmic dance that somehow maintains stability over billions of years. When KOI-5ab was first identified in the Kepler data, it was among the very earliest planet candidates found, but the complexity of the triple star system made it difficult to confirm the planetary nature of the signal for many years. Only with additional observations and careful analysis was the planet finally verified, joining the small but growing family of worlds known to exist in the chaotic gravitational environments of multiple star systems. The fact that planets can form and survive in such settings speaks to the resilience and adaptability of planetary formation processes, and it expands our sense of the diverse contexts in which worlds might come to exist throughout the galaxy. Among the lightweight champions of the exoplanet population is Kepler 51b, a world so remarkably low in density that it has earned the informal nickname of the Styrofoam planet. With a density estimated at approximately 0.03 grams per cubic centimeter, this world is less dense than any material we commonly encounter in everyday life on Earth, fluffier even than cotton candy and far less substantial than the lightest aerogels produced in our laboratories. The planet achieves this extraordinary low density by combining a relatively modest mass with an enormously inflated radius, puffed up by thick layers of hydrogen and helium gas that extend far out from whatever small rocky or icy core may lie at the center. The mechanisms that produce such extreme inflation are not entirely understood, but they may involve the trapping of heat in the deep atmosphere, the effects of stellar radiation on the upper atmospheric layers, or some combination of factors that conspire to prevent the planet from contracting into a more compact configuration. Kepler 51b and its sibling planets in the same system represent an extreme end of the planetary density spectrum, worlds so light and airy that they seem almost insubstantial, and yet they are real and measurable objects whose transits dim the light of their host star in ways that Kepler faithfully recorded. Finally, let us consider the case of Kepler 10c, a world that for a time was believed to represent an entirely new category of planet called a mega-Earth. Initial measurements suggested that this planet had a mass of approximately 17 times that of Earth, packed into a radius only about 2 1/3 times larger, implying a density so high that the planet must be composed almost entirely of rock and metal with little or no gaseous envelope. Such a massive rocky world would challenge our understanding of planet formation, which suggests that objects above about 10 Earth masses should accumulate thick atmospheres of hydrogen and helium and become more like Neptune than like Earth. The discovery of Kepler 10c as a mega-Earth seemed to indicate that rocky planet formation could proceed to much higher masses than we had expected, perhaps through special conditions in the protoplanetary disk or through unusual evolutionary pathways. However, subsequent measurements using more precise techniques revised the mass estimate significantly downward, suggesting that Kepler 10c is probably less dense and less massive than initially thought, perhaps more consistent with a world that has a substantial volatile envelope after all. The story of Kepler 10c serves as a useful reminder that our measurements and our interpretations are always subject to revision as new data become available and as our techniques improve, and that the process of scientific discovery is one of gradual refinement rather than sudden and final revelation. These strange worlds, from the scorched remnant core of Kepler 70b to the disintegrating dusty trail of Kepler 1520b, from the gravitationally entangled pair of Kepler 36 to the precariously doomed giant of Kepler 432, represent just a sampling of the extraordinary diversity that the Kepler mission revealed in the population of exoplanets. Each of these objects tells a story of formation, evolution, and survival under conditions that we might never have imagined before we had the tools to detect them. They remind us that the cosmos is a place of endless variation, where the familiar categories of planet that we derived from studying our own solar system represent only a small corner of the true range of possibilities. As you rest here in the quiet and the dark, perhaps drifting towards sleep, you might take comfort in the thought that the universe is filled with wonders beyond counting, with worlds both strange and familiar waiting to be discovered by future missions and future generations of astronomers, and that the Kepler spacecraft, during its 9 years of patient observation, gave us our first true glimpse into this extraordinary cosmic menagerie. Among the many millions of stars that Kepler observed during its primary mission, there was one that behaved in a manner so peculiar, so utterly unlike anything astronomers had encountered before, that it would eventually capture the imagination of scientists and the general public alike, spawning headlines around the world and prompting serious scientific discussion about possibilities that had previously belonged only to the realm of science fiction. This star, catalogued with the designation KIC 846-2852, sits approximately 1,400 light-years from Earth in the constellation Cygnus, and for most of Kepler's mission it appeared entirely unremarkable, just another F-type star slightly larger and hotter than our own Sun, going about its stellar business in the quiet depths of the galaxy. But hidden within the data that Kepler faithfully collected, day after day and month after month, were patterns of dimming so strange and so irregular that they defied easy explanation. And when these patterns were finally discovered, they would set in motion one of the most fascinating astronomical investigations of the early 21st century. The discovery of this star's peculiar behavior did not come from professional astronomers working in observatories or universities, but rather from ordinary people participating in a remarkable project called Planet Hunters, which had been established in 2010 as part of the Zooniverse Citizen Science Platform. The premise of Planet Hunters was beautifully simple, recognizing that while computers are excellent at finding patterns that match what they have been programmed to seek, human eyes and human intuition remain remarkably adept at noticing things that are simply odd, things that do not fit neatly into predefined categories. Volunteers from around the world, requiring no scientific training beyond a willingness to learn and look carefully, would examine Kepler light curves on their home computers, marking any dips in brightness that might indicate a transiting planet. By 2015, hundreds of thousands of people had participated in this project, collectively examining millions of light curves and contributing to the discovery of numerous confirmed exoplanets that automated algorithms had initially overlooked. It was through this network of dedicated volunteers that the strange behavior of KIC 846-2852 first came to scientific attention. Several citizen scientists, working independently but all examining the same star's data, began flagging it as unusual, noting that its light curve contained dimming events unlike anything they had seen in their many hours of careful observation. The dips were not the smooth, regular, U-shaped valleys that characterize planetary transits, where a spherical body passes in front of a star and blocks a consistent fraction of its light in a predictable, repeating pattern. Instead, the dimming events were irregular in their timing, asymmetrical in their shape, and most remarkably, varied enormously in their depth. Some dips blocked only a fraction of a percent of the star's light, while others reduced its brightness by several percent, and in the most extreme cases recorded during Kepler's observations, the star dimmed by as much as 22%, a staggering amount that implied something truly enormous was passing between the star and Kepler's watchful eye. To appreciate just how extraordinary a 22% dimming truly is, one must consider what we know about how much light planets typically block when they transit their host stars. Jupiter, the largest planet in our solar system, a world so massive it contains more matter than all the other planets combined, would block only about 1% of the Sun's light if viewed by a distant observer during a transit. Even a star being orbited by an object the size of Jupiter at a very close distance would produce dips of only 1 or 2% at most. For something to block 22% of a star's light, it would need to be roughly half the diameter of the star itself, an object so large that if it were a planet, it would almost certainly have become a star in its own right through gravitational collapse and nuclear ignition. The dimming events of KIC 846-2852 seemed to require something that was not only enormous but also possessed an irregular shape, something that was decidedly not spherical. And this realization was what transformed a curious astronomical anomaly into a genuine scientific mystery. The task of making sense of this mystery fell initially to Tabitha Boyajian, then a postdoctoral researcher at Yale University who was working with the Planet Hunters team and who would become so closely associated with the star that it is now commonly known as Boyajian's star in her honor, though it is also sometimes called Tabby star as a more informal tribute. Boyajian gathered a team of collaborators and set about the painstaking work of analyzing all available data on the star, attempting to characterize its behavior with scientific rigor and to consider what natural phenomena might explain what Kepler had observed. Their paper, which was submitted for publication in the summer of 2015 and appeared in the monthly notices of the Royal Astronomical Society in September of that year, presented the observational evidence in careful detail and considered a range of possible explanations, from instrumental artifacts to various astrophysical scenarios. The paper methodically worked through and largely dismissed many prosaic explanations. The dimming was clearly not caused by problems with Kepler itself, as the star's neighbors showed no similar behavior and the spacecraft's instruments were functioning normally. The star did not appear to be intrinsically variable in the ways that many stars are, pulsating or fluctuating due to internal processes. There was no evidence of a companion star that might be causing eclipses. The irregular nature of the dips, Their varying depths and durations and their non-periodic timing ruled out any simple explanation involving a single orbiting body. Boyajian and her colleagues ultimately suggested that the most likely natural explanation might be a swarm of comets, perhaps a large family of icy bodies that had been gravitationally perturbed and sent streaming toward the inner regions of the star system, where their dusty tails might create the irregular obscurations that Kepler had detected. This explanation was tentative, offered not as a confident conclusion but as the least problematic of the available hypotheses, and the paper acknowledged that the star's behavior remained genuinely puzzling. It was shortly after the paper's publication, in October 2015, that the story of KIC 846-2852 took an unexpected turn toward the spectacular. Jason Wright, an astronomer at Penn State University who studies stars and searches for signs of extraterrestrial intelligence, had been following the developing mystery with great interest. Wright pointed out, in discussions with journalists and in his own blog posts, that one should at least consider the possibility, however remote, that the irregular dimming might be caused by artificial structures, vast constructions built by an advanced technological civilization to harvest energy from their star. This concept, often called a Dyson sphere or Dyson swarm after the physicist Freeman Dyson who first proposed it in 1960, imagines that a sufficiently advanced civilization might construct enormous orbiting platforms or habitats to capture a significant fraction of their star's energy output. And such structures, if they existed, might produce exactly the kind of irregular, aperiodic dimming that Kepler had observed. Wright was careful to note that he considered this explanation highly unlikely, that natural explanations were almost certainly correct, and that the responsible scientific approach was to investigate thoroughly before reaching any conclusions. But the mere suggestion that astronomers were seriously discussing, even as a remote possibility, the idea that an alien megastructure might exist around a star 1,400 light-years away proved irresistible to the media and the public imagination. Headlines proclaiming the discovery of a possible alien civilization spread rapidly across the Internet, and K846-2852 became perhaps the most famous star in the sky, known to millions who had never heard of Kepler or transit photometry or any of the patient work that had led to its discovery. The scientific community responded to this surge of public interest not with dismissal but with genuine curiosity, recognizing that while the alien megastructure hypothesis was almost certainly wrong, the mystery it had helped publicize was real and worthy of serious investigation. The SETI Institute, which operates radio telescopes dedicated to searching for signals from extraterrestrial intelligences, pointed its instruments toward the star and listened carefully for any signs of artificial radio transmissions. These observations, conducted using the Allen Telescope Array in California, found no evidence of artificial signals, no narrowband radio emissions of the type that a technological civilization might produce for communication or other purposes. This negative result did not definitively rule out the presence of extraterrestrial intelligence, as there are many reasons why an advanced civilization might not be broadcasting detectable radio signals, but it did suggest that the simplest versions of the alien megastructure hypothesis were not supported by the available evidence. Meanwhile, astronomers recognized that the best way to understand the star's behavior would be to observe it during an actual dimming event, something that had not been possible during the Kepler mission because the spacecraft only provided brightness measurements in a single broad optical band, and the dips had only been identified through retrospective analysis of archival data. To catch the star in the act of dimming and study it with multiple instruments at many different wavelengths would require a dedicated monitoring campaign, and Boyajian launched an effort to make this happen. In 2016, she organized a crowdfunding campaign on Kickstarter to raise money for telescope time, and the response from the public was extraordinary, with more than 1,700 backers contributing over $100,000 to support continued observations. This outpouring of support demonstrated just how deeply the mystery of this peculiar star had captured public imagination, and it provided the resources needed to begin a long-term monitoring program. The patient waiting was rewarded in the spring of 2017, when astronomers around the world received word that Boyajian's star was dimming again. For the first time, a dimming event could be observed in real time with modern telescopes, and astronomers scrambled to gather data across the electromagnetic spectrum, from ultraviolet through visible light to infrared. The results of these observations would prove crucial in distinguishing between the various hypotheses that had been proposed. If the dimming were caused by solid, opaque structures, whether natural or artificial, then the star's light should be blocked equally at all wavelengths, just as an ordinary solid object casts a shadow that is the same at all colors. But if the dimming were caused by dust, by tiny particles comparable in size to the wavelength of light, then the blocking should be wavelength dependent, with shorter wavelengths being blocked more effectively than longer ones, producing a characteristic signature known as reddening. The observations of the 2017 dimming events, and subsequent events that followed in the years after, consistently showed that the dimming was indeed wavelength dependent. The star dimmed more strongly in blue light than in red light, precisely as would be expected if the obscuring material consisted of fine dust particles rather than large solid structures. This finding was a significant step toward resolving the mystery, effectively ruling out the alien megastructure hypothesis and pointing firmly toward a natural explanation involving circumstellar dust. Whatever was causing the dimming of Boyajian's star, it appeared to be something grainy, something particulate, something that scattered and absorbed light in the manner of very small solid particles suspended in the space around the star. The Breakthrough Listen initiative, a 10-year program funded by technology investor Yuri Milner to search for evidence of technologically advanced life beyond Earth, also turned its attention to Boyajian's star during this period. Using the Green Bank Telescope in West Virginia, one of the largest fully steerable radio dishes in the world, Breakthrough Listen conducted extensive observations searching for any artificial signals emanating from the star's vicinity. These searches examined a wide range of radio frequencies and signal types, looking for anything that might suggest the presence of intelligent beings, and like the earlier SETI observations, they found nothing out of the ordinary. The star appeared, by every measure that could detect artificial activity, to be accompanied by nothing more than ordinary cosmic silence. With the alien megastructure hypothesis effectively laid to rest by the wavelength-dependent dimming observations and the negative radio searches, astronomers have focused their attention on understanding what natural phenomenon might explain the star's remarkable behavior. Several possibilities have been proposed and debated, each with its own strengths and weaknesses. The original comet swarm hypothesis remains viable, imagining that a large population of comets on eccentric orbits might periodically shed dust as they pass near the star, creating the irregular dimming events. This would require an unusually large and active population of comets, perhaps recently perturbed by some gravitational interaction, but it is not outside the realm of known astrophysical phenomena. Another possibility involves the debris from a relatively recent collision or disruption event, perhaps involving a planet or large moon that was torn apart by tidal forces or shattered by an impact with another body. Such an event could produce a vast cloud of debris, ranging from large fragments to fine dust, that would spread out along the orbital path and gradually disperse over time. This hypothesis is attractive because it naturally explains both the irregular dimming, as clumps and streams of debris pass in front of the star, and the apparent long-term fading that some studies have suggested may be occurring, as the debris slowly spreads and diffuses. The disruption of a moon comparable in size to Ceres, the largest object in our solar system's asteroid belt, might produce enough material to explain the observations, and such events, while rare, are not impossible in the dynamic environments of planetary systems. Some researchers have proposed that the dust might not be orbiting the star at all, but might instead be located in the interstellar medium along our line of sight, a coincidental alignment of dust clouds between Earth and this particular star. However, detailed studies of the star's brightness variations over time have made this explanation seem less likely, as the behavior appears to be too structured and too correlated with the star itself to be easily explained by intervening material. Despite more than 8 years of intensive study since the star's strange behavior first came to widespread attention, the precise nature of the obscuring material remains uncertain. The weight of evidence now points firmly toward dust, fine particles that scatter blue light more strongly than red. But the question of where this dust comes from and why this particular star should possess so much of it in such an apparently disturbed configuration has not been definitively answered. The leading hypothesis favored by many researchers is that we are witnessing the aftermath of some dramatic event, perhaps the tidal disruption of a small moon or large asteroid, that has recently, in astronomical terms, produced a substantial quantity of debris that is now slowly spreading and settling around the star. The story of Boyajian's star illustrates beautifully both the power of citizen science and the self-correcting nature of the scientific process. The star's peculiar behavior was discovered not by professional astronomers but by ordinary people examining Kepler data in their spare time, demonstrating that important contributions to our understanding of the universe can come from anyone willing to look carefully and think critically. The alien megastructure hypothesis, far from being an embarrassment, served a valuable purpose in drawing attention to a genuine mystery and motivating the intensive observations that ultimately helped to rule it out. And the years of patient follow-up work, the telescope observations and data analysis and careful reasoning, exemplify how science gradually converges toward understanding through the accumulation of evidence and the testing of competing ideas. KIC 846-2852 continues to be monitored, and future observations may eventually provide the definitive answer to what has been blocking its light. Perhaps we will one day understand in complete detail the dusty debris that surrounds this distant star, the remnants of some ancient moon or planetesimal that met its end in the gravitational embrace of its stellar host. For now, the star remains a gentle reminder that the universe still holds mysteries, that careful observation can reveal the unexpected, and that sometimes the most remarkable discoveries come not from knowing what to look for but from remaining open to the possibility of finding something entirely new. When the Kepler Space Telescope turned its unblinking gaze toward a single patch of sky in the constellation Cygnus, it began collecting something far more enduring than the photons themselves, for it was gathering what would become one of the most valuable scientific archives ever assembled. A treasury of starlight measurements that would outlive the spacecraft by decades and continue yielding discoveries long after the last drop of hydrazine fuel had been exhausted and the telescope had fallen silent in its orbit around the Sun. The data that flowed from Kepler's instruments represented not merely observations but a kind of permanent record, a detailed census of stellar behavior that scientists would return to again and again, finding new worlds hidden in the numbers, sometimes years or even decades after the original measurements were taken. And this archive, carefully preserved and freely shared with researchers around the world, would prove to be one of the mission's most profound and lasting contributions to human knowledge. The custodian of this remarkable collection is the Barbara A. Mikulski Archive for Space Telescopes, known by its abbreviated name MAST, which operates as part of the Space Telescope Science Institute in Baltimore, Maryland, where rows of servers hum quietly in climate-controlled rooms, maintaining perfect digital copies of observations gathered by some of humanity's most ambitious astronomical instruments. MAST serves as the primary archive not only for Kepler but also for the Hubble Space Telescope, the Transiting Exoplanet Survey satellite, and numerous other missions that have expanded our understanding of the cosmos. And its servers hold within their magnetic memory the accumulated observations of generations of space-based observatories. When Kepler's data arrived on Earth, traveling across the millions of kilometers of space via the Deep Space Network's receiving stations, it eventually found its permanent home within this archive, where it was processed, calibrated, organized, and made available to any researcher who wished to examine it. The sheer volume of information that Kepler transmitted back to Earth during its operational lifetime is difficult to fully appreciate without pausing to consider the numbers involved. For the telescope produced over 678 gigabytes of calibrated science data during its years of operation, a figure that may seem modest by the standards of modern consumer electronics, but which represents an extraordinarily dense and valuable collection of astronomical measurements. Every 30 minutes throughout the primary mission, Kepler captured a fresh image of its entire field of view, and every 30 minutes, the brightness measurements of over 150,000 stars were recorded and eventually transmitted to Earth, creating an almost unimaginably detailed record of stellar behavior spanning 4 continuous years. This long cadence mode, as the 30-minute observation interval was known, captured the gradual dimming of stars as planets crossed in front of them, the subtle fluctuations caused by star spots rotating across stellar surfaces, and the slow pulsations of variable stars expanding and contracting over periods of hours or days. For certain targets of particular scientific interest, Kepler also offered a short cadence mode, which recorded brightness measurements every single minute rather than every 30 minutes, and this more rapid sampling allowed scientists to study phenomena that occurred on faster timescales, such as the oscillations of stars that vibrate with multiple frequencies simultaneously, or the rapid flickering of compact binary systems where 2 stars orbit so close together that matter streams between them. The short cadence observations consumed more of the spacecraft's limited data storage and transmission capacity, so they could only be allocated to a subset of the most scientifically valuable targets. But for those selected stars, the minute-by-minute measurements provided extraordinarily detailed portraits of stellar behavior, allowing researchers to detect subtle variations that would have been invisible in the longer cadence data. The combination of these 2 observation modes meant that Kepler could serve multiple scientific communities simultaneously, providing the broad survey data needed for planet hunting while also delivering the high-resolution measurements required for asteroseismology and other specialized fields of stellar physics. The 4-year primary mission, which stretched from May of 2009 until May of 2013 when the second reaction wheel failed, produced light curves for well over 150,000 individual stars, each light curve consisting of thousands upon thousands of individual brightness measurements taken over the course of those 4 years. If you were to print these light curves on paper, placing one star's measurements on each page, you would need a stack of paper reaching higher than a human being. And if you were to examine each page for just 1 minute, searching for the tiny dips that might indicate a transiting planet, you would need to work continuously for more than 100 days to review them all. The scale of this data collection was unprecedented in the history of exoplanet science, and it required entirely new approaches to data analysis. For no team of human researchers, however dedicated and numerous, could hope to examine every light curve with the careful attention it deserved. This challenge, the challenge of extracting meaning from an overwhelming abundance of data, would drive innovations in computational analysis that extended far beyond astronomy and into the broader world of machine learning and artificial intelligence. One of the most remarkable aspects of the Kepler mission was NASA's policy regarding the accessibility of its data. For after a brief initial proprietary period during which the science team had exclusive access to new observations, all of the mission's data was released to the public, freely available to any researcher at any institution anywhere in the world who wished to download and analyze it. This policy of open data access reflected a broader movement within the scientific community toward transparency and collaboration, a recognition that the greatest discoveries often emerge when many minds examine the same observations from different perspectives, applying different techniques and different insights to the same underlying measurements. A graduate student at a small university in Europe could access precisely the same data as a senior professor at a major American research institution, and a retired engineer with a passion for astronomy could examine the same light curves as a professional astronomer with decades of experience. And this democratization of access meant that discoveries could emerge from unexpected quarters, from researchers who brought fresh perspectives and novel approaches to familiar observations. The consequences of this open data policy became apparent quite quickly, as researchers around the world began downloading Kepler data and applying their own analytical techniques to the search for planets. And the discoveries that emerged from this distributed effort far exceeded what any single team could have accomplished alone. Years after certain observations were originally recorded, researchers would return to archival data and find planets that had been overlooked in earlier analyses, sometimes because the signals were too faint to be detected with older algorithms, sometimes because the planetary systems were unusual in ways that made them difficult to recognize with standard detection methods. The archive was not a static collection but a living resource, one that continued to yield new findings as analytical techniques improved and as researchers with new ideas brought fresh approaches to the accumulated measurements. A planet that was invisible to the analysis methods of 2010 might reveal itself clearly to the more sophisticated algorithms of 2015. And so the same observations could be examined multiple times over the years, each examination potentially revealing something that had been missed before. One particularly striking example of this phenomenon occurred in 2017. When a team of researchers at Google applied machine learning techniques to Kepler's archival data and discovered a previously undetected planet orbiting a star called Kepler 90. The neural network that made this discovery had been trained on a large collection of confirmed Kepler planets, learning to recognize the subtle patterns in brightness measurements that indicated a transiting world. And when it was set loose on the full Kepler dataset, it found what human analysts had missed: a small planet with an orbital period of about 14 days, tucked into a system that already held 7 known planets. This 8th planet, designated Kepler 90I, made the Kepler 90 system the first known planetary system with as many planets as our own solar system. And its discovery demonstrated the power of machine learning to find signals hidden within vast datasets, signals that might have remained undiscovered for years or decades if human researchers had been forced to examine every light curve individually. The success of this machine learning approach inspired numerous other efforts to apply artificial intelligence to astronomical data, and researchers at institutions around the world began developing neural networks and other algorithms capable of searching through Kepler's archive with superhuman speed and precision. These algorithms could examine millions of light curves in the time it would take a human researcher to study a few dozen, and they could detect patterns too subtle for human perception, variations in brightness that were buried beneath the noise of the measurements but which became visible when analyzed with the right computational techniques. The archive that had been assembled over Kepler's 9 years of operation thus became a testing ground for new approaches to data analysis, a resource that enabled not only new discoveries about distant worlds, but also new methods for extracting information from complex datasets, methods that would prove valuable in fields far removed from astronomy. The preservation and sharing of Kepler's data required careful attention to standardization, for the measurements would be useless if researchers could not reliably interpret the numbers and compare observations taken at different times or under different conditions. The file format adopted for Kepler's data products was the Flexible Image Transport System, known by its abbreviated name FITS, which had been developed by astronomers in the late 1970s and had become the standard format for astronomical data of all kinds. A FITS file consists of a header section containing detailed metadata about the observation, information such as the date and time of the measurement, the coordinates of the target star, the exposure duration, and dozens of other parameters that researchers need to properly interpret the data, followed by the actual numerical measurements themselves, arranged in tables or arrays that can be read by standard astronomical software. The adoption of this well-established format meant that researchers did not need to learn new tools or develop new software to work with Kepler data, for the same programs they had used to analyze data from other telescopes could read and process Kepler's light curves without modification. The standardization extended beyond file formats to include the calibration procedures applied to the raw data before it was released to the archive, for the measurements transmitted by the spacecraft required extensive processing to remove instrumental effects and convert them into scientifically meaningful brightness values. The Kepler pipeline, as this processing system was known, applied corrections for the varying sensitivity of different pixels on the detector, removed the effects of spacecraft motion and temperature variations, and flagged measurements that were likely to be contaminated by cosmic ray hits or other anomalies. The resulting calibrated light curves represented the best estimates of each star's true brightness at each observation time, cleaned of instrumental artifacts and ready for scientific analysis. And the consistency of this calibration across the entire dataset meant that researchers could compare measurements of different stars with confidence, knowing that any differences they observed reflected genuine astronomical phenomena rather than variations in how the data had been processed. The scientific community that coalesced around Kepler's observations extended far beyond the mission's official science team, encompassing researchers at hundreds of institutions and spanning nearly every subfield of stellar and planetary astronomy. To coordinate the efforts of this dispersed community and to support the ground-based observations that were essential for confirming and characterizing new planet candidates, NASA established the Kepler Community Follow-up Observing Program, which provided a framework for researchers to share information about their observations and to coordinate their use of telescopes around the world. When a new planet candidate was identified in the Kepler data, follow-up observations were often needed to confirm that the transit-like signal was indeed caused by a planet rather than by some other phenomenon such as a background eclipsing binary. And these confirmation observations required access to ground-based telescopes equipped with spectrographs capable of detecting the tiny wobble in the star's motion caused by the gravitational pull of an orbiting planet. The Community Follow-up Observing Program helped ensure that these precious telescope resources were used efficiently, preventing duplication of effort and allowing researchers to share their results so that others could build upon them. By the time Kepler's mission officially concluded, the scientific literature had been enriched by more than 2,800 peer-reviewed papers making use of the telescope's data, a number that continued to grow steadily in the years after the spacecraft fell silent, as researchers continued to mine the archive for new discoveries and new insights. These papers covered an astonishing breadth of topics, from the detection of individual exoplanets to broad statistical analyses of planetary demographics, from the detailed characterization of stellar oscillations to the study of eclipsing binary stars and the measurement of stellar rotation rates. Some papers focused on the development of new analytical techniques, describing algorithms for detecting transit signals or methods for removing systematic noise from light curves, while others presented theoretical models explaining the phenomena observed in the data. And still others discussed the implications of Kepler's findings for our understanding of planetary formation and the prevalence of potentially habitable worlds in the galaxy. The archive continues to serve the scientific community to this day, and new papers drawing upon Kepler data appear in astronomical journals with remarkable regularity, each one representing another small contribution to the great edifice of human knowledge about the universe beyond our solar system. Researchers continue to develop more sophisticated analytical techniques, and each improvement in methodology creates the possibility of new discoveries hiding within the same observations that have been studied countless times before. A transit signal that was too faint to detect with yesterday's algorithms may become clearly visible with tomorrow's more sensitive methods, and a planetary system that seemed to contain only 3 worlds may reveal additional companions when examined with more careful attention to the subtle variations in transit timing. The archive is patient, holding its treasures in perpetual readiness for the researchers who will eventually come to claim them. And the photons that were collected during those 9 years of observation continue to speak across the years, telling their stories to anyone who takes the time to listen. The data that streams silently through the servers at MAST, available for download at any hour of the day or night, represents something more than mere measurements of stellar brightness, for it carries within it the potential for discovery. The possibility that someone examining these numbers for the first time will notice something that everyone else has missed, a pattern that reveals a new world or a new phenomenon or a new understanding of how stars and planets behave. This potential is what gives an archive its true value. The recognition that the observations gathered today may answer questions that no one has yet thought to ask, that the data collected for one purpose may prove essential for investigations that the original observers could never have imagined. Kepler's designers understood this, and they took care to ensure that the mission's data would be preserved in forms that future researchers could use, employing standard formats and careful documentation so that the archive would remain accessible and interpretable for decades to come. And so the measurements continue to accumulate their citations, as one paper after another acknowledges its debt to the spacecraft that gathered this unprecedented collection of Starlight observations, and the archive grows more valuable with each passing year, as new analytical techniques make it possible to extract information that was previously inaccessible. The stars that Kepler observed continue to shine in their distant orbits around the center of the galaxy, and the planets that circle them continue their endless journeys, utterly unaware that their existence has been recorded in the magnetic patterns of servers on a small world 93 million miles from its own star. The data endures, a permanent record of a particular patch of sky during a particular span of years, and the discoveries that remain hidden within it await only the curiosity of researchers yet to come. Scientists who will bring new questions and new methods to these familiar observations and find within them answers that we cannot yet imagine. When Kepler found a candidate planet, when its photometer recorded that characteristic dimming in a star's light, the discovery was really only beginning. The spacecraft could tell us that something had passed in front of a distant sun, could measure how much light had been blocked and how long the transit had taken, but it could not, on its own, confirm with certainty that the dimming was caused by a planet. There were other possibilities, other astronomical configurations that could mimic the signature of a transiting world, and so the work of confirmation fell to telescopes here on Earth, to patient observers perched on mountaintops, gathering the additional evidence needed to transform a candidate into a confirmed planet. This was the confirmation problem, and solving it required a global effort, a collaboration of instruments and observers spanning continents and hemispheres, all working together to verify what Kepler had seen. The primary tool for this confirmation work was the radial velocity method, a technique that relies on the simple fact that planets do not merely orbit their stars but actually cause their stars to move as well. A star with a planet is not stationary. It wobbles, ever so slightly, tugged by the gravitational pull of its companion, and this wobble causes the star's light to shift in predictable ways. When the star moves toward us, its light is compressed slightly, shifted toward the blue end of the spectrum. When it moves away, the light stretches, shifting toward the red. By measuring these tiny shifts with extraordinary precision, astronomers can detect the presence of an unseen planet and, crucially, determine its mass. This mass measurement, combined with the size information from Kepler's transit observations, allows us to calculate a planet's density and begin to understand what it might be made of, whether rock or gas or something in between. The instrument that bore much of this burden, that served as the primary radial velocity confirmation tool for Kepler discoveries, was the HIRES spectrograph, mounted on one of the twin Keck telescopes atop Mauna Kea in Hawaii. HIRES stands for High Resolution Echelle Spectrometer, a name that describes its function with admirable directness. It takes starlight collected by the Keck telescope's enormous 10-meter mirror and spreads it into an exquisitely detailed spectrum, recording the precise wavelengths of thousands of absorption lines, the dark gaps in a star's rainbow where specific elements have absorbed specific colors of light. By tracking how these lines shift back and forth over time, HIRES can detect stellar wobbles with velocities of just a few meters per second, a sensitivity remarkable enough to reveal the gravitational influence of planets much smaller than Jupiter. The W.M. Keck Observatory itself occupies a special place in the history of exoplanet science, and its role in the Kepler mission only added to that legacy. Perched near the summit of Mauna Kea, at an elevation of nearly 14,000 feet, the observatory sits above much of Earth's turbulent atmosphere, in air that is thin and dry and remarkably stable. The mountain is sacred to native Hawaiians, who know it as a place where the realm of humanity meets the realm of the gods, and there is something fitting about using this high and quiet place to search for distant worlds. The twin Keck telescopes, with their segmented mirrors made of 36 hexagonal pieces working together as one, were for many years the largest optical telescopes on Earth, and their light-gathering power made them ideal for studying the faint stars in Kepler's field of view. Night after night, semester after semester, observers used HIRES to monitor Kepler's candidate host stars, returning to each target repeatedly to build up the measurements needed to detect a planetary wobble. A single radial velocity measurement tells you only where the star is at one moment. To confirm a planet, you need many measurements spread over time, enough to trace out the periodic back-and-forth motion as the planet completes its orbit. For a planet with a short orbital period, a few weeks of observations might suffice. For a planet in a longer orbit, you might need months or even years of patient monitoring. The observers kept their schedules and took their data and slowly, carefully, built the evidence needed for confirmation. Leading much of this early radial velocity follow-up work was Jeff Marcy, a researcher whose name had been synonymous with exoplanet discovery since the field's earliest days. Marcy and his longtime collaborator Paul Butler had been among the first to confirm the existence of planets around other Sun-like stars. And by the time Kepler launched, Marcy had discovered more exoplanets than any other living astronomer. His team at the University of California, Berkeley, worked closely with the Kepler science team, using Keck and HIAS to confirm many of the mission's most important early finds. Marcy brought decades of experience with radial velocity techniques, an understanding of the instrumental challenges and systematic effects that could complicate measurements, and his involvement lent credibility and momentum to the confirmation effort. His contributions to Kepler's success during those early years were substantial and widely acknowledged within the astronomical community. In 2015, however, Marcy's career came to an abrupt end when an investigation by the University of California found that he had violated campus sexual harassment policies in his interactions with students over many years. The revelations prompted his resignation from Berkeley and his effective departure from astronomy entirely. The community was left to grapple with the complicated legacy of a researcher who had contributed greatly to the science while also causing real harm to individuals who had trusted him as a mentor. The work continued without him, as scientific work always does, carried forward by the many other researchers who had been building the field alongside him. But the episode served as a reminder that the human institutions of science are not immune to the failings found in any human endeavor. The radial velocity confirmation effort was never limited to a single telescope or a single spectrograph. Across the Atlantic, on the island of La Palma in the Canary Islands, another instrument joined the campaign, HARP-SEN, the high-accuracy radial velocity planet searcher for the Northern Hemisphere, was installed on the Telescopio Nazionale Galileo specifically to support the characterization of transiting planet candidates from Kepler and, later, other transit surveys. HARP-SEN was the northern twin of HARPS, an instrument on the European Southern Observatory's telescope in Chile that had set records for radial velocity precision and discovered many planets of its own. By placing a similar instrument in the Northern Hemisphere, where it could observe the same patch of sky that Kepler was monitoring, the astronomical community gained a powerful new tool for follow-up work. HARP-SEN brought several advantages to the effort. Its design emphasized stability above all else, with the spectrograph housed in a vacuum chamber to eliminate the effects of changing air pressure and temperature controlled to fractions of a degree to prevent thermal expansion from shifting the optical elements. Light from the telescope was fed to the spectrograph through optical fibers, isolating the instrument from the mechanical flexure that plagues spectrographs mounted directly on moving telescopes. The result was an instrument capable of detecting stellar wobbles with velocities of just 1 meter per second or even less, a precision that opened the door to confirming ever smaller and lighter planets. HARP-SEN made particularly important contributions to the characterization of small planets in the habitable zones of their stars, the very worlds that Kepler had been designed to find. But radial velocity observations were not the only form of ground-based follow-up that Kepler candidates required. Before investing precious telescope time in lengthy spectroscopic campaigns, researchers needed to rule out the various false positive scenarios that could masquerade as planetary transits. One of the most common of these scenarios involves blended sources, situations where the light of the target star is contaminated by light from a nearby companion that Kepler's pixels could not resolve separately. If that companion happened to be an eclipsing binary star, a pair of stars orbiting each other and periodically blocking each other's light, the diluted eclipses could look remarkably like the transits of a small planet around the brighter target star. To address this problem, researchers employed high-resolution imaging techniques that could peer more closely at Kepler's target stars and reveal any nearby companions that might be contaminating the measurements. One particularly efficient tool for this work was RoboAO, the first robotic laser adaptive optics system, which operated initially on the Palomar Observatory's 60-inch telescope and later on other instruments. Adaptive optics is a technology that corrects for the blurring effects of Earth's atmosphere in real time, using deformable mirrors that change shape hundreds of times per second to counteract the twinkling that makes stars appear to dance and shimmer when viewed from the ground. By sharpening the images of Kepler's target stars, RoboAO could detect companion stars that would have been smeared into invisibility in ordinary seeing limited observations. The robotic nature of RoboAO made it particularly well suited to the Kepler follow-up challenge. With thousands of candidates to check, there was no practical way for human observers to examine each one individually using traditional adaptive optics systems, which require constant attention and adjustment. RoboAO could work through target lists automatically, acquiring each star, locking onto its laser guide star, recording its sharpened image, and moving on to the next target, all without human intervention. Over several years of operation, the system observed thousands of Kepler candidate host stars, building up a comprehensive catalogue of which targets had nearby companions and which appeared to be isolated. Similar high-resolution imaging work was conducted using speckle interferometry, a technique that takes many short exposures of a star and combines them mathematically to achieve resolution approaching the theoretical limit of the telescope's aperture. The WIYN telescope at Kitt Peak National Observatory in Arizona contributed significantly to this effort, with its speckle imaging program examining hundreds of Kepler targets to search for close stellar companions. Speckle imaging is particularly sensitive to companions at very small angular separations, the kinds of nearby stars that would fall within Kepler's photometric aperture and contaminate its measurements even if they were too close for conventional imaging to detect. Beyond checking for contaminating companions, there was also the important work of characterizing the host stars themselves. A transit observation tells you only the ratio of the planet's size to its star's size. So if you want to know the planet's actual radius in kilometers, you first need to know the star's radius with some precision. The same applies to other stellar properties. The mass of the star affects the interpretation of any radial velocity measurements. The temperature and luminosity of the star determine whether a planet at a given orbital distance receives enough warmth to maintain liquid water on its surface. To properly understand Kepler's planets, researchers needed to properly understand Kepler's stars. The California Kepler survey was a major effort to address this need, systematically observing and characterizing the host stars of Kepler's planet candidates. Using hires on the Keck telescope, the survey obtained high-resolution spectra of more than 1,000 Kepler host stars, analyzing the spectra to determine each star's temperature, surface gravity, and chemical composition with a precision and uniformity that had not been achieved by earlier, more piecemeal efforts. These improved stellar parameters propagated through to improved planetary parameters, refining our understanding of the sizes and characteristics of Kepler's worlds. The survey revealed, among other things, that many Kepler host stars were slightly larger than previously believed, which meant that their planets were slightly larger too, a finding that shifted some candidates out of the coveted Earth-sized category into somewhat larger classifications. The combination of transit observations from Kepler with radial velocity measurements from ground-based spectrographs yielded something particularly valuable: the mass-radius relationship for exoplanets. Kepler's transits gave you the planet size. The radial velocity wobble gave you its mass, and dividing mass by volume gave you the density, a quantity that tells you a great deal about what a planet is made of. Rocky worlds like Earth have densities around 5 grams per cubic centimeter, reflecting their composition of iron and silicate rock. Gas giants like Jupiter have much lower densities, around 1 gram per cubic centimeter, because they are made mostly of hydrogen and helium. By measuring the masses and radii of many planets across a range of sizes, researchers could map out how composition changes with planetary scale, identifying the transition region where worlds shift from rocky to gaseous and revealing an unexpected abundance of planets in a size range that has no counterpart in our own solar system. There was, however, a significant limitation to the radial velocity approach as applied to Kepler's discoveries. The precision of a radial velocity measurement depends fundamentally on how much light you can collect from the target star. Fainter stars yield noisier spectra with less well-defined absorption lines, making it harder to measure the tiny wavelength shifts that betray a planet's presence. And Kepler, by design, observed many stars that were quite faint, pushing to greater distances to accumulate the large sample needed to determine how common Earth-like planets really are. Most of Kepler's planet candidates orbit stars too faint for radial velocity confirmation with existing instruments, their host stars simply too dim to yield the precise spectroscopic measurements needed to detect the gravitational wobble of a small planet. This limitation meant that dynamical confirmation, the gold standard of proving a planet's existence by measuring its gravitational effect on its star, was simply not achievable for the majority of Kepler's candidates. A different approach was needed, and the astronomical community developed one. It came to be called statistical validation, and it represented a philosophical shift in how exoplanet discoveries were certified. Instead of proving definitively that a signal was caused by a planet, statistical validation asks what is the probability that any false positive scenario could have produced the observed signal. If that probability is sufficiently low, typically less than 1%, then the candidate is considered validated, accepted as a planet even without a direct measurement of its mass. Statistical validation works by systematically considering all the ways a transit-like signal could be produced without a planet being present and calculating how likely each scenario is given everything we know about the target star and its surroundings. It considers the probability of background eclipsing binaries falling by chance within Kepler's photometric aperture. It considers the probability of bound companion stars hosting eclipsing binaries or transiting planets of their own. It accounts for the high-resolution imaging that has ruled out companions above certain brightness limits at certain separations. It incorporates the statistics of the stellar populations in the Kepler field and the observed properties of the transit signal itself. When all these probabilities are combined, most genuine planet candidates emerge with false positive probabilities well below 1%, and researchers can state with high confidence that a given signal is indeed a planet. The development and acceptance of statistical validation was crucial to realizing Kepler's scientific potential. Without it, thousands of candidates would have remained in limbo indefinitely, perpetually awaiting radial velocity confirmation that could never come. With it, the astronomical community could confidently discuss the properties of validated planets, could include them in statistical analyses of planet occurrence rates, could build our understanding of planetary systems on a foundation of thousands of worlds rather than dozens. The technique was refined over many years by many researchers, tested against samples of candidates that could be confirmed by other means, and gradually accepted as a legitimate alternative to dynamical confirmation for cases where dynamical confirmation was impractical. Throughout all of this work, the international nature of the collaboration was essential. American observatories like Keck and WN contributed their unique capabilities. European facilities like HARPS-N on La Palma added their own strengths. Australian astronomers and observatories joined the effort as well, bringing their expertise in stellar characterization and their access to Southern Hemisphere facilities for related work. The Kepler mission was nominally a NASA project, built and operated by American institutions, but the scientific exploitation of its data was a global endeavor from the start. Researchers from different countries and different institutions shared data and techniques, critiqued each other's methods and improved upon them, and together built a confirmation and characterization program that no single observatory or national effort could have achieved alone. The telescopes on Mauna Kea watched Kepler's stars from Hawaii. The spectrographs on La Palma tracked their wobbles from the Canary Islands. The speckle cameras at Kitt Peak checked for hidden companions from Arizona. And meanwhile, Kepler itself continued to stare at that same patch of sky, recording transit after transit, building an ever larger catalogue of candidates for the ground-based observers to investigate. The confirmation problem was never truly solved in the sense of being eliminated. It remained a challenge throughout the mission and remains one today for other transit surveys. But the combination of radial velocity spectroscopy, high-resolution imaging, stellar characterization, and statistical validation allowed the community to transform Kepler's raw detections into confirmed and validated planets, into real worlds with measured sizes and estimated compositions, into data points that could answer the question Kepler had been built to address. Before Kepler, our understanding of how planetary systems were arranged came almost entirely from the one example we knew best, which was of course our own solar system, with its neat division between the small rocky worlds huddled close to the Sun and the massive gas giants orbiting at greater distances, all of them tracing out their paths in roughly the same flat plane, like marbles rolling around the inside of a vast shallow bowl. It seemed reasonable to imagine, in those early years of exoplanet discovery, that other planetary systems would follow similar patterns, that the architecture of our cosmic neighborhood represented something approaching a universal template, a standard blueprint that nature followed when constructing planetary systems around other stars. What Kepler revealed, through the patient accumulation of thousands upon thousands of planetary discoveries, was that our solar system is not particularly typical at all, and that the universe has been far more creative in its planetary arrangements than we had ever anticipated. Perhaps the most striking departure from our expectations came in the form of planetary systems that are packed far more tightly than anything we see around our own Sun. These configurations, which planetary scientists began calling tightly packed inner planetary systems, or sometimes simply SDIPs in the abbreviated language of scientific discourse, feature multiple planets crowded together in the region very close to their host stars, all of them completing their orbits in a matter of days or weeks rather than the months or years we associate with the inner planets of our own system. In some of these remarkable arrangements, you might find 4 or 5 planets, each of them larger than Earth but smaller than Neptune, all orbiting closer to their star than Mercury orbits our Sun. The planets in these compact systems are often separated by remarkably small distances, their orbits nested together like the rings of a target, each one just far enough from its neighbors to maintain gravitational stability over billions of years. The prevalence of these tightly packed systems came as something of a surprise, because the processes of planet formation, as we understood them before Kepler, did not seem particularly well suited to creating such crowded arrangements. The traditional picture of planetary accretion suggested that planets would form at wider intervals, cleared zones emerging in the disk of gas and dust as each growing protoplanet swept up the material in its vicinity. Yet here was Kepler, finding system after system where planets had somehow managed to form in close proximity and remain there, their orbits stable and orderly despite the cramped quarters. This discovery prompted a wholesale re-examination of our theories about how planets migrate through their systems during and after formation, and about how the delicate gravitational interactions between neighboring worlds can settle into configurations that persist for the entire lifetime of their star. One of the more puzzling patterns to emerge from the Kepler data was what researchers came to call the Kepler dichotomy, a curious observation about the distribution of planets among different stellar systems. When astronomers analyzed the statistics carefully, they found that the population of stars could be roughly divided into 2 groups: those that host multiple detectable planets and those that appear to host just one or perhaps none at all. This might seem like an obvious and unremarkable distinction, but the puzzle lay in the proportions and the sharpness of the divide. If planetary systems were distributed smoothly across a spectrum, with some having many planets and others having fewer, you would expect to see a gradual decline in the number of systems as you moved from higher to lower planet counts. Instead, the data suggested something more like 2 distinct populations, as if stars had to choose between being planet-rich or planet-poor, with relatively few occupying the middle ground. Various explanations have been proposed for this dichotomy, and the true answer likely involves a combination of factors. Some researchers suggested that the difference might be one of geometry rather than actual planetary abundance, that systems with single detected planets might actually harbor additional worlds, whose orbits are tilted at angles that prevent them from transiting across the face of their star as seen from Kepler's vantage point. Others proposed that the dichotomy reflects genuine differences in the planet formation process, perhaps related to the initial conditions in the protoplanetary disk or to the early dynamical history of the system, with some environments fostering the creation of multiple stable planets while others lead to more chaotic outcomes where planets collide or are ejected, leaving behind a solitary survivor or an empty system. The resolution of this puzzle remains an active area of research, but the observation itself stands as one of the more intriguing architectural patterns that Kepler uncovered. The question of orbital geometry, of how planetary orbits are oriented in 3-dimensional space, proved to be another area where Kepler provided valuable insights. Through careful analysis of multi-planet systems where several worlds were observed to transit, astronomers could place constraints on how closely aligned the orbital planes of different planets must be. If the planets in a system orbited in wildly different planes, at steep angles to one another like the spokes of a wheel, then the likelihood of multiple planets all transiting as seen from any particular viewing angle would be extremely small. The fact that Kepler found so many systems with multiple transiting planets implied that the orbital planes in these systems must be quite well aligned, that most multi-planet systems are flat, with their worlds orbiting in nearly the same plane, much as the planets of our own solar system do. These mutual inclination studies, as they came to be known, revealed that the typical dispersion in orbital angles within a multiplanet system is only a few degrees, a finding that has important implications for theories of planet formation and subsequent dynamical evolution. A flat, well-aligned planetary system suggests a relatively quiescent history, a system that formed from a coherent disk of material and then evolved without the violent gravitational upheavals that might have scattered planets into tilted or chaotic orbits. The prevalence of flat systems among Kepler's discoveries suggests that such calm histories are common, though there are certainly exceptions. Systems where gravitational interactions or past encounters with passing stars have left the orbital planes in disarray. Turning from the angles of orbits to their shapes, Kepler also provided new information about the eccentricity distribution of exoplanets, which is to say how circular or elliptical their orbits tend to be. In our own solar system, the planets follow paths that are very nearly circular, with only slight elongation to their ellipses, and this has generally been taken as evidence of a settled, mature system that has had billions of years to shed any initial orbital energy and settle into stable configurations. Before Kepler, the population of known exoplanets, discovered largely through the radial velocity method, seemed to include a higher proportion of eccentric orbits, worlds on elongated paths that carried them much closer to their star at some points than at others. This raised the question of whether such eccentric orbits might be the norm throughout the galaxy, with our own circular planetary paths representing an unusual case. Kepler's transit observations, combined with follow-up studies using other techniques, helped to clarify this picture by showing that the true eccentricity distribution depends quite strongly on the type of planetary system being considered. Among the tightly packed systems with multiple small planets orbiting close to their stars, circular or nearly circular orbits predominate, which makes sense because highly eccentric orbits in such crowded systems would quickly lead to gravitational instabilities and collisions. Among the giant planets orbiting at greater distances, a wider range of eccentricities is observed, including some quite elongated orbits, perhaps reflecting the more violent dynamical histories that larger planets can undergo. The overall lesson seemed to be that nature produces a range of orbital shapes, but that the most common architectures, the ones featuring multiple small planets in close orbits, tend toward circularity and stability. Another pattern that emerged from the Kepler data, one that continues to fascinate planetary scientists, is the phenomenon of intrasystem uniformity, sometimes described colloquially as the peas in a pod observation. When researchers examined the sizes of planets within individual multiplanet systems, they found a striking tendency for siblings to resemble one another. In systems with multiple small planets, the planets tend to cluster around similar sizes, as if they were drawn from the same family. In systems featuring larger worlds, the planets again tend toward similar dimensions. It is as though each planetary system has a characteristic scale for its planets, a preferred size that the formation process establishes and that most of the planets then conform to. This uniformity extends beyond just size to include the spacing between orbits, with the gaps between adjacent planets also showing a tendency toward regularity within individual systems. The spacing is often described in terms of mutual Hill radii, a measure that accounts for the gravitational influence of each planet, and within a given system these spacing intervals tend to be more similar than would be expected by chance. This ordered, almost regimented character of many planetary systems suggests that the formation process imposes some kind of coherent structure, perhaps through the physics of the protoplanetary disk or through subsequent gravitational interactions that preferentially preserve evenly spaced configurations. Kepler also contributed to our understanding of how the properties of host stars influence the types of planets that form around them, and one of the clearest correlations to emerge involves stellar metallicity, which astronomers use to describe the abundance of elements heavier than hydrogen and helium in a star's composition. These heavy elements, forged in the cores of earlier generations of stars and dispersed into space when those stars died, form the raw materials from which rocky planets and the cores of gas giants are constructed. Stars with higher metallicity, those that formed from gas clouds enriched with more of these heavy elements, were already known to be more likely to host hot Jupiters, the massive close-orbiting gas giants that were among the first exoplanets discovered. Kepler's observations extended and refined this correlation, confirming that metal-rich stars are indeed more likely to host gas giant planets of all types, not just the hot ones, while the occurrence of smaller rocky planets shows a weaker dependence on metallicity, suggesting that the threshold of heavy elements needed to form an Earth-sized world is lower than that required to build a Jupiter. Among the more tentative findings to emerge from the Kepler data is evidence suggesting that the occurrence of planets may be somewhat lower around binary star systems, those systems where two stars orbit a common center of mass. While Kepler did discover circumbinary planets, worlds that orbit around both stars of a binary pair, the overall statistics suggested that such planets might be less common than planets around single stars. This is perhaps not surprising from a theoretical standpoint, as the gravitational environment of a binary system is more complex, with the two stars creating a shifting gravitational landscape that might make planet formation more difficult or might destabilize planetary orbits over time. However, the evidence remains somewhat preliminary, and the detection of planets in binary systems presents additional observational challenges that make firm conclusions difficult to draw. Stepping back from the details of individual planetary architectures, one of Kepler's most profound contributions was simply to establish that planets are extraordinarily common throughout our galaxy. Before Kepler, we knew of a few hundred exoplanets, found through painstaking observations of nearby stars, and while this suggested that planets were not rare, the true frequency remained uncertain. Kepler's survey, by watching a fixed patch of sky and detecting planets through their transits, allowed astronomers to perform rigorous statistical analyses and to conclude with confidence that planets are the rule rather than the exception. Virtually every star in the sky, or very nearly so, can be expected to host at least one planet, and many host multiple worlds. The galaxy contains billions upon billions of planets, a number so large that it transforms our understanding of our cosmic environment and our place within it. These statistical insights, drawn from the accumulated weight of Kepler's observations, prompted what can fairly be described as a revolution in planet formation theory. Before Kepler, theorists had constructed models of planet formation that were designed primarily to explain our own solar system, with its particular arrangement of planets, its asteroid belt, its Kuiper belt, its division between inner rocky worlds and outer giants. These models did a reasonable job of accounting for the features of our system, but they were not well tested against other examples because so few other planetary systems were known. Kepler changed that by providing thousands of examples spanning a wide range of architectures, and the existing theories were often found wanting. The prevalence of super-Earths and sub-Neptunes, the existence of tightly packed systems, the P's inner pod uniformity, the Kepler dichotomy, All of these observations required theoretical explanations that the older models had not anticipated. In response, planet formation theory underwent considerable revision and expansion. New mechanisms were proposed, existing mechanisms were re-evaluated, and the relative importance of different processes was reconsidered. The role of planetary migration, the movement of planets through the disk during and after formation, came to be seen as more central and more varied than previously appreciated. The conditions in protoplanetary disks, the initial masses and compositions and density profiles, were recognized as sources of diversity that could lead to very different outcomes for different systems. The interplay between planet formation and disk evolution, the timing of when planets reach particular sizes relative to when the gas in the disk disperses, emerged as a critical factor in determining final architectures. In all of these ways, Kepler data served as both a challenge and a guide, pushing theorists toward models that could account for the true diversity of planetary systems rather than merely replicating the single example we had known before. And so, from this one small spacecraft, staring patiently at a patch of sky in the constellations of Cygnus and Lyra, came a transformation in our understanding of how planetary systems are built and how they are arranged. The architecture of worlds around other stars proved to be far more varied and in some ways far more regular than anyone had anticipated, with patterns and correlations that continue to inform and constrain our theories. Our own solar system remains a fascinating place, worthy of all the attention we give it, but it is now understood to be just one example among countless billions, one particular outcome of processes that can lead to many different arrangements, each stable, each enduring, each orbiting quietly around its star in the long night of interstellar space. In the spring of 2016, the Kepler spacecraft experienced what mission controllers would formally classify as a spacecraft emergency, though to understand what occurred requires first appreciating how very far from Earth the telescope had traveled by this point in its extended mission, and how the vast distance separating the spacecraft from its human caretakers meant that any problem, however small, carried with it a particular weight of uncertainty that closer missions simply do not experience. On the 7th of April, during what was designated Campaign 9 of the K2 mission, ground controllers at the Laboratory for Atmospheric and Space Physics in Boulder, Colorado, attempted to establish their regular contact with the spacecraft, and found instead that Kepler had entered a protective state known as emergency mode, which is the lowest operational mode a spacecraft can enter while still remaining functional, and which indicated that something had gone significantly wrong in the hours or days since the previous communication. The spacecraft, trailing behind Earth in its orbit around the Sun at a distance of approximately 120 million kilometers at that time, had detected some anomaly in its own systems and had responded by placing itself into this emergency configuration, which prioritized the most basic functions of survival over all scientific operations. In emergency mode, the spacecraft would orient its solar panels toward the Sun to maintain power, and it would broadcast a simple signal indicating its distressed state, and it would wait, in a sense, for instructions from home. The difficulty was that at such tremendous distances, even light itself takes time to travel, and radio signals sent from Earth to Kepler required approximately 13 minutes to arrive, with another 13 minutes required for any response to return, meaning that every exchange of information involved a round-trip delay of more than 26 minutes. Which transforms troubleshooting into a slow and patient exercise quite unlike the rapid-fire diagnostics one might perform on earthly equipment. The engineers and mission controllers who gathered to address this emergency worked through what must have been a tense 14 hours, though their approach remained methodical and careful, as is always the case with spacecraft operations, where hasty decisions can transform recoverable problems into permanent failures. They sent commands and waited for responses, analyzed the data that returned, formulated hypotheses about what might have caused the emergency mode entry, and sent further commands to test their theories and attempt recovery. The specific cause of the emergency mode entry was investigated thoroughly in the weeks that followed, and while the precise trigger remained somewhat uncertain, the spacecraft was successfully recovered and returned to normal operations, and Campaign 9 was able to proceed after the interruption, though some observations were inevitably lost during the hours when the telescope was focused solely on its own survival rather than on the distant stars it had been built to study. This emergency served as a reminder of the spacecraft's age and the accumulating uncertainties that came with operating a machine far beyond its intended lifespan, and it brought renewed attention to a concern that had quietly accompanied the extended mission from its very beginning, which was the question of how much fuel remained in Kepler's tanks. The spacecraft carried a supply of hydrazine fuel when it launched in 2009, and this fuel was essential for the attitude control maneuvers that allowed the telescope to point precisely at its targets and to perform the regular adjustments required by the K2 mission's campaign-based observing strategy. Unlike automobiles, which possess fuel gauges that allow drivers to monitor their tanks with reasonable precision, and unlike many modern spacecraft that incorporate sophisticated fuel measurement systems, Kepler was designed with no direct means of determining how much hydrazine remained in its tanks at any given moment. This absence of a fuel gauge was not an oversight but rather a consequence of the mission's original design philosophy and the engineering trade-offs that are inevitable in spacecraft construction, where every instrument and sensor adds weight, complexity, cost, and potential points of failure, and where the original mission plan called for a relatively straightforward operational profile that would consume fuel at predictable rates over the planned 3.5-year primary mission. The designers had calculated how much fuel would be needed, had included appropriate margins for contingencies, and had not anticipated that the spacecraft would still be operating nearly a decade after launch, by which time the cumulative uncertainties in fuel consumption estimates would have grown substantial. Engineers monitoring the mission could estimate fuel levels based on the history of thruster firings and the known fuel consumption rates for various maneuvers, but these estimates carried error bars that grew wider with each passing year, and by the later stages of the K2 mission, the honest answer to the question of how much fuel remained was something along the lines of probably very little, but we cannot say with certainty exactly how little. The spacecraft continued its work through Campaign 10 and Campaign 11, and onward through the following years, with each successive campaign adding to the scientific harvest while drawing down the finite reserves that kept the telescope functional. The mission team developed increasingly sophisticated techniques for managing the fuel situation, finding ways to reduce the frequency and intensity of thruster firings where possible, and accepting that each campaign might potentially be the last. This uncertainty created a particular emotional texture for everyone involved with the mission, where the satisfaction of continued scientific success was accompanied by the knowledge that the end could come at any time, not through any dramatic failure but simply through the quiet exhaustion of a consumable resource. Campaign 19 began on the 6th of August in 2018, and by this point the fuel situation had become acute, with estimates suggesting that only the barest traces of hydrazine remained in the spacecraft's tanks. The mission team proceeded with what they knew might well be the final observing campaign, pointing the telescope toward a region of sky that would yield valuable data while accepting that the observations might be interrupted at any moment. The spacecraft performed its duties faithfully through the following weeks, gathering photometric measurements of distant stars with the same precision and dedication it had demonstrated throughout its nearly decade-long career, even as the fuel that enabled this work dwindled toward exhaustion. On the 25th of September, 2018, mission controllers sent commands that placed Kepler into a sleep mode configuration, which was a deliberate decision to suspend scientific observations in order to preserve what little fuel might remain for the eventual transmission of the data the spacecraft had collected during Campaign 19. This choice reflected a fundamental principle of robotic space exploration, which is that the value of observations lies not in the act of making them but in the successful return of the resulting data to Earth, where scientists can analyze and interpret and publish and share what the spacecraft has learned. A telescope that makes beautiful observations but fails to transmit them home before losing power or functionality has, in a meaningful sense, observed nothing at all. And so the decision to stop observing in order to prioritize data transmission was a sound and responsible one, even though it meant accepting that Kepler's days as an active observer had come to an end. The spacecraft remained in this sleep mode through the following weeks, awakening periodically to transmit portions of its stored data back to Earth, where the Deep Space Network's large antenna dishes collected the faint signals and forwarded them to the Mission Operations Center. These data transmission sessions themselves required fuel, as the spacecraft needed to maintain its orientation toward Earth with reasonable precision, and so each download represented a small but measurable deduction from the remaining reserves. The mission team monitored these transmissions carefully, watching for any signs that the fuel was finally depleted, knowing that when the hydrazine was gone, the spacecraft would lose its ability to point itself, and its antenna would drift away from Earth, and the radio link that had connected Kepler to its creators for nearly a decade would be permanently severed. The announcement came on the 30th of October, 2018, when NASA publicly confirmed that the Kepler Space Telescope had exhausted its fuel supply and could no longer continue operations. The spacecraft had been checked on the previous week and had shown signs of running on the very dregs of its hydrazine, and subsequent contacts confirmed that the fuel was effectively depleted and that no further scientific operations or data transmissions would be possible. The mission, which had begun with such hopeful aspirations in 2009 and had exceeded every reasonable expectation in the years that followed, had reached its natural and inevitable conclusion, not through any failure or accident but simply through the exhaustion of a finite resource after years of extraordinary service. The final act of the Kepler mission came on the 15th of November, 2018, when mission controllers transmitted what they termed good-night commands to the spacecraft. These commands, sent across the vast distance separating Earth from the telescope's location in its heliocentric orbit, instructed the spacecraft to disable its transmitters and enter a permanent safe mode from which it would never be awakened. The decision to send these commands was both practical and symbolic, as a spacecraft with no fuel and no ability to transmit data serves no operational purpose, and the radio spectrum is a shared resource that should not be occupied by defunct equipment, and there was something fitting about allowing Kepler to cease its transmissions deliberately rather than simply fading into silence through malfunction or drift. The good-night commands traveled through space at the speed of light, covering the enormous distance in a matter of minutes, and were received by the spacecraft's antenna, and were processed by its onboard computer, and were executed faithfully, as Kepler had executed so many thousands of commands before. The transmitters that had sent data back to Earth throughout the mission fell silent, and the spacecraft's radio voice, which had carried so much precious information across such vast distances, was heard no more. The telescope itself, with its 95-megapixel camera and its carefully polished primary mirror, remained physically intact, still pointed in whatever direction it had last been oriented, still orbiting the Sun in the same path it had followed since launch, but now silent and unreachable, a small artificial object drifting through the solar system with no one to talk to and no one listening for its voice. The orbit in which Kepler now rests, and in which it will remain for the foreseeable future, is a heliocentric orbit that trails behind Earth as our planet makes its annual journey around the Sun. This orbit was chosen for the original mission because it provided a stable thermal environment and freedom from the gravitational perturbations that would have affected an Earth-orbiting telescope. And it placed Kepler in a dark region of space where scattered sunlight would not interfere with its sensitive observations. The consequence of this orbital choice is that Kepler drifts further from Earth with each passing year, receding into the distance at a rate of roughly 15 million kilometers annually, so that by now the spacecraft is considerably further from us than it was when the mission ended. And in the centuries and millennia to come it will continue to recede until it becomes, in effect, just another small body orbiting the Sun in the inner solar system, indistinguishable to distant observers from the countless other rocks and fragments that share this region of space. The total operational lifespan of the Kepler mission, measured from launch on the 7th of March, 2009, to the official end of operations in late October of 2018, amounted to 9 years, 7 months, and 23 days, which exceeded the original design life of 3.5 years by a factor of nearly 3. This extraordinary longevity was a testament to the quality of the spacecraft's construction, to the skill and dedication of the mission operations team, to the clever engineering that extended the mission even after the failure of the second reaction wheel, and to a certain measure of good fortune that allowed the telescope to avoid the various mishaps that can befall spacecraft operating far from home in the harsh environment of space. The mission had been designed to answer a specific scientific question, which was whether Earth-sized planets in the habitable zones of Sun-like stars were common or rare. And it had answered that question definitively, finding that such planets were indeed abundant. And in doing so, it had transformed humanity's understanding of the cosmos in ways that will echo through astronomical research for generations to come. Over the course of its primary mission and its extended K2 campaign, the Kepler Space Telescope observed a total of 530,506 stars, each one examined with the patient precision that the transit method demands, each one checked repeatedly for the tiny dimming that would indicate the passage of a planet across its face. Of these hundreds of thousands of stars, several thousand yielded confirmed or candidate planets, a harvest of alien worlds that dwarfed all previous discoveries combined and that provided the statistical foundation for understanding planetary systems throughout the galaxy. The data collected by Kepler continues to be analyzed by researchers around the world, and new planet discoveries from the Kepler dataset continue to be announced years after the spacecraft fell silent, as improved analysis techniques extract ever more information from the observations the telescope made during its years of operation. William Borucki, the principal investigator who had championed the Kepler mission concept for more than 2 decades before it finally received approval, retired from NASA's Ames Research Center in 2015, 3 years before the mission's final commands were sent. His retirement came at a point when the mission's success was already assured, when the primary mission had been completed and the K2 extended mission was demonstrating that the spacecraft still had valuable science to contribute, when the question he had spent his career trying to answer had been answered in the affirmative, with Earth-sized planets in habitable zones found to be common throughout the galaxy. He had proposed the mission concept in the early 1980s, had persisted through 4 rejections by NASA's review process, had refined the design and built the necessary technological demonstrations and advocated tirelessly for the scientific importance of the work, and had ultimately seen his vision realized in a mission that exceeded all expectations. There is something peaceful in contemplating the final state of the Kepler spacecraft, drifting silently in its orbit around the Sun, carrying within its structure the 95-megapixel camera that stared at distant stars for so many years, the primary mirror that gathered the faint light of hundreds of thousands of suns, the computers and electronics that processed the observations and transmitted them home, all now silent and dark but physically preserved in the cold vacuum of interplanetary space. The telescope will remain in its orbit essentially unchanged for millions of years, slowly drifting away from Earth but never leaving the solar system, a permanent memorial to the scientific curiosity that built it and launched it and operated it through nearly a decade of discovery. The fuel that constrained the mission's length was, in the end, simply a practical limitation of the sort that affects all human endeavors, a reminder that even our most sophisticated technological achievements operate within boundaries set by physics and engineering and the finite resources we can afford to carry into space. But within those boundaries, Kepler accomplished everything its designers had hoped and considerably more, answering questions that humans had asked for centuries, providing data that will support scientific research for decades to come, and inspiring future missions that will build upon its legacy and extend its discoveries into ever greater detail. The spacecraft sleeps now in its distant orbit, its work complete, its transmitters silent, its mission accomplished, and the stars it watched continue to shine, many of them now known to host worlds that were unsuspected before Kepler turned its patient gaze upon them. And now we come to the part of our story where we might simply sit with the numbers, letting them settle around us like leaves drifting slowly to the ground on a still autumn afternoon. Because there is something rather soothing about statistics when they are presented without urgency, when we allow ourselves to receive them as gifts of knowledge rather than demands upon our attention. And the numbers that emerged from the Kepler mission are, in their quiet way, some of the most significant figures ever compiled in the history of human inquiry into the cosmos, though we shall take our time with them, turning each one over gently like a smooth stone found on a beach, appreciating its weight and texture before moving on to the next. When the Kepler science team released their final catalogue, the one that represented the culmination of all those years of patient observation and careful analysis, the tally of confirmed exoplanets stood at 2,662, and this number, which we might write out as 2,662 if we were making a note of it in a journal, represents individual worlds, each one a sphere of matter orbiting a distant sun, each one with its own particular characteristics of size and orbital period and distance from its host star. And though we cannot visit these worlds, cannot stand upon their surfaces or feel whatever winds might blow across them, we know that they exist, and we know quite a lot about them, because a small telescope with a very good camera stared at their stars for years and noticed the tiny diminishments of light that revealed their presence. But the confirmed planets are only part of the story, for the Kepler data also contains evidence of an additional 2,900 or so candidates, worlds that the algorithms flagged as likely planets but which have not yet been verified through the additional observations and analyses required to move a candidate from the status of probable to the status of confirmed. And these candidates, numbering more than 2,900 at the time the mission concluded, represent a kind of treasure chest of potential discoveries still waiting to be fully opened. Though scientists continue to work through this backlog even now, years after the telescope itself fell silent, gradually confirming more and more of these candidates as genuine planets, while occasionally determining that some were false positives caused by other astrophysical phenomena. And the work goes on, unhurried and methodical, much like the mission itself. If we add together the confirmed planets and the candidates, we find ourselves with a number exceeding 5,500 potential worlds detected by a single instrument looking at a relatively small patch of sky. And this is where the statistical reasoning becomes particularly interesting, because the Kepler field of view represented only about 1/400th of the entire celestial sphere, a tiny window onto the galaxy. And yet it revealed such an abundance of planets that scientists could begin to make reasonable extrapolations about the total planetary population of our Milky Way, applying the detection rates and occurrence frequencies derived from Kepler data to the galaxy as a whole. And when they did this, they arrived at a conclusion that would have seemed almost preposterous to astronomers of earlier generations. The calculation, performed with appropriate care and statistical rigor, suggested that there are more planets than stars in our galaxy, which is to say that the average number of planets per star is greater than 1. And since the Milky Way contains somewhere between 100 billion and 400 billion stars depending on which estimates one prefers, this means that the total number of planets in our galaxy likely exceeds even the upper bound of that stellar count. And we might pause here for a moment, letting that thought settle, because it represents such a profound shift from the way humanity once understood its place in the universe, when planets were rare exceptions rather than cosmic commonplaces, when our own solar system seemed a remarkable quirk rather than a fairly typical arrangement. And now, thanks largely to Kepler, we understand that planets are everywhere, that they form readily and frequently around the stars that condense from clouds of gas and dust, that they are, in a sense, the natural outcome of the processes by which stars themselves come into being. Among the most significant statistical results to emerge from the Kepler mission is the one that scientists refer to as Eta-Earth, a term that sounds rather technical but simply represents an estimate of how many stars similar to our own Sun might host planets similar in size to our own Earth within the region known as the habitable zone, where temperatures might permit liquid water to exist on a planetary surface. And the estimates derived from Kepler data suggest that this fraction lies somewhere between 10 and 20%, meaning that if we were to examine 100 Sun-like stars, we might expect to find between 10 and 20 of them orbited by Earth-sized planets at distances compatible with the existence of liquid water. And this is, when one considers it carefully, a rather generous fraction, suggesting that worlds potentially suitable for life as we understand it are not vanishingly rare but relatively common throughout the galaxy. Taking this Eta-Earth estimate and applying it to the full population of Sun-like stars in the Milky Way yields a number that is frankly difficult to hold in one's mind all at once, for the extrapolation suggests that there are roughly 300 million potentially habitable planets in our galaxy alone, 300 million worlds where the conditions might be right for liquid water and perhaps, on some of them, for the chemistry that leads to life. And though we must be careful not to overinterpret this number, recognizing that a planet in the habitable zone is not guaranteed to actually be habitable, that many factors beyond mere distance from a star determine whether a world can support life, the figure nonetheless represents a profound statement about the architecture of our galaxy, suggesting that Earth-like planets are scattered throughout the stellar population in numbers almost too large to comprehend. And somewhere out there, under the light of other suns, some of these worlds may harbor their own versions of oceans and atmospheres and perhaps, on some of them, processes that we might recognize as living. The Kepler data also revealed something important about the size distribution of planets, showing that small planets vastly outnumber large ones, which is perhaps not surprising from a theoretical standpoint since smaller objects generally form more easily than larger ones. But it was nonetheless gratifying to have this intuition confirmed by actual observations. And the distribution curve shows a steep increase as one moves from giant planets like Jupiter and Saturn down through Neptune-sized worlds, and further down to super-Earths and finally to Earth-sized planets and smaller, with the smallest detectable worlds being far more numerous than their larger counterparts. And this finding has implications for our understanding of planetary formation, suggesting that the processes by which dust and gas aggregate into solid bodies tend naturally to produce many small worlds for every large one. And it also means that the galaxy is likely teeming with rocky planets of modest size, worlds that might have solid surfaces and thin atmospheres, worlds that might, in their essential character, resemble the one on which we live. When scientists examined the host stars of the planets detected by Kepler, they found that roughly 70% of the stars in the Kepler field of view were M-dwarfs, which are the smallest and coolest and most common type of star in the galaxy. Stars that burn their nuclear fuel slowly and can persist for trillions of years, far longer than our own Sun will endure. And these M-dwarfs proved to be just as likely to host planets as larger stars, meaning that the most numerous stars in the galaxy are also planet-bearing stars. And since M-dwarfs make up perhaps 3/4 of all the stars in the Milky Way, this finding has significant implications for the total planetary census, suggesting that billions upon billions of planets orbit these dim red stars that are invisible to the naked eye but that populate the galaxy in vast numbers. And some of these M-dwarf planets lie within their host stars' habitable zones, though the habitable zone of an M-dwarf is much closer to the star than Earth is to the Sun, meaning that such planets would likely be tidally locked with one face perpetually turned toward their star, which presents interesting challenges for potential habitability but does not necessarily preclude it. As a byproduct of its planet hunting activities, Kepler also compiled an extensive catalogue of eclipsing binary stars, systems in which two stars orbit each other in such a way that they periodically pass in front of one another as seen from Earth, causing the same kind of brightness variations that Kepler was designed to detect from transiting planets. And the final count of these eclipsing binary systems stood at 3,279, making it one of the largest and most precise catalogues of such systems ever assembled. And this catalogue has proven valuable to astronomers studying stellar evolution and stellar structure, because eclipsing binaries provide one of the best ways to measure stellar masses and radii with precision. And so Kepler contributed significantly to astrophysics beyond the specific domain of exoplanet research, its steady gaze revealing not only planets but also the intricate gravitational dances of paired stars throughout its field of view. During the K2 mission, after the secondary action wheel failed and the telescope was reborn as an ecliptic scanning observatory, Kepler detected more than 60 supernovae, stellar explosions marking the violent deaths of stars either through core collapse at the end of massive stellar lifetimes or through thermonuclear detonation on white dwarf surfaces that had accumulated too much material from companion stars. And these supernova observations were particularly valuable because Kepler was able to capture the very early phases of the explosions, the first hours and days of brightening that are often missed by surveys that observe each patch of sky less frequently. And this early-time data provided insights into the physical processes driving the explosions, the shock waves propagating through stellar envelopes, the radioactive heating that powers the subsequent glow. And so the telescope that was built to find planets ended up contributing to our understanding of how certain stars die, a reminder that scientific instruments often yield discoveries beyond their original design parameters, that the universe has a way of revealing unexpected gifts to those who take the time to look carefully. From an economic perspective, The Kepler mission cost approximately $600 million over its lifetime, including development, launch, operations, and data analysis. And if we divide this figure by the number of confirmed planets discovered, we arrive at a cost of roughly $226,000 per planet, which is, in the context of space exploration, a remarkably efficient investment, comparable in some ways to the per-unit cost of discovering new species in biological surveys or mapping new territories in geographic expeditions. And while some might question whether any amount of money is well spent on discovering distant worlds we cannot visit, others would point to the profound value of pure scientific knowledge. The way that understanding our place in the cosmic context enriches human culture and inspires future generations of scientists and engineers. And the technology and expertise developed for Kepler have fed into subsequent missions and commercial applications, creating ripple effects that are difficult to quantify but undoubtedly real. Perhaps the most striking statistic of all is the simple comparison between Kepler's planet count and those of all other detection methods combined. For at the time the primary mission concluded, Kepler had discovered more exoplanets than all the radial velocity surveys and direct imaging programs and microlensing experiments and ground-based transit searches had managed to find in all the years before it, more than doubling the total number of known worlds beyond our solar system in a single stroke. And this comparison speaks to the power of the transit method when implemented with Kepler's precision and persistence. The ability of a well-designed space telescope to survey huge numbers of stars simultaneously and catch the faint shadows of orbiting worlds. And while other methods continue to make important discoveries and to characterize planets in ways that Kepler could not, the sheer numerical achievement of the mission remains unmatched. A census of distant worlds that transformed exoplanet science from a field of rare individual discoveries to one of population statistics and demographic analysis. These numbers, taken together, paint a picture of a galaxy rich with worlds. A cosmos in which planets are perhaps as common as the stars themselves. And this picture emerged over the 9 years of Kepler's operation, gradually coming into focus as the data accumulated and the analyses matured, revealing a universe far more populated with potential homes for life than earlier generations could have imagined. And while we must be careful not to assume that abundance implies habitability, that the presence of Earth-sized planets in habitable zones means that life is common, the statistics nonetheless provide a foundation for hope, a suggestion that the conditions necessary for life are not confined to our one small world but may be replicated across hundreds of millions of planets in our galaxy alone. And this knowledge, this statistical legacy of the Kepler mission, represents one of the great intellectual achievements of our species, a careful accounting of distant worlds performed with patience and precision over nearly a decade of observation. As we prepare to move on to other aspects of the Kepler story, we might take a moment to appreciate the peculiar satisfaction of these numbers. The way they reduce the immense complexity of a space mission and its discoveries to figures that can be written on a single page. 2,662 confirmed planets, 2,900 candidates, 300 million potentially habitable worlds in the galaxy, 70% M-dwarfs, 3,279 eclipsing binaries, 60 supernovae, $600 million. And yet these numbers, for all their apparent simplicity, contain within them stories of individual worlds and stellar systems, of patient scientists and careful engineers, of years of observation and analysis, and they point toward a universe far richer and more interesting than the sterile emptiness that some once imagined. A universe in which planets form readily around stars of all types, in which worlds suitable for life may number in the hundreds of millions within our own galaxy, and in which the question of whether we are alone has been transformed from philosophical speculation into a problem that admits of scientific investigation. And so we rest with these numbers, letting them settle into our understanding like sediment drifting slowly to the floor of a calm and quiet pond. And so we come now to what followed, to the telescopes and instruments that rose up in the years after Kepler fell silent, carrying forward what had been learned during those 9 years of patient watching. And it is a gentle thing to consider, this passing of knowledge from one mission to another, like the way a river feeds into a delta and the delta spreads outward into many channels, each one finding its own path toward the sea while still carrying the same water that fell as rain somewhere far upstream. And in this way Kepler's legacy did not end when the spacecraft turned its cameras away from the stars for the last time, but rather continued onward, informing the design of new telescopes, shaping the questions that scientists would ask, and providing a foundation of knowledge about planets around other stars that would guide astronomical inquiry for decades to come. The most immediate inheritor of Kepler's work was a spacecraft called TESS, which stands for Transiting Exoplanet Survey Satellite. And this mission launched in April of 2018, just a few months before Kepler's fuel finally ran out, so that for a brief period both telescopes were operating at the same time, one winding down and the other just beginning its work. And there is something rather comforting in that overlap, in the knowledge that the search for planets did not pause even for a moment as one mission ended and another began, but rather continued without interruption, as though the universe itself were being courteous enough to provide a seamless transition. And TESS was designed from the very start to incorporate the lessons that had been learned from Kepler's experience, both the triumphs and the difficulties, so that in a very real sense TESS can be thought of as Kepler's child, built with the wisdom that only comes from having done something once before and having paid close attention to what worked and what did not. The strategy that TESS employs is quite different from the one that Kepler used, and it is worth spending a moment to understand this difference because it illustrates how the same basic technique, the detection of planets by watching for tiny dips in starlight as something passes in front, can be applied in very different ways depending on what questions you are trying to answer. And Kepler's approach, as we have discussed at length, was to stare deeply at a single patch of sky for years at a time, watching the same 150,000 stars continuously, never looking away, building up an exquisitely detailed record of how each star's brightness changed over time. And this deep stare strategy was ideally suited for finding planets with longer orbital periods, planets that might take months or even years to complete a single orbit, because you needed that sustained attention to catch the infrequent transits of such worlds. And it was also well suited for finding smaller planets because the longer you watched and the more transits you accumulated, the more you could average together the tiny signals and pull them out of the noise. TESS takes a different approach entirely, one that trades depth for breadth, and instead of staring at one small region of the sky for years, TESS surveys nearly the entire sky, dividing it into sectors and spending roughly 27 days observing each sector before moving on to the next, so that over the course of 2 years it observes almost the whole celestial sphere. And this all-sky survey approach means that TESS can find planets around stars that are much closer to Earth and therefore much brighter than the distant stars in Kepler's field. And brighter stars are easier to study with other telescopes, easier to examine for signs of planetary atmospheres or to measure with precise velocity techniques. So TESS was designed specifically to find planets that would be good targets for follow-up observations, planets that we could study in greater detail with other instruments. And in this way TESS and Kepler are complementary rather than redundant. each one answering different questions and together providing a more complete picture than either could offer alone. The decision to design TESS in this way was directly informed by what Kepler had taught us. Because Kepler had demonstrated that small planets are common, that rocky worlds exist in abundance throughout the galaxy, and once that was established, the next logical question became not how many such planets exist, but rather what are they like? What do their atmospheres contain? What conditions prevail on their surfaces? And to answer those questions you need planets around bright nearby stars that can be studied in detail. So TESS was built to find exactly those planets. And the entire rationale for the mission grew out of the statistical results that Kepler had provided. A lovely example of how one scientific project can give rise to the next in a chain of inquiry that extends forward through time. And speaking of studying planets in detail, we should mention the James Webb Space Telescope. That magnificent infrared observatory that launched in December of 2021 and began science operations in the summer of 2022. Because Webb possesses the ability to examine the atmospheres of exoplanets in ways that were previously impossible. Looking at the light that passes through a planet's atmosphere as it transits in front of its star and analyzing that light to determine what molecules are present. Whether water vapor or carbon dioxide or methane or other compounds that might tell us something about the conditions on that world. And this technique, called transmission spectroscopy, requires that you already know where the planets are and when they will transit. Which means that Webb depends on the discoveries made by earlier missions like Kepler and TESS to provide it with targets. So in a sense Webb is another of Kepler's children. Not in terms of how it was designed, but in terms of the science it pursues. The questions it asks about planets that Kepler was the first to find. And the thousands of planets in Kepler's catalogue represent thousands of potential targets for atmospheric characterization. Worlds whose basic properties Kepler determined and whose deeper secrets Webb may one day reveal. There are other missions as well, either in development or in planning stages, that build upon what Kepler accomplished, and one of these is called PLATO, which stands for Planetary Transits and Oscillations of Stars. And this is a European Space Agency mission currently scheduled for launch in 2026. And PLATO aims to combine the best aspects of both Kepler and TESS, offering the long continuous observations that Kepler pioneered while also covering a larger area of sky than Kepler did and focusing on brighter stars that are amenable to detailed follow-up. So it represents a kind of synthesis of the two approaches, taking the lessons learned from both missions and attempting to achieve something greater than either. And the design of PLATO with its array of 26 individual telescopes working together grew directly out of the experience accumulated during the Kepler and TESS missions, incorporating strategies for handling the challenges of long-duration photometry that were first developed or refined during Kepler's operation. Another forthcoming telescope is the Nancy Grace Roman Space Telescope, named after the pioneering astronomer who played such a crucial role in the development of the Hubble Space Telescope. And Roman is a NASA mission that will carry out a wide range of astronomical investigations. But among its programs is a component dedicated to finding exoplanets through gravitational microlensing, a technique quite different from the transit method that Kepler employed. And microlensing works by watching for the slight brightening that occurs when one star passes almost directly in front of another as seen from Earth, and the gravity of the nearer star bends and magnifies the light of the more distant one. And if the nearer star happens to have planets, then those planets can produce additional brief brightenings in the light curve, tiny signatures that reveal their presence. And this technique is sensitive to planets that the transit method tends to miss. Planets in wider orbits around their stars. Planets that might never transit from our vantage point. So Roman will help to fill in gaps in our knowledge about planetary systems. providing a more complete census when combined with the results from transit surveys. And the statistical framework for understanding what Roman will find is built in part on the foundation that Kepler established. Because Kepler taught us how common various types of planets are in the inner regions of planetary systems, and that knowledge helps us interpret what Roman discovers about planets in the outer regions. Looking even further into the future, there are planning efforts underway for something called the Habitable Worlds Observatory, a flagship mission concept that aims to directly image Earth-like planets around other stars, actually capturing light from the planets themselves rather than merely detecting their presence through the dimming they cause when they transit. And direct imaging of small rocky planets is extraordinarily difficult because such worlds are so faint compared to their host stars, billions of times fainter, like trying to see a firefly hovering next to a searchlight from 1,000 kilometers away. And achieving this will require telescopes of remarkable size and precision, with instruments designed to block out the overwhelming glare of the star while preserving the feeble light of any planets that might orbit nearby. And the science goals of such a mission trace back directly to what Kepler taught us, because Kepler demonstrated that Earth-sized planets in the habitable zones of Sun-like stars exist in meaningful numbers, that they are not rare flukes but a normal outcome of planet formation. And knowing this made the case for investing in the technology needed to someday photograph such worlds, made the enormous effort worthwhile because Kepler had shown that the targets we hope to image are actually out there waiting to be found. Meanwhile, on the ground, new instruments have come online that continue the work of characterizing planets first detected from space. And one notable example is ESPRESSO, which stands for Echelon Spectrograph for rocky exoplanets and stable spectroscopic observations, a spectrograph installed at the European Southern Observatory's Very Large Telescope in Chile. And ESPRESSO can measure the velocities of stars with a precision of about 10 centimeters per second, an almost unimaginable level of exactitude. The speed of a person walking slowly across a room, measured from light years away. And this precision allows astronomers to determine the masses of small planets discovered by transit surveys. Because when a planet orbits a star, the planet's gravity tugs on the star and causes it to wobble ever so slightly. And measuring that wobble tells you how massive the planet must be. And when you combine the mass from velocity measurements with the size from transit observations, you can calculate the planet's density and begin to understand what it might be made of, whether rock or water or gas. And many of the Kepler planets have been studied in this way. Their masses determined by ground-based spectrographs, their natures revealed through the combination of space-based and ground-based techniques working together. It is worth noting that many of the scientists and engineers who worked on Kepler have gone on to contribute to these subsequent missions, carrying their experience and expertise forward into new projects. And in this way, the knowledge gained during Kepler's development and operation has propagated through the scientific community, embedded in the minds of people who now help to design TESS data pipelines or plan PLATO observing strategies or develop atmospheric retrieval codes for Webb. And this human dimension of Kepler's legacy is sometimes overlooked, but it is really quite important. Because scientific knowledge exists not only in papers and databases, but also in the skills and intuitions of the people who do the work. And a mission like Kepler trained a generation of researchers in the art of extracting tiny signals from noisy data, of thinking carefully about systematic errors, of developing statistical frameworks for interpreting large catalogues of detections. And those researchers have dispersed to universities and laboratories around the world where they continue to apply what they learned, teaching students and postdocs who will someday work on missions that do not yet have names. The observing strategies that future missions employ owe a great deal to what Kepler demonstrated about the value of long baseline continuous observation. Because before Kepler, it was not obvious that staring at the same stars for years on end without interruption would be scientifically productive. There were concerns about whether spacecraft could maintain the necessary stability over such long periods, or whether the data would become too corrupted by systematic effects to be useful. And Kepler proved that these concerns could be overcome. That with careful design and clever analysis techniques you could indeed watch stars for years and learn things that would be completely inaccessible to shorter observations. And this proof of concept has influenced how subsequent missions are planned, providing confidence that long-duration photometry is a viable and valuable approach. And missions like PLATO that require years of continuous observation to achieve their scientific goals are built on the foundation that Kepler established by demonstrating that such observations actually work. The target selection strategies for future missions have also been informed by Kepler's statistical results. Because Kepler taught us not just that planets exist, but how their occurrence rates vary with stellar type and orbital period and planet size. And this information allows mission planners to choose their targets more wisely, to focus on the kinds of stars most likely to host the kinds of planets they are searching for, rather than observing blindly without prior knowledge. And in this way, Kepler's catalogue serves as a guide for future exploration, a map of where the planets are most likely to be found. And missions can be designed more efficiently when their designers know something about the underlying population they are trying to sample. So Kepler's statistical legacy continues to shape the field even as the specific planets in its catalogue recede in attention, because the general principles derived from those thousands of detections remain valuable indefinitely. And so the torch has been passed. From Kepler to TESS and onward to missions not yet launched and some not yet built. A progression that will continue for as long as humans remain curious about the planets that circle other stars. And each new telescope builds upon what came before, standing on the shoulders of its predecessors and reaching a little higher, seeing a little more clearly, answering questions that could not previously be asked. And Kepler's place in this progression is secure, as the mission that opened the door, that transformed exoplanet science from a field of individual discoveries into a field of statistical populations, that showed us for the first time how common planets truly are and gave us reason to believe that somewhere out there, perhaps not so very far away by cosmic standards, there may be other worlds not so different from our own. In this way, Kepler continues to contribute to our understanding even though its cameras have long since gone dark. Through the missions it inspired and the scientists it trained and the statistical framework it established and the thousands of confirmed planets still being studied and the many more candidates still being analyzed. And this ongoing contribution is perhaps the most fitting legacy for a mission that was always about patience, about the slow accumulation of data over time, about waiting and watching and letting the universe reveal its secrets at its own unhurried pace. Because the benefits of that patient observation extend far beyond the mission itself and continue to unfold year after year as new telescopes come online and new analyses are performed and new understanding is achieved. And there is something rather beautiful in that, in the way that 9 years of quiet observation can ripple outward through time, influencing the course of scientific inquiry for decades to come, long after the spacecraft itself has fallen silent.